Hi, and welcome to Hands-on Computer Vision with OpenCV 4, Keras, and TensorFlow 2.0. My name is Rajiv Ratan, and I'll be your course instructor. I hope you're super excited to start learning about computer vision. So let me just tell you a bit about myself. I've got 5 years experience working as a data scientist, primarily in the areas of computer vision. Currently employed as a senior data scientist and a computer vision mentor. I graduated from the University of Edinburgh with a master's in artificial intelligence, and I've worked at several London startups over the last 5 years. I'm very passionate about deep learning, particularly in areas involving computer vision. But enough about myself. Let me talk about the course. So this course is split up into 6 sections. Firstly, we start with section 1, where I introduce computer vision with OpenCV. In section 2, I take you through some simple image manipulations using some OpenCV operations. In section 3, we take a look at image segmentation and object detection with OpenCV. In section 4, we take a look at machine learning and deep learning and how it's applied in computer vision. In section 5, we take a look at more advanced deep learning. We're talking about advanced convolutional neural networks to be used for image recognition, facial recognition, and gesture recognition. And in section 6, we take a look at topics like transfer learning, using deep learning for object detection, and lastly, we finish it off with neural art style transfer. In the first section, I guide you through installing all the tools needed for this course. You'll install Python, OpenCV, and TensorFlow. You'll then start exploring some simple concepts in OpenCV such as grayscaling, color spaces, and drawing on images. In section 2, you'll start performing some more advanced operations in OpenCV, such as image manipulations, cropping, edge detection, blurring, thresholding, scaling and resizing, dilation, erosion, and bitwise operations. In section 3, we learn the ins and outs of image segmentation and simple object detection, including face, vehicle, and eye and people detection. You'll learn how to extract and identify shapes in images, lines, circles, and blobs. In section 4, you'll learn how machine learning is applied to computer vision. You'll learn how neural networks and convolutional neural networks work, and learn how to start building them using TensorFlow 2.0 with Keras. You'll learn how to build your own image classifiers to detect handwritten digits. And now in section 5, we dive deeper into convolutional neural networks and create more complex image classifiers. Starting with a classifier for sign language, you'll learn how to create your own dataset to build your own gesture recognition system. We'll then take on applying deep learning to face recognition, where we do face similarity and build a real-time video facial recognition system. In section 6, you'll learn about using pre-trained ImageNet models. You'll learn how to do transfer learning, and then we'll explore deep learning object detectors using pre-trained models as well. You'll learn about RCNN, single shot detectors known as SSDs, and YOLO, and then you'll get to use these advanced detectors on your very own images. And finally, we'll end the course with a very cool project on neural art style transfers. So what are the goals of this course? Well, firstly, you'll learn how to use OpenCV to perform many computer vision algorithms such as edge detection, contouring, and many more. You'll learn to apply machine learning and deep learning computer vision tasks using TensorFlow 2.0 with Keras, and then you'll understand deep learning, particularly convolutional neural networks, and how to apply them to computer vision. You'll understand how to use pre-trained models for image classification and object detection, and then you'll learn how to create your own art using neural style transfer. So by the end of the course, you'll be able to create your very own convolutional neural networks and create your own datasets. So what about the prerequisites for this course? Well, you'll need a basic laptop or PC with a modern browser and a moderately fast broadband connection to download or view your videos. Next, in terms of skills, you'll need to know some Python basics and some NumPy basics. However, the programming in this course isn't too intense, and I step you through the code in all of the exercises. Lastly, in terms of knowledge requirements, you need some familiarity with basic high school level maths, and some basic knowledge of machine learning would be very helpful, but again, none of these are assumed. So now, let's get started. Hi, Introduction to Computer Vision with OpenCV, where I guide you through the setup of all the computer vision tools that you'll be using in this course. That includes Python, OpenCV 4, and TensorFlow 2.0. So let's take a look and let me show you what actual versions of the tools we'll be using in this course. So we start with Python, and the minimum version of Python 3.6 is necessary for this course. We ideally use 3.7. Possibly, if you're doing this course months later or years later from its release, you can probably use Python 3.7, 3.8, 3.9, maybe even version 4.0 if it ever comes out. Secondly, we're going to be using OpenCV 4.x. Now, you can use 4.0. We're going to use 4.2, and everything should be similar in later versions of OpenCV 4.x. Similarly, the third module we'll be using and focusing a lot on is TensorFlow 2. Now, TensorFlow 2.x, I fully believe any version 2.x and above will be supported by the code on this course. We specifically use version 2.10 in this course. Now, I'm going to take you to some important links here. Now, these links are subject to change sometimes. However, these core links should remain the same. And if you follow my install guide, you'll probably be able to find everything you need to find just by searching for it on Google. These are the 3 main things you'll need. Anaconda is our data science distribution platform that comes with Python version 3.6. This is what we'll be using in the course. Then we're going to download TensorFlow. Well, actually, I'm not going to download TensorFlow. You're going to install the module directly from the command line using pip. So I'll show you guys how to do that shortly. And then you're going to get course code from this GitHub repository here. So let's get started with our install as I guide you through all the steps needed to set up your computer vision modules. So firstly, go to Google and let's start downloading Anaconda with Python. So Anaconda, just type in Anaconda Python here in your Google search engine, and that should bring up the Anaconda page here. So just click this link here. And now what I want you to do is scroll down a bit to the individual edition and press download now. That brings up a page here where you have to select the version appropriate for your system. You can choose Mac, Linux, and you can actually look at the 32-bit or 64-bit versions as well. Now, I'm going to want you to use the Python 3.7 version and download the version that's suitable for your system, whether it's 64-bit or 32-bit. So when that's finished downloading, click on the installer, and I'll go through the install here. Just use the default settings when the install box pops up, default directories. Leave this alone. You don't have to click the first one, and it just takes a few minutes to install. I'm fast forwarding it through here. Then press next, next again, and you can bring this up if you want to learn more about Anaconda on your own. It's fully up to you. So now we're finished installing Anaconda. So when that's finished, I want you to go to your start menu, and you'll find your Anaconda tree install here. Click on Anaconda prompt, not Anaconda PowerShell, Anaconda prompt, and that brings up this command prompt dialog box here. So the first thing I want you to do is type out conda create -ncv --clone base. What you're doing here, you're creating a new environment for all your deep learning packages and libraries that we're going to be using in this course. Now, there are just two we're going to install after this is complete. That is OpenCV and TensorFlow. So just press yes when this comes up. This dialog box will pop up about 4 or 5 times during the install. Just press yes for each one. And what you've done, you've cloned your base environment in Anaconda. So now you have a brand new clean environment to mess with to install your own libraries. So when it's done, I want you to type conda activate CV, and that way you'll see there'll be CV in this bracket here. It'll change from base to CV after you type this out, and there we go. So your environment has been successfully created, a CV environment. So now just clear the screen, and I want you to update pip. So we're going to do type pip install -- upgrade pip, and there we go. So just make sure your pip is up to date to the latest version before continuing. Now I'm going to install OpenCV. So we go pip install OpenCV -Python. This will install OpenCV. This should take about a minute, maybe a little longer, depending on your internet speed and system processing power. And there we go. So we're finished. Now we're ready to install TensorFlow. So to ensure you're using the latest version of TensorFlow, what I want you to do is type pip install -- upgrade TensorFlow. And that will take you to the install here. And it should be quick anyway. And once that's done, you should have OpenCV and TensorFlow. However, we can run a test here and just make sure everything works. You can press Python, and this brings up the actual Python interpreter inside of a command prompt. And then you can import CV2, press enter, that executes successfully. Then do import TensorFlow as TF. You may get a warning here. However, that's fine. However, if you do get a missing DLL error here, you're going to need to download the C++ Visual Studio redistributable files, and I'll show you how to do that now. So now let me show you how to find the link to redistributable file we need. So go to tensorflow.org/install/pip, and that brings up this site here. Now, this takes you to the actual link of the C++ redistributables that you want. This is it right here for Windows 7 or later. Click this link here, and now that brings up the distributable files you want. Now, if you have an x84 64-bit system, click that, and it installs, downloads, and installs. Well, you install it afterward. Likewise, if you have x86 32-bit processor, you can download and run that one as well. So now we just go through the C++ redistributed installations. Fairly simple. Just click next from the installer. And there we go. It's successful. So restart your computer after it's installed. So there we go. It's completed and it's successfully installed. So you can restart your computer if you need to. I don't need to because I already have it installed. And now let's move on to the next part of install. After you've restarted, what I want you to do now is go to the GitHub link I supplied to you in the presentation. What you can do now is download the course code from this link. So what you do is you go to this green button here and press download as zip. And there we go. You don't have to sign in or sign up just yet. Code downloads at the bottom left of the screen. And you're fine right there. So then what I want you to do is go to use a WinZip if you have WinZip installed and extract the files right here just so you know where they are. It should take maybe a couple minutes to scan to unzip. And then what you can do is you can cut this file and place this into your main user directory here. Now the main user directory is just your C drive users / your username. My name is Rajiv, so I'm going to that directory and paste the files there. Now the reason you're putting the files here is because this is where, when you bring up your IPython notebook, which you'll see shortly, it defaults to this directory here. So now you can see my code is here. These are the sections from the course. Everything is set up correctly. Now let's launch our IPython notebook browser. So go back to Anaconda here, and you should see something like this, Jupyter Notebook CV in brackets there. That brings up your IPython notebook server, which would launch your default web browser. And it takes a couple seconds here, depending on how many files you have in this directory, your main user directory. And there we go. So all of your code files are here in this directory, which we cut and paste previously before. So now let's start using our IPython notebook. This is what you're going to be running all your code in. So let's go to new in the top right and open a new Python tree file. So what you can do here, this is a Python command line interpreting system here. So you can import CV2 and press enter and Alt to run. Likewise, you can import TensorFlow and press Alt and enter to run. When you run this, you'll see a number coming up on the left, 1, 2. You can even do some addition here just to make sure it works. And if you wanted to rename your window, just rename the file like that. So now let's actually just test some of the code here from the notebook. So go to section 1's code, and you'll see the code right here. So this is code you'll be using in the course with all the comments and guidelines for it. And basically, you're done now. So just to quickly summarize what you've learned in this install guide video, you've learned how to install Anaconda, which is our Python data science platform that we'll be using throughout this course. You've learned how to create a new environment where we install all our computer vision packages, which are TensorFlow and OpenCV. Then you've learned how to download our code from GitHub, and then you started running your code in your own IPython notebook. So now stay tuned. We'll move on to image formation and digital representation in the next video. Thank you. Hi, and welcome to the video, where we take a look at image formation and the digital representation of images. So firstly, how do computers see? Well, firstly, and can they see? Imagine you're a computer and you have an advanced artificial intelligence robot and you're able to basically identify a motorbike out of a cluttered scene like this and even identify the model. Now that's pretty cool, and that's far from how computer vision or computers actually see, because computers don't see like how we do. How we see is extremely good. The human brain has a magnificent, amazing capacity to see and visually understand what is being seen. We can identify hundreds of thousands of objects in one photo, or what our eyes see, immediately, quickly, and get context. This is what makes us humans so intelligent and so capable, our vision. And that's why our brain is actually a lot of our resources in our brain are dedicated to vision. But how do computers see? Because computers don't see the world like this at all. This is what they see, just a bunch of raw numbers streaming from a camera sensor or an image file or video file, and it's just going to be different numbers representing blue, green, and red. Perhaps that's one of the color spaces, and we'll learn about color spaces soon. But imagine you're a computer and you're seeing this. Now this is very hard to make sense of, and that's what the goal of computer vision actually is. Now let's stop here and think about something. What exactly are images? Or what is vision, I can ask? What is this light? What are these colors? What are these things we're actually seeing or coming to our eyes? Well, it's basically the two-dimensional representation of the visible light spectrum. And you may remember this from your high school physics class, that EMS, electromagnetic spectrum, has all the different waves here of various wavelengths. You can see from largest wavelength to smallest wavelength, which is gamma rays, and the visible light spectrum is part of this EMS. And this is it right here. You can actually see, it goes from invisible to dark red. Red is the longest wavelength, blue is the shortest wavelength here. And you can actually see it right here as it goes. We can actually see the colors. Actually, this would be the shorter wavelength here, this kind of pink indigo color right here. And now this is basically what we see. This is the light spectrum. And combining different colors here gives us complex images like this. So basically anything comprised of different colors in the electromagnetic spectrum. And that's what makes vision cool. It's just a reflection of different light waves from objects that are coming to our eyes. And it gives us these colors. And this is what images essentially are. So now let's move on to how are images seen digitally. So computers store images in a variety of formats. However, they all involve mixing some of the following, which are colors, hues, brightness, and saturation. And you'll take a look at these different representations shortly in the future video. However, the most common one and the easiest one for us to understand is the BGR, which is the blue, green, red, or RGB. BGR is what we say in OpenCV, that's what it stores it in. However, it's commonly stored as RGB. And what this means is that each pixel here, so imagine this is a pixel of an image. Imagine your screen is comprised of thousands of pixels here. Now imagine we're breaking it down, we're just looking at 10 pixels by 10 pixels here. If you were to zoom into like the corner of your screen with a magnifying glass, you would probably see the mixed individual arrays showing red, green, and blue. Now, how do we get white and different colors out of it? Well, it just means it's different brightness of or intensities of these three colors here mixing that gives us the color we want to see. So imagine in each pixel here, we store three values, and these values range from 0 to 255, 255 being the brightest, 0 being the darkest, or essentially black at that point, because it's not, this means totally off. And this mixture here is what gives us our colors. So imagine now, we want to get the color yellow out of these three colors. That's just red at max, green at max, and blue at 0. So that's pretty cool. So now if we wanted to create an image, something simple like this here, you can actually see the different mixtures we'd need to make this. This is all at max, all at max, all at max, max being 255. To get white, when I say all at max, we need red, green, and blue to be at 255. Green now, you can just reduce red and blue accordingly until you get a nice shade of green. Brown would be a different color. This is a yellow. So you can see how by mixing different colors, individual grid here, individual pixel points, you can generate nice images. So now imagine this is blown up to like 1,000 by 1,000, and you have like almost a million pixels at that point. Actually, you would have a million pixels at that point. Then you can get complex images, high resolution images out of things like screens and tablets, displays and TVs and stuff. So that is core of how images are represented digitally. Now, let's talk a bit about arrays, because arrays are important in OpenCV, Python, and computer vision with understanding how images are actually stored. So firstly, let's take a look at this. This is a one-dimensional array. What this means here is just that we have a 0 index. This means that there's a value here, and we index it by this first column number here. Now, a two-dimensional array is like a table. We have different values here. We can have a value here, value here, value here, and this is like the index here. So we have 2, 1, 3, 2. That gives us a value here. So this is how we can represent images here. But how do we store three values in one spot? We have a three-dimensional array now. So this is essentially how a three-dimensional array can be visualized. So now you can see how, like a display, we can store the different colors, these three colors here, to give us to put colors at our points here. So I hope you understand this. Now, just so you know, in a black and white, or I should say a grayscale image, because black and white images are essentially just shades of gray, we don't need a three-dimensional array. We just need a two-dimensional array. So going back to it here, you can have one value here, and that value will give you a shade of gray that is from 0 to 255. That's the darkest shade of gray at 0, and the lightest shade at 255. So you can actually represent what we refer to as black and white images, which are really just grayscale images, like this. Now, let's take a look at what makes computer vision so hard. Now, before we get into what makes computer vision hard, let's just take some time to appreciate how good our brains are at vision. In fact, almost 20% or at least 20% of our brain is dedicated to visual processing. And that means that things that are super easy for us are now super hard for computer vision. And there are many factors that present challenges to computer vision. And these are things like camera sensor or lens limitations. You can see there's noise here. If it's too zoomed in, we can't actually make out what we're seeing. There's different viewpoint variations. This is all the Statue of Liberty at different angles. It's going to be tough for a computer to actually figure out it is in fact the Statue of Liberty. Changing light conditions. This is a view from my apartment during the daytime and during dusk. You can see how vastly different it looks, even though it is the same scene we're looking at. Issues of scale. This is the Taj Mahal zoomed out all the way and now close in. Is it the same building? I think it is, but is it really? There's non-rigid deformations. This is a horse galloping, this is a horse resting. Same for this dog here. They look so different. So non-rigid deformations are very complex for computer vision tasks as well. Things like occlusion. Remember, this horse is partially hidden by these trees. Is it really a horse or is it multiple horses? What is it? Things like clutter. Figuring out that this is an octopus that's camouflaged amongst these stones is going to be pretty difficult. I mean, some humans won't have this trouble with this, and some people will definitely have trouble finding, say, a specific sign in an image like this. This clutter presents a lot of difficulty. And then there are things like object class variation. Look how many different types of chairs there can be. This is just one sample search from Google Images, and there are tons of different chairs here. Likewise with dogs. Dog breeds are so different. You can have a pit bull or a chihuahua, both being classified as a dog, but they look entirely different. And then there's ambiguous optical illusions. Is this a wine glass or a vase, or is this two faces? Is this really alligators here, or is it a drawing? And what is this guy doing? Is he faking or not? We don't know. So what have we learned in this lesson? We've learned how images are represented digitally, that our brains are incredibly good at visual processing, and we've learned what makes computer vision so hard. So now let's move on to getting started with OpenCV in the next video. Thank you for watching. Hi, and welcome to the video on getting started with OpenCV 4. So what exactly is OpenCV? Well, you must have taken this course for a reason. You want to get started in computer vision, right? Well, OpenCV is a de facto default computer vision library that you will use in any language. However, it's highly developed for C++ and Python right now. So OpenCV firstly stands for Open Source Computer Vision, which is easy enough to understand, and it's basically a simple acronym given to one of the most powerful computer vision libraries that exist. It's an entire assortment of hundreds of computer vision algorithms and functions that are primarily aimed at around real-time computer vision. And it was originally developed by Intel, Intel who makes all those Pentium processors. And the library is cross-platform and free to use under the open source BSD license, so that's very useful for all your projects, be it research or commercial. So the first major release of OpenCV was in 2006, version 1, and this was a landmark occasion because it enabled all these developers across the world to start using all these advanced computer vision functions that we would either have to rebuild from scratch or just find them or pay for them in other libraries. And the second, much more mature and developed version was released in 2009, and this version honestly hasn't changed much since 2009. It's just gotten better and better and added more functions. But OpenCV 2.0 X was brilliant, and the third release was in 2015, and the fourth release was in November 2018. So the latest version right now is OpenCV 4.2.0, and that's of February 2020. And this is the version that's the latest stable release. And if you want to learn more about this whole computer vision library, you can go to opencv.org to learn more. So let's talk a bit about OpenCV. It was originally written in C++, and actually it's still written in C++. All of the core of OpenCV is C++ code, and basically we use it in Python because it has bindings for Python. And these bindings mean that we are able to execute and run underlying C++ functions, and we can basically use them in many other languages such as Python, Java, MATLAB, Octave. And there are OpenCV APIs in many other programming languages too, so it allows developers across many different systems to use OpenCV. And basically OpenCV has been extensively used in developing things like facial recognition, gesture recognition, robotics, object identification and classification, medical imaging, self-driving cars, and many other applications. And one of the great things about OpenCV right now is that it supports all the latest and popular deep learning frameworks such as TensorFlow, Torch and PyTorch, and Caffe. So it's quite versatile and quite useful. It's basically totally entrenched in the computer vision world. So essentially you cannot do computer vision without having to use or be familiar with OpenCV. So now let's actually go into our Python or IPython Notebook Explorer and actually execute some very simple OpenCV code so we get familiar with actually working with OpenCV. So what we're going to do, we're going to open and view images, we're going to get the dimensions of an image, and we're going to save those images after. So now let's summarize what we've just learned about OpenCV. So now you should understand what OpenCV is and why it's so important to the computer vision world. You also know a bit of the history of OpenCV and how it evolved over the years, and you've learned some very popular common applications of OpenCV in the computer vision domain. So now let's move on to using OpenCV in Python. So you're going to start using the practical aspect of OpenCV. You'll learn how to import, how to open images, how to manipulate some simple things, how to save images. So you're going to want to stay tuned for this because you're going to get your feet wet using OpenCV now. Thank you. Hi, and welcome to the video, using OpenCV in Python. Okay, so you saw how to launch your Anaconda Navigator in the previous video. So remember, every time you want to go into your code, you can bring up Anaconda Navigator. Remember, you want to switch to your CV library, and that changes here. If you didn't install a different library using Anaconda, it'll be in your base directory, so don't worry, okay? So now, program we're going to launch our code in is the Jupyter Notebook. So press launch here, and that brings up your IPython notebooks in your web browser. So here we go. It loads perfectly right here. It just takes a couple of seconds and your code will be installed or be placed in this directory here. So if you downloaded the code from GitHub, well, you would want to put your zip file, your extracted code in your base directory. I'm talking about your users directory in Windows. So every Windows user has a default Windows directory, which will usually be C drive users / your name. So I'll put a little text thing here so you can see what it looks like, for example. And when you're using WinZip to extract your files, I want you to extract it into that directory. That's because IPython or Jupyter Notebooks, default directory they load up in is your user directory. So it's going to be easy for you to find the code here. So now let's just click on the directory with the code. And you will see all the sections of your course, section 1, 2, 3, all the way to 6, and a little install guide text file in case you wanted to see how to install and set up everything, which you would have already done, but you can always go back to this file to check and see how to do it again. So the course is organized into 6 sections, and all the code is going to be in each section. Now, because I recorded this course with all the code initially in one big directory, I'm showing you guys how it's set up here because it's the first video, but in all the videos in the future, it is in the videos itself. It's going to be in one directory. So what's going to happen is that the numbering of the course, every code item is numbered here. These numbers remain consistent in all video. Or when I say just go to the code labeled number 12 may very well be in section 4, but it will be easy to find and you should have no trouble finding the code in this course because everything is well named and well labeled. So now let's start with section 1 in our introductory code where we're getting started using OpenCV. So the first section we're going to do is section 1 called getting started with OpenCV. So let's launch this IPython notebook, and to launch it, just click on it and it pops up in a new window here. And as you can see, you have all your code in this IPython notebook. So let me just explain quickly the structure of this notebook. In these IPython notebooks, we have what we call cell blocks here. And cell blocks are good because they allow us to run small segments of code here. And we can print, we can do many things. We can run entire program in these blocks if you so wish. However, why it's great for teaching is that we can run small pieces of code so we can illustrate concepts as we step through them. So we're going to run through a few beginning concepts here of OpenCV, and this is all very easy code. And luckily, everything here is well commented and well explained. So if you want to do this on your own, without watching the video or even after watching the video just to get more familiar with what's going on, you're free to do so. So now in the first block, what we're going to do, we're going to import OpenCV, and OpenCV in Python is labeled as the module CV2. So everything that's CV2 is really OpenCV. Now, the reason for the 2 is basically, and when OpenCV2 was launched, the OpenCV guys renamed the entire packages as CV2 by default. If for whatever reason you wanted to use CV, you can just import CV as CV and use it as that such. But I don't want to confuse you guys, so just probably just erase that knowledge from your memory right now because it's pretty much irrelevant. So what we're going to do is going to run this first block of code. So how did I do that? Press Control and Enter together. So you can run that here and it runs like that. You can also press Shift and Enter, also runs. And lastly, you can do Alt Enter as well to run a code block, and what it does, it runs this block and creates a brand new one under it. So I often alternate between all running code blocks by using Alt Enter if I want additional code block after, or Shift and Enter and Control Enter to do the exact same thing. So we can erase these code blocks by just cutting it here and deleting it. So if you just want to clean up your notebooks here, you can just quickly remove them here. But remember, once you delete a block here, it sort of disappears forever. There's no undo for deleting a code block here, at least not yet, to my knowledge. So just be careful when you're doing that. So now let's move on to finding out what version of OpenCV you're using. So we run this code block here and we see it prints out using the print statement in Python, prints the CV2 version right here. So this is the latest version of OpenCV as of April 2020. So I'm hoping you guys will have this version at least, or even a newer version in future. Now OpenCV 4.x, X meaning any future versions of OpenCV or even previous versions like 4.1 or 4.0, they all should be compatible with all the same code. If there's anything that's incompatible, you can contact me and I'll try to update the code to fix the issue. So now let's import NumPy. So what we're going to use NumPy for is that images are stored as NumPy arrays. So effectively, every time we're loading an image from OpenCV, it's a NumPy array. So if we're doing any future operations on that image that does not involve using OpenCV, you're going to want to use import NumPy and use it. So when we say import NumPy as NP, every time we call something with a function saying np.something, we're using NumPy. Now again, this may be a little bit too much knowledge. If you're an absolute beginner, you can just sort of ignore this for now, just knowing that we're going to use it sometimes in the course, sometimes not. It's not always necessary, but when you do some sort of operations on the images, which you'll see in future video, just remember you can import NumPy and use it as such. So now let's get started finally with using OpenCV for something pretty cool. So what we're going to do, we're going to import CV. Now you don't always need to do this in every cell block. Once you import something in one cell block, it remains imported. You can use it in every cell of this notebook. So that's pretty cool. So what we're going to do, we're going to read an image here. So by reading an image, we just point this function cv2.imread to load this image here, this input image, this test image we're going to use, and store that variable called image here. And then we're going to use the cv2.imshow function. That's a function that displays the image on our screen. So we just give window name this here, loading a first image, and we tell it which image we want to load here. So this function takes two parameters. One is a name, one is the image variable we want to load. And then cv2 wait key, we call this function because otherwise if we don't, window just stays on top and we can't really do anything with it. So it has to wait for a key to be pressed so we can move on to the next step of our program. And fortunately, the next step of our program is to destroy that window. So let's take a look and see how this runs. There we go. So that's our test image here. This image is in your base directory here. You can find this images here, input. That's the directory I was pointing it to. And let's get back our image. So as I said, cv2 is waiting for some command because right now it pauses the program at this point. It wants you to do something with the image. So what we're going to do is going to hit any key and the window will close. So consider this like a pause key here that is waiting for input. So when you load an image and you want it displayed for a second, we can do it here. So now let's do something else. And that something else is actually exactly the exact same thing as we did before, but with all the extraneous comments here. Just going to run this simple program here. There we go. So notice we have a 0 here. We didn't have a 0 before. The 0 acts like the same as leaving it as blank. However, sometimes in some operating systems like macOS and Linux, you do need to have an input 0 here, or 1 sometimes, just to make it work correctly. So I'm not going to go into too much detail about why it works if it doesn't work for you, because what happens sometimes on macOS, if you don't have the 0 here, everything just freezes and pauses here and you can't do anything to progress to the destroy Windows command, which is the last command in our cell. So now let's see what we're going to use NumPy for. So we're going on to this cell here. So we're importing NumPy as NP, as I said before, which we already did before. And what we're going to do, we're just going to print the shape of the image. So when I say shape of the image, tell me what you think this is. I know you can't actually tell me, but think about it. What do you think this is? So you saw the image before. This is the image here. It looks fairly nice, nicely detailed. Well, in case you haven't figured it out, this is a resolution of the image. As in when I say resolution, I mean height, width, and what's this tree about? This tree is actually the color depth. Remember, images are comprised of different color spaces. So remember we have RGB color space here. That's what this is. This is the red, green, and blue color combinations. Every pixel, we have a color combination for red, green, and blue. So that's why shape is like this here. Three-dimensional array. And these are the quantities of the dimensions in this array. So now if you want to just see some more detail here, just have these print statements here to explain it. And what we're doing here, we're using the shape thing here, the shape function. I shouldn't call it a thing, it's actually a function. What it does here, remember this returns a tuple. Consider a tuple to be an array here, in case you don't know the Pythonic definitions of a tuple and an array. But either way, we can actually get the first value here, which is 597, by addressing the first value in this array. The second value would be addressed by index 1, and the third value by index 2. So you can see these are the pixels here for the height, the width, and the depth with color components. So you can see it's nicely displayed here. So it's a good little function just to get familiar with. Now, what about saving images? Suppose we have done some fancy cool OpenCV operations on our image, and we want to save it. Well, we can use this simple function called cv2.imwrite, and you can just give it a name, and we can actually use many different names here. So you can use JPEG, PNG, BMP, TIF, I believe, or FF actually. There's many others are supported by OpenCV's imwrite function, and image was a variable you want to save. So remember we loaded this image here as From our input, we pointed it to the directory and we loaded it and we call it image here. That's our variable. Well, let's go back down. This is what we're going to do. We're going to save the variable image as output JPEG. So let's do this here. And it returns true. True meaning it ran successfully. Now also do it and change the image file format to PNG, which is portable network graphics, and does it there. So now you should see these two files here. These two output files are correctly saved here. And you can see the difference in sizes. PNG is actually much bigger. It's 4 times bigger, to 1.3 megs, whereas the JPEG, which is compressed, which is at 300K. So that's it for this video. You got a quick introduction to OpenCV. There's some basics with loading OpenCV, how to load images, how to use NumPy, how to get the image dimensions, and how to save images here. So to quickly summarize what you've learned in the video, you've learned how to import OpenCV in Python, what NumPy and use it when needed, how to view the image dimensions, which we did use NumPy shape function to determine, how to open images, you saw using cv2.imread, how to view images with cv2.imshow, how to save images with cv2. Do you remember? It's cv2.imwrite. So you learned how to use these basic functions in OpenCV. So now let's move on to the next video, where we get a closer and deeper understanding of color spaces and then how to apply grayscaling, which is a different color space that you'll see shortly. So now let's move on to the next video. Hi, and welcome to the video, Understanding Color Spaces and Applying Grayscaling. So firstly, what exactly are color spaces? Well, have you ever heard of the terms RGB, HSV, or CMYK? Well, if you're into professional photography or printing, I'm guaranteeing you've heard of these terms before. And what these are the names of color or very popular color spaces. And color spaces, also known as color models or color systems, all refer to mathematical models used to describe colors. So why do we need color spaces then? Well, as I just said, color spaces are needed to represent color. There are different ways we can actually have different parameters or different contributing factors that give us the color we want, okay? So different color spaces offer unique features, and those things are like for different applications like printing, or for representation in computer vision, or for photography. So the one we're dealing with, the most common and popular one in OpenCV is RGB. Oh wait, it's actually BGR. And that's just a funny little thing in OpenCV, where we do use the RGB color model, which is popularly known as colloquially in different systems. However, the order OpenCV stores the colors in is BGR, blue, green, and red. So that's our default color space in OpenCV, and it's also an additive color model. And what does additive mean? It basically means we have different intensities of red, going on the scale from 0 being the darkest, to 255 being the brightest. So we have different contributions of red, green, and blue that give us the color we want. So you can imagine we can get yellow by having different intensities here. We can just get red and green and decrease blue entirely, and then we get yellow, and that's how we get colors from the RGB model. And just a note here, OpenCV actually stores in BGR format, which I refer to here. So now let's talk about the HSV color space. Now this isn't as popular in computer vision, however it is very useful when you want to actually filter specific colors in a computer vision application. So how does it represent color? Now the additive model in BGR is quite self-explanatory, and you would have done this basically if you were doing art or painting as a child or as a student in college. However, how does HSV work? HSV represents the way humans perceive color. However, that doesn't help us too much because we need to take a look at a model cylinder here. So imagine we have one parameter being hue, and hue is essentially the color value, and it ranges on a scale from 0 to 179. We have saturation, which is basically how rich the color is here. So you can see it gets kind of pale here in this axis. Then as we go further along the saturation scale, it gets more vibrant. Value here represents brightness. So that's the z-axis in all of this. So as you can see, we go from lighter to darker as value goes from low to high. And hue basically is a color. So by changing saturation and value, and hue is how we get different colors using the HSV model. So HSV, like I said, allows color filtering, unlike RGB. Now, it's possible you can do color filtering on RGB. However, it's very, very difficult, and it's no point because HSV is so much easier. As you can see here, if you ever wanted to filter the red colors, you have a filter on hue scale from say 15 to 165, just a small range right here. Green is quite simple here as well. It's 45 to 75. Blue is around roughly 90 to 120. So as you can see, HSV lends itself perfectly for color filtering. So what about grayscaling? When we say an image is grayscale, we basically are talking about a black and white image. However, black and white images are not just black and white. They're comprised of shades of gray. And OpenCV, a grayscale image is even simpler to represent because it's not three-dimensional. It's effectively two-dimensional. So imagine we have a grid here. This is handwritten number 1 here. So if you were to represent this in grayscale, as you can see, every pixel here has a value. Remember 255 being the brightest, that's white. And the lower you go on this, as you can see, like these values here are quite dark. You can't even see the numbers here because they're almost black. They're much lower in value to 255 to 91 and 68 here. So that's how grayscale images work. And it's basically, as I said, just a two-dimensional grid where every pixel here has a value that represents the intensity of the level of gray. So just to quickly summarize what we've learned what exactly are color spaces, and we've taken a look at the RGB, that's red, green, blue, and the HSV, that's hue, saturation, and value, color spaces. So now let's go into OpenCV and actually play with some color models and do some grayscaling on some images as well. Thank you. And welcome to the video, OpenCV, and play with some color models and do some grayscaling on some images as well. Now to begin our video on grayscaling color spaces, I want you to open this file here from your IPython notebook browser. It is titled 2 Grayscaling and Color Spaces. So let's load this file, and what this file has in it is blocks of code that are going to basically teach you how to convert an image to grayscale, and then how to basically view the components, the individual channels in an RGB image, and how to basically interfere or play with or boost different color components. And then we're going to take a look at the HSV color space as well in the last cell here. So to begin with, let's convert a color image. We're going to load the image here with this code, which you've seen in the previous chapter. And what we're going to do, we're going to use this function called cv2.cvtcolor. And this function takes two inputs. It takes the image that we're loading here, and it takes this value here. Now, this value is a function. It's a cv2 function here that converts a color image here, color BGR, to gray. Now, there are loads of different component functions we can use in OpenCV. This is the one we're going to use to convert it to grayscale. So we're going to rename this image here because it outputs an image output here. And we're going to call this gray_image. And then we're going to display that image here. So let's now run this block of code. So that's our nice color image. And whoops, didn't run that there. Let's click on the image. And there we go. Our nice grayscale image looks quite good. You can see it basically adjusts perfectly. It looks the same image. However, all the color components are now shades of gray. So that's quite cool. And the algorithm it uses for this is basically finding the average of all the color components, red, green, and blue, at each pixel, and then gives you the average gray value here. And that's how it looks. So accurate. Okay. So if you want to read more about it here, you can click on these two links here just to get some more information from documentation. Looking at the individual channels in an RGB image here. So you're going to learn two more functions here. You're going to learn cv2.split function, which splits an image into the color components here. Now remember, the image here we've already loaded up here, so we don't have to reload it again. Once it's loaded into this notebook here and we run this code, it's loaded in the background of your basically IPython notebook. So what we're going to do is split this image into components here, and then we're going to create a blank image here. This blank image here is basically what we're going to use to basically show the different color components individually here. So we imagine we're creating a blank array of zeros in the same shape of the original image. That's why we use image.shape here. This is to capture the same dimensions here. And what we're doing here, we're just putting zeros in each two-dimensional color grid here. So this is the color grid for blue, color grid for green, and this is the color for R, which we got here. And the reason I print the shape here is that you can actually see the component because it's going to be in a grayscale dimension. Effectively, grayscale meaning a two-dimension. And what we're doing, we're just adding that three-dimensional array here. Use cv2.merge to merge it back. And that way, you can look at each color component separately, just like this. So this is pretty cool because what you can explore here is that there are a lot of details in the red and green components, especially the green. Now look at the blue. There's basically all dark shades in the blue. And that means that the original image didn't have much blue in the additive color space here that was needed to represent the color image. It's quite nice and interesting to explore images like this. It's not always necessary unless you want to dig deeper, but it's a cool thing to see. Now let's look at something else here. We're going to do the same thing here. However, we're going to look at this separately. So effectively what we're doing, we're not looking at each color component as a color image. We're looking at it as a black and white image now. So you can see this is a red and green with a lot of detail, very similar to our original grayscale image. However, the blue is a much darker image as we would expect. So what else are we going to do here? We're going to boost the blue here. So look at the code below these images here. Let me just shift this up slightly. And what we're doing here, we're adding 100 to the blue values here in the image. So by boosting the blue, we can see that now it has a blue tint or blue shade to that image here. This is the original image over here, and this is it with boosted blue. Now, remember the blue image was quite dark, all right? Now, what would happen if you added 100 to, say, the green components of the image? You would max out all of the green values, and let's see how it looks. It looks like this, which is quite different to how the boosted blue image looked. And that's because green is already high. And when we push the green even higher, it just messed with everything here in the image. So it looks a bit cartoony right now. Whereas if we did a blue, it looks like a blue tint. If you wanted to get a more realistic looking image with the green, don't boost it that much. Maybe like 30 or 40 would give you a more accurate representation of the image with the boosted greens. Actually, we can try it right now. Let's see how it looks. This part of the code. Second part of the code here. So you can actually see while the sky changed pink for some reason, the image color components here, there's less clipping. Clipping means it's maxing out in the colors here and saturating to one color. Is a lot less common here in this image. So it's quite a good experiment to play with. And now lastly, let's look at the HSV color space. So you remember the components, the hue, saturation, and value being intensity. Now let's actually look at them separately. Now there's two things to note with HSV images right now. Firstly, OpenCV doesn't have a way of representing HSV when it ImShow. ImShow treats everything as a BGR image. So that's why when we first look at the image here, in this line right here, it doesn't look like you'd expect. You expect it to look. Let's bring that back. There we go. So you can see the HSV image basically looks nothing at all like the original image. And that's because OpenCV is trying to represent an HSV image as a BGR. So don't think too much about it. Just know that OpenCV's ImShow does not work with HSV images in that color space. But what we can see here, we can look at the individual channels. Let's just space this out a little bit more. So you can actually see now how the hue channel, how much it contributes to the image, the value, and saturation channels. So this is a quite interesting thing to look at. You can see these areas on the mountains are high in saturation values, whereas the sky is low. Similarly, you can see the hues in a grayscale representation, how it looks. Remember though, since the hue is only up to 179, the image is always going to look quite dark because of how ImShow represents it. If you wanted to multiply by a factor to scale it to 255, you could. Wouldn't make a huge difference in my opinion. And you can look at the value intensity channel here as well. So you can see the brightest parts of the image was the sky, understandably so, and some of the flowers and mountain tops here as well. So this is just a way to explore what HSV images look like, okay? So that concludes this video here on grayscaling and HSV and BGR color spaces. So to quickly summarize what we've learned in this lesson, you learned about color spaces and what they are. You learned a bit about RGB or BGR and HSV color spaces. You understood how to split images into the individual components of RGB and HSV in OpenCV, and you were able to convert normal color images to grayscale in OpenCV. So let's move on to the next video, where we create and draw on images with OpenCV. Thank you. Hi, on creating and drawing images with OpenCV. Okay, so let's get started with drawing and creating images in OpenCV. So let's open this file here, number 3, drawing images, and it brings up our IPython notebook here. Good. All right, so the first thing we're going to do is we're going to create a black canvas image, and we're going to do this in 2 different ways, and I'll tell you why we're doing this in 2 different ways. Firstly, as you can see here, we're creating a black canvas here. We use numpy zeros because we just want black. Remember, black is number 0. So black is the absence of all colors, be it red, blue, or green. So we use numpy zeros here. We get an array of this dimension, which is 512 pixels by 512 pixels, and 3 dimensions here. So it's 3 layers of this. This is to indicate BGR or RGB color points, okay? So they're all going to be 0 here. So we're going to create a black color image using the color space. And in this case here, you see we left out a 3. That's because this is a grayscale. So I can just add this in here just to be more specific, okay? And this is going to be a grayscale black image. So they're going to look exactly the same. Ta-da! You can see they're both black, both exactly the same. However, this image here has 3 dimensions and it can support color, while this one can't. This one will just support shades of gray. So it's something that's not super important right now, but it's just good to know that you can have different color spaces and how you create them in OpenCV. So sometimes, whenever you're doing an operation that requires a grayscale image, you know what you have to do, and vice versa. So now, let's draw a line over our black square. And we do this by using cv2.line here, and this takes the following inputs here. This takes image, which is the image we're creating up here. It takes a starting point, ending coordinates, and it takes a color, and it takes the line thickness. Now it sounds quite simple, and let's see it in action. So let's run this, and this is exactly what we wanted. And why is it what we wanted? Because we specified 0, 0 as the starting point, that's this point here, and 511, which is the last point here. Now, remember, OpenCV uses this top area here as the 0, 0 reference point. So as we go here, basically 255 is somewhere here. So now let's actually start our line at, say, 255 and 255, and let's see how it looks. And it's exactly as we expected. So that's brilliant. So now you've learned to draw a line. Now let's learn to draw a rectangle, okay? So to draw a rectangle, basically we create our same black canvas image here, and we have very similar starting inputs to our function, which is cv2.rectangle. So we have the input image, we have our starting vertex, this is on the top left side. This is the ending vertex, so the opposite vertex, which is going to be on the bottom right, because of our coordinates we specified here, the color, and the thickness. Now, let me just put a note about thickness here. Okay, so I just edited this here, so now it's correct and pertains to this one. So let's see what this does, okay? So let's draw this here, and we get a beautiful little triangle right here. Remember, this point is 100, 100, and this is 300, 250. This is the color here. It's a nice purple shade. And because it's negative, it means it's filled. So now let's actually put a value, let's put value 10, and let's see how it looks. Ta-da! We get a rectangle with a relatively thick outline here, and we just created this. So that's pretty cool. Now, how about circles, okay? So in cv2.circle, we input our image canvas here, which we're just creating. I'm calling it a canvas, but basically it's an image. Any image would work. We can load images and draw lines or circles over it. It's just easier to do this over a black image. And you also learn how to create these black canvas images in OpenCV. One thing I neglected to tell you was that the second argument in np.zeros here is the data type. Remember, OpenCV uses basically unsigned integer 8. That's our 8-bit data type. And that's our data type for images by default in OpenCV, okay? So let's create our circle. And remember, this is the center of a circle here. This is going to be roughly more to the bottom right. This is going to be our radius. It's going to probably occupy maybe 1/3 of the canvas. This is the color, and we're going to fill our circle. Yeah, so that's pretty much what we expected. A little more to the bottom right than I anticipated, but that's just because 350 is closer to 512 than it is to 0, 0, obviously. And we get a nice olive green color, so that's pretty cool. And remember, this same thickness argument applies here. If you were to change this to, say, 5, you'd get a nice outline circle without the fill. So let's put it back on the fill. And now, what about polygons? Okay, so polygons are a bit different, okay? But the reason they're different is because you're not actually doing a shape. What you're doing is plotting a line of points. And how this function works, before I get to how we format our points here, we use the cv2.polylines. We have our input image, which we've created similarly in the previous cell blocks. All right, so just added in some lines here to explain how polylines work. So we have the image, we have the points, as I said. True indicates whether the image is a closed image or not. And if closed, that means we're joining the first point to the last point. If this is false, we don't join these 2 points. And if we don't join those 2 points, we can't actually make it like a filled image. Otherwise, it's not theoretically going to work. It has to be a closed image for it to be filled. And this is a color like we've seen before. So let's create this here. And we get this nice boomerang-shaped image here. Now, what if I put this as false? Let's see what happens. See, it doesn't actually join these last 2 points here, which is basically change the shape entirely. So let's put this back, and now let's actually fill this here, experimenting with that. And it actually did not work here. Oh, that's actually a good error I found, because actually there's another function called cv2fillPoly, because actually polygons are by nature always meant to be filled like this. Otherwise, it can cause some logical issues, okay? So as we see, this is how it works here. Now the reshape here, now this is a point I wanted to mention to you guys before. The reshape here is necessary because CVT polys take these points here in a different format. If you actually want to see that format, let's explore it here, okay? So let's take a look at first PTS here, all right? Now let's do a dot shape here, and we can actually see it's a 2-dimensional array right there. Now let's see what happens in this line. I always encourage you to explore examining your arrays like this, and you can see exactly what happens. It seems like we've added a 2 dimension in the middle here. Now the reason for this reshape basically is just to keep the format for several OpenCV functions inputs consistent. It can be confusing to beginners because it logically does not make much sense, to be fair. However, it's just to maintain a lot of cross-functionality between functions in OpenCV, which when you get more heavily into OpenCV, you realize it actually helps a lot. So that's it for polygons. Lastly, we're going to learn how to put text, or basically, put text is the name of the function, but how to basically overlay text onto images. And it's quite simple and quite cool. So what we're doing here, we're using this CV2 function called put text, input our image. We can input the text here, you can put it in the string, or you can put it directly here. When I mean put it as a string, put it as a string variable like this out here. And there we go. And now we can just put that in here, and we can run this, and it's nice hello world right in the middle. So how do we get it in the middle? How do we get the font, and how did we get the color and size? Let's take a look. So quite simply, this is the second argument here. Bottom left is a starting point here. That's this coordinate here. When I mean bottom left, that's this point here. So normally we start here. In some OpenCV shapes, we're starting here now. That's a bit different, just remember that. And let's look at the other inputs here. So we have font. We have these 5 fonts to choose from. I'm not sure if they've added more fonts over the years. These were the fonts in OpenCV 3. Maybe OpenCV 4 has more. I'll have to check the documentation to be sure. Color, which we've seen before. Thickness, and font size right here, left out font size. So that's all important. So now let's change a couple of these things. Let's just change the color, randomly making color here. Let's change this to a larger font. Let's try, instead of complex, let's try simplex. And now let us make the thickness less. And now let's start it maybe a bit higher, let's say 25. Actually, no, let's go a bit lower, 155. There we go. And you can see it's a nicer looking font in my opinion. However, it's out of the screen. It doesn't fit anymore. And that can commonly happen when all of these things basically enlarge the font so that it no longer fits on the canvas. So what do? We can either adjust the font so that it fits on the canvas or enlarge the canvas. It's up to you. So probably easier right now to just enlarge the canvas. Let's make it 1000 by 1000. I'm not even sure that's going to be enough, but let's check. Yeah, it is. So there we go. So that concludes this very important lesson on how to draw different shapes and how to put text on images. So in conclusion, what we've learned how to create a blank image canvas using the grayscale colorscape and a full colorscape as well. We've learned how to draw lines, rectangles, circles, and polygons, and we've learned how to overlay text onto an image. And now we move on to section 2, which is image manipulations and operations in OpenCV. Thank you. A bit more difficult. We're moving on to some more complicated image manipulations and transformations, and we're starting with some simple ones, which are translations and rotations. So let's take a look at what they actually are. So firstly, transformations are geometric distortions enacted upon an image. And what exactly does that mean? Well, they're used to correct distortions or perspective issues arising from the point of view the image was captured. And 2 main examples are affine and non-affine. Now, I'm pretty sure you're confused. However, this diagram should shed a bit more light onto what transformations actually are. Imagine this is our original image, and we're doing some operation on it to move it this way and then move it that way. That is the simplest type of transformation, and that's called a translation, which you will see in the following slides. But for now, let's take a look at what affine transformations actually are. So take a look at these objects here. Let's start with this one right here. Firstly, you can see scaling. Now, intuitively, we know what scaling is. It's making something larger or bigger. So it's an operation that changes the size of an image. And you can see just a square, a larger square here, and a smaller square here. Now, let's take a look at rotations. It's the same square, but now it's tilted in this direction. We went anti-clockwise a bit. And this is the square, remains same shape and size, however, it's now tilted. And translations, which we mentioned before, is the same square here, but now it's shifted. Now, the square remains here, by the way. You just shifted off my canvas of my page here, just to illustrate what happens when you translate or move objects in an image off of the canvas being the image pixels or image dimension in pixels right here. So that's what a translation is. And also we have skewing. Now, skewing is a bit more complicated to understand, and it's also called shearing. However, it's just transforming. So what's happening in skewing, essentially, which it's a bit tricky to explain here, but every point on the image here is being mapped to a predefined other point here. However, that isn't simply what it is. And this becomes the essence of what affine transformations actually are. Take a look at the lines in the skewed squared. These 2 lines are still parallel, just like they were here. And these 2 lines were parallel here. In affine transformations, parallelism is maintained. And you can see in all of these other transformations here, parallel lines will remain parallel. Now, there's a lot more maths you can actually do to apply this and understand this better. However, for your knowledge and your sake right now, these are what affine transformations actually are. Just remember they preserve collinearity and parallelism, okay? Alright, so now let's move on to non-affine transformations, or also called projective transforms and also called homography as well. So in non-affine transformations, what happens is that we don't preserve parallelism, length, and angle. It does, however, preserve collinearity and incidence. Collinearity meaning that the points still lie on a straight line, so we're not actually like bending points along. So imagine this line is still a line here. We're not actually warping this line, essentially. However, you can see, though, that we've lost parallelism in these 2 lines here, this line, and now this line. So that proves that this is a non-affine transformation. So now let's move on to something simpler, okay? So don't get confused with this translation matrix here. I'm going to explain to you what this is exactly, okay? So now translations, like I said before, are simply shifting an image left, right, up, down, okay? Now, how do we shift and how do we do this? Firstly, we need to define a translation matrix here. So what we do, these are the parameters we leave here. We leave these 1s and 0s here, and we have this tx and this ty. So what exactly is this? Well, this tx and ty are how much we move the image, we shift the image in the x-axis direction or the y-axis direction. So you can see, let's just assume this was say 100 pixels and this was 100 pixels. It pushes the image now from here, remember the starting point right here, shifts it to somewhere down here, which is how this image looks like this now. And if you're curious about how the translation matrix actually enforces this image or this shift, imagine we have an x and y coordinate here, all right? If you're familiar with matrix calculations, it's going to be very easy for you. If not, I'm not going to go through the math in detail, but what I'm going to tell you is that you take the coordinates of a point. Let's say we're taking this point here. Well, let's assume this point is 1, 1 instead of 0, 0. when you multiply 1 by this matrix here, and tx and ty are how much we're going to shift the image by, let's say 100, you're going to get the new coordinates as the output, as the result of that multiplication. And that's how we use translation matrix to get the new points here. That's mathematically how it's done. All right, so now let's take a look at rotations. Now rotations have a different matrix here. You have all these cosines and sines here. So what a rotation does now, take a look at the image here. Before I go into the CV OpenCV function, what I'm going to show you here is, imagine we have this image right here, and we want to rotate this image by theta degrees in the anti-clockwise direction. So what we do, we again take all the coordinate points here, multiplied by this matrix here, where theta is the angle we want to rotate it by, and this is a resultant image. And using the CV2 get rotation matrix 2D function, you have the inputs here. And now pay attention to what the inputs are. Rotation center X and rotation center Y, the angle of rotation and the scale. So let's ignore scale for now. We're assuming a 1-to-1 ratio with scale here. Now the rotation center is point we're rotating about. You can rotate about any point. You can rotate about this point, and the image is going to swing all the way over here around this point. Imagine this point being a pivot, and any pixel here can be a pivot. Now typically we assume the center of the image is always the pivot. However, that's not entirely true. If you've used apps or Photoshop, you can always drag the center around and rotate around that point. It's quite cool. And basically this is how the function fit is done. So the CV2 function here just takes these inputs here and does rotation for you, okay? By doing the mathematics here, by just multiplying every pixel by this point to get a resultant output pixel. So now let's actually do this and perform these operations in OpenCV. Okay, so let's begin with our practical portion of that section, which is the translation and rotations we're actually going to perform using OpenCV in Python. So let's open this file here. That's file number 4, transformations here. All right, now there we go. So the first thing we're going to introduce to you is the warp affine CV2 function, okay? So what that function does, that function is quite simple in that it takes our matrices here. All right, it's one single matrix, and creates it here in code. I'm skipping some bits here because I'm going into the core of the code right here. So you've seen these bits before, I'm sure. And now what we do here, we take the CV2 warp affine function. We have the image, we put the input translation matrix here, and basically we do width and the height. Now the width and the height is something that you don't actually need to think much about because it's the end shape. It's basically like a scaling factor here. So we're just going to put the image back in the same width and same height as we had before, okay? So just to go through this here, we scale the width and the height of the image by using the shape function, which is a numpy function, which you've seen before. And what we do here, we're just going to shift it by quarter of the height and width. So we just simply divide height and width by 4 to get quarter height and quarter width, and then we shift it. We put tx and ty to be quarter height and quarter width, which is how we have this translation matrix here. And there we go. That's pretty much it. So let's take a look at it. So this is exactly what we expected. We shifted the image in this direction here, just imagine an arrow pointing that way, by quarter of the height, which is this width dimension here, quarter of the width, which is this dimension here. So that's simply all we did. So if you want to take a look at what t is, I already have the output printed, but we can do it again. This is what quarter height and quarter width was, okay? So that's our translation matrix here. So now let's move on to rotation. So remember in rotations, the CV2 get rotation to matrix 2D, we have the rotation center, x and y coordinates, the angle of rotation, and the scale of the final image. All right, so now let's actually do this. So we are going to get the center of the image, first of all, which is a pivot point we're rotating about. It's just simply the width divided by 2 and the height divided by 2. 90 degrees, which means we're going to flip it anti-clockwise, exactly 90 degrees. And we're going to reduce the scale to 0.5. So let's take a look at how that is done. And just so you know, there's an extra step here, because what this does here, this CV2, that rotation matrix here, is exactly that. It gets the rotation matrix. And then we input this rotation matrix into warp affine right here. Just like we did before with our translation matrix T, we have our rotation matrix here. And we just do this and rotates around the center here at 0.5 scale. So you can actually see the entire image here without it being clipped. Because let's take a look at what happens if we didn't do this scaling here. So let's put it at 1. See, the ends are clipped. So let's keep it at 0.5. Now, using the rotation matrix with warp affine allows for a lot of powerful rotations where we can actually control the angle of rotation, the final size, everything. However, what if we wanted to do a simple rotation and not have all that black space around the image? And the black space I'm referring to is this, because this happens because of the scaling we've used and how we've rotated the image around the existing canvas. So what if we just wanted our simple rotated image without all this black borders here? So let's take a look at how we do that. And we can do that by simply taking advantage of the CV2 transpose function. Now, if you're familiar with matrices, the transpose function basically flips the matrix over its diagonal. So imagine we have a matrix where, let me see if I can actually describe this properly. Let's put like 1, 2, 3, 4, 5, 6. And if we were to transpose this, what happens? We end up with, let's just do it here. It's equal sign, it equates to, and we have 1, 3, 5, like that. And we have final one between 2, 4, 6, all right? That is effectively what transposing this matrix does, okay? So what we do, by taking advantage of the transpose function here, we're going to actually flip this counterclockwise like this. And as we're transforming pixels directly, we don't end up with any black space around it. It actually just rotates the image around a 90-degree angle, okay? So that's fine. Now, what about using flip? Now, what does flip do? Let's try something here. This is our image here. Now, did you remember the original image? Probably should have kept the original image up, so let's actually do that. Let's do some good practical work here. So let's take the original image here, and let's call this original. So now you can actually see what the flip did. And actually, you can put it like that, and you can see it's like a mirror image here, where just everything that was on this side now is on the right. So that's what flip does. And we can actually do a different argument in flip. We can have -1, and it flips around the vertical axis here, okay? If you want to picture it better, we can just align it like this. Might not fit if totally. Bring this down a bit, and there we go. So you can actually see the mirror image flip vertical flip there. So -1 gives a vertical flip, and +1 gives a horizontal flip like this. Which you should have left it like this initially, but there we go, okay? And this is actually original here, so this should actually be on the left, and this should be on the right, so you can actually see the line that it basically flips from, the center line here, okay? There we go, so that concludes this lesson right now. So what have we learned in this lesson? Well, we've learned how to perform translations and rotations in OpenCV using CV2 warp affine and CV2 gut rotation matrix, and that's to get the rotation matrix, which we then feed into warp affine to get the final transformed image. And then we also learned how to use CV2 transpose to do quick counterclockwise rotations where we eliminate the black border, and how to use CV2 flip to actually flip images around the horizontal or vertical axis. So now that concludes this video. And now let's move on to scaling, resizing, interpolations, and cropping, okay? So stay tuned for the next video. Thank you. Hi, and welcome to the video on scaling, resizing, interpolations, and cropping. So it's a lot of little things we'll be doing in this chapter, and they're all quite simple, but you need to know this stuff because they're very important in computer vision. So let's take a look at resizing or scaling and what exactly is the difference. Well, they both seek to enlarge or reduce the size of an image. That's self-explanatory. But the difference is that resizing seeks to change either the height or width or both of them, and they don't tend to be at the same scale. So imagine we can resize the square by doubling the width, but keeping the height consistent or constant, and we end up this rectangle. However, in scaling, we seek to keep the height to width ratio the same. So scaling keeps the image dimensions, or the image ratios, I should say, together or constant. So you end up with a square. So no matter what you do, you can scale by, say, let's say we're scaling by percent. You can scale 1000%, 500%, or even 5%, and you still have the same height to width ratio, which is giving us our square, okay? So now let's take a look at interpolations and how do they relate to resizing or scaling? Well, firstly, interpolation is a method of constructing new data points within the range of discrete or known set of data points. So what exactly does that mean? Okay, so let's imagine we're a car, and this car is traveling along the savanna here, it's Queen's Park Savanna. This is in Trinidad and Tobago, and red are our existing points, and yellow are our interpolated points. And what does that mean? It means that let's say our GPS is logging our coordinates every 30 seconds. So we have a red point here, a red point here, and a red point here, and a red point here. Good. So interpolated points means that we're going to start to automatically generate points between these points so that we can infer the space between. So that's how interpolation does. It looks at this and this point and gets an average here. Same as these 2 points, gets the average point here. But look what happens here. We're rounding a corner here. This is our actual point. However, the interpolated point is going to put us somewhere in this diagonal triangle here, which is wrong. But it's not actually wrong, it's just how it calculates it. So how does this relate to images? Well, imagine you're resizing an image now. And when resizing, you want to try to infer points between the other points. So it's kind of hard to illustrate this by talking. So what I'm going to do, I'm going to move on to this slide here. So imagine this is our original image here, and we're blowing it up. We want to try to get the enlarged image to be as crisp and clear as possible. Now, this is a bad example of what bad interpolation does. You can see here, it looks very blocky, very jagged, not high quality. Now, in good interpolation, all these points here that make this look so jaggy and blocky are inferred at a much better rate. Now, using standard algorithms, it's almost impossible to get a high quality enlarged image. So all those things you see in CSI and all those TV shows where they take a very, very blurry, blocky image and enlarge it to get super high quality, well, it's not quite possible. However, there are some deep learning methods that are quite good, but it's almost impossible to get a highly accurate detailed image out of a blurred image. All right, but the best we can do is by using advanced either deep learning or some advanced interpolation algorithms. So now let's go back to the slide, and OpenCV has few interpolation algorithms here that are quite useful, quite good. None are fantastic, but they work quite well. And what they do, they use different methods here to average the points between pixels. So when we enlarge it and we have to add pixels between our pixels, because that's what's happening here, we try to get the closest inferred pixel as possible. So instead of having a point here, we're going to accurately assess the point here. So now I hope you conceptually understand what interpolations actually are and how they relate to computer vision and how we infer points when we enlarge images. Because always remember, if this image has say 100 pixels here and we're blowing this up to 200 pixels, we're adding 100 new pixels to our image. Pixels that are going to be in between these values here, and we want to infer the color and light and luminosity, all those things as accurately as possible so that we don't end up with something like this, which is a bit low quality and blocky. So now let's move on to something a bit simpler, which is image pyramid. So pyramiding images refers to either scaling up, which is enlarging, or downscaling, which is shrinking images. And OpenCV provides a quick little function to do very, very quick resizing or scaling of images using the pyramid function. You'll see it in our code in a practical slide. However, now let's move on to something a bit more important and useful, which is cropping images. Now, cropping images refers to extracting segments of that image. So pretty sure we all do cropping of images using our mobile phone apps or all those photo editors. What if you took this nice, cool picture here? However, there's some goofy person photobombing the image on this end here. We just want to crop him out, and cropping him out means you're actually keeping a section of the image here, drawing a section that you want to keep. And we can do that with code in OpenCV, which you will see shortly. So now what have we learned in the video? We've learned the difference between resizing and scaling, interpolations, image pyramiding, and cropping. So now let's move on to practical part of this exercise, where we'll take a look at scaling, resizing, and playing with some interpolations, as well as cropping images, all in OpenCV. Thank you. Hi, and welcome to the practical exercise of scaling, resizing, interpolations, and cropping. So let's take a look at our code. Alright, so now let's start doing the practical exercise of our last chapter, which is code number 5, scaling, resizing, interpolations, and cropping. So click on this IPython notebook, and let's bring up our code. Okay, so firstly, I have some notes here which describes how to use the resizing function, what the desize argument is, which we will see shortly, all right, and a list of interpolation methods here. But before we take a look at this, let's just actually run the code here. So I'm going to read a bit through the code and before I run it. So now, firstly, we're loading our test image here, which is a picture of Oxford that I took last year being 2019. And what we're going to do, we're going to use the resize function here. So the resize function takes a few arguments here. We take our image, we put none here. Now I'm going to describe to you what none is here. None is the desize argument here, which is the output image size. Now, by putting none or 0, what it does, it actually uses the dimensions of what we scale here as. Otherwise, you can actually scale an image and then put some dimensions here that you want it to be, which keeps it fixed. However, I don't use this terribly often. Just kind of use the scaling to actually get the image size that I want. So now you're seeing fx and fy as our third and fourth arguments, and you're seeing I'm using 0.75 here. What this is saying is that I'm going to scale the x-axis here, x-axis actually being this one, horizontal axis, by 0.75% of the original size, which is 3/4 of the original size, same thing, and the y-axis, which is the vertical axis or the height, I'm scaling to 75% of the original. And we don't specify an interpolation here as a fifth argument here, and that's because by default we're going to use interlinear. That's the default resize argument or interpolation method. However, in a few other examples here, we're going to specify different interpolation methods here: intercubic, internearest, and interarea. Now, if you remember correctly, intercubic is a lot slower than internearest, which is one of the fastest one. Interlinear is also quite fast as well. Interarea is pretty much in between, it's also quite fast, but they're not terribly different when you actually look at the outputs. However, I do see a big difference sometimes with using intercubic. So now let's run this code and take a look at our different scaling methods. So let's try this. So this is our 0.75 or 75% of our original image. We scaled it down or downscale it here using linear interpolation as a default interpolation method. Now let's upscale this image to twice, which is why fx and fy are 2. And using cubic interpolation, and you can see it's actually pretty good. It doesn't look noticeably upscaled, although I mean I can't tell it is, but it's not too bad. Now let's take a look at internearest, and internearest looks good. However, to me it seems a bit harsh and a bit jagged in some areas, whereas intercubic does look a bit smoother. You can look at them side by side. Hopefully the image quality of your video is good enough for you to detect the difference. However, as you can tell, look at this building here. You can see it's a bit jagged, especially coming down here, where intercubic is a lot smoother and more natural looking. So that's a positive of intercubic. And now we can actually do skewing, which is when we specify our fy to be different to our fx, which we'll see in the code. This is actually what I wanted to teach you. We can change fx and fy to different values and get different types of scaling or resizing. However, you also can input dimensions here. Now these dimensions here, the outputs using the desize argument now, and you're ignoring these arguments here, which is why they're not in the arguments of this function here. By default, they're 1 to 1, and now we can just actually output the specific dimensions we want. So if you want to resize images to a specific size, you can actually use this here as a desize. And this is actually pretty cool. You can just basically change the ratios. So now this is actually resizing and not scaling, okay? So this is actually phrased wrongly. But that is okay. If you absorb this lesson, you would know where the terminology is used incorrectly. And I apologize for that. So now this is some experimental code I'll delete. And now let's take a look at image pyramiding now. So this is quite simple. Have our image here, our original image. PYR, which is pyramid down, makes the image smaller by half. So it's using fx as 0.5 and fy as 0.5. And py up is basically using fx and fy as 2. So we take the image, we make it smaller, and we create smaller here. Now we're feeding smaller back into our pi up, pyramid up, and we're creating a larger image. However, you'll see the quality isn't going to be good because what's happening here is that we've taken the original image here, we've scaled it down, so we already have lost some information in the image by scaling it down, and we're taking this lower information image and blowing it up back to the original size, because this is a half and then double again. So that's why we end up with this very blurry image here. So you can see it side by side how much worse quality it is. So that's what image pyramids have done. Now, they're not really useful for resizing. They're more useful in object detection when you want to just get quickly resize images for different operations. So it's good that you've learned that. Now let's take a look at cropping. Now, cropping can appear a bit tricky, however, it's quite simple. So what we're doing here, let me step through the code. So we're just getting our input dimensions, image dimensions here, which is a height and width by using the shape arguments here. And what we're going to do, this is just getting the coordinates of our cropped region. So what we're doing, imagine or remember, actually I have a diagram that I can illustrate this here. All right, so it's easier to explain when I describe in the code in this diagram here. So let's put this side by side with the code so you can actually see what's happening. All right, so the area we want to crop, imagine this white canvas here is the entire region. So let me just make it, it's a bit hard to get the exact high as I want to do, but this is still readable, I'm guessing. So imagine we want to get this region here cropped out of the original image. So imagine this whole white canvas here is our image, and we want to crop the middle rectangular square of this image here. So what we're doing, we're going to move 0.25 down here, which is why I have 0.25 times the width and 0.25 times the height. That is our start row and start column here. Those are these points here. So just like drawing a rectangle, we have to get the top left vertice and then the bottom right vertice here, which is going to be 0.75 times the height and 0.7 times the width, which we get here. So end row, end column. So that's relatively straightforward. Don't think about it as being complicated. It's a bit much to look at, but it's not complicated. All right. So quite simply, when you want to crop an image, you use this indexing here. So this is a function of NumPy lists, or just Python lists, I should say. So you actually just get the start here, start row to the end row. You just want these columns here, or these, I should say, array list elements here, and these elements here. These are the elements we want to extract from our original list here. So that's actually it, all right? Now, what I'm going to do in the other code here, I'm just going to actually draw the area using the CV2 rectangle. And CV2 rectangle, by the way, is an in-place operation, which means that it actually draws a rectangle over the original image, which we don't want to do. So just use image.copy to create a copy of the image, and that copy will be the one that the rectangle function draws over. So hope I don't confuse you, but now let's just run this code starting from the top. So This is our original image, nice and clean. This is the area we want to crop. This is the area that, remember this is 0, 0. So this is 0.25 down, 0.25 here, and then this is 0.75 down and 0.75 here. That's how we get the end and start columns and rows, so the end vertices. And this is our cropped area. So you can see this is exactly what we cropped out of it. You can actually put it back here just to click on overlay it. Because it's a window, it's a bit tricky, and because of the rectangle width, it doesn't actually line up perfectly, but you can see it is exactly the region we wanted. So cropping is extremely important and extremely useful in computer vision. So it's a useful thing to know, and keep in mind that this code is actually quite simple. This is all the cropping function is. It's not a function, it's actually just the way we do it. So all of this code is just to illustrate this one line here. So that's it for this video. So now just to summarize what we've learned in this video. We've learned the two different methods to resize images in OpenCV. Just to reiterate, that is the fx/fy, or using the desize method to specify the actual dimensions of the output resized image. You've learned how to specify or change different interpolation methods. You've also used the pyramiding functions, which is CV2 pyramid up and pyramid down, as well as you've learned a very important tool, which is how to crop images. So now let's move on to arithmetic and bitwise operations. Thank you. Alright, so now let's start where we take a look at arithmetic and bitwise operations. So now let's go straight to the code, since this chapter doesn't really have any theory that we're teaching using our PowerPoint slides. So we're on code number 6, arithmetic and bitwise operations. So just click this file and bring up our IPython notebook, and here we go. So now the arithmetic operations I'm going to teach you basically pertain to this function right here, CV2 add. Now, what is important about this function is that, remember when we were adding brightness values, I should say, to RGB image? Remember we were maxing out different colors? So what we're going to do, I'm going to illustrate the difference between using the CV2 add to add brightness to an image, as opposed to using regular matrix addition here, which is supported in Python, to add brightness to an image. So firstly, let's create a matrix of 100. So what we're going to do, we're going to add 100 to all the values here. These 100s, remember we're adding this to all our values in the image. So we're going to use a grayscale image here. That's what the 0 is about. We use the 0 when we're using mread to load an image as a grayscale. So remember, if we're adding 100 to every value in our grayscale image, you're going to make the image much brighter. So let's take a look at it. So before we look at the second one here, hide it. This is exactly what you expected. You expect a very bright image like this. That's what we have done by adding 100 to every value here. And a lot of it looks white because it's reached 255 and it's maxed out. Now, what happens when we actually don't use our CV2 add function? It looks like this. Now, what is this? Why is it looking so different? So let's put them side by side and I'll tell you why. So when you use CV2 add values here, remember, let's suppose a value was say 200 and you're adding 100 to it. You're going to get 300. However, 300 is out of the scale of that 0 to 255 value we're looking for in our RGB image. So what happens if you get a 300? Now, what we want to do when you get a 300, you're basically telling it it's a super bright value and it just exceeded 255. So CV2 add caps the value at 255. That's why it's all white. However, when you add it regularly and you get a value of say 300, what OpenCV is going to treat it as, it's basically going to treat it as in going over the 255 and starting back at 0. So you're going to get 50. So it goes over the 255, so technically 45 actually. So 300 really represents 45 here when you use regular addition. So CV2.add caps it at 255, which is why this one looks so bad and this one doesn't. Simple as that. And all of this code is just to illustrate that very simple function here. And similarly, there's subtracted with CV2.subtract. You take a look at it here, and it works perfectly as well. All right, now what would have happened? Let's, instead of doing added here, let's do a subtracted version here. So let's minus it now, and let's call this added tree to avoid any confusion. And let's take a look at that. So look how bad this looks. Instead of having a dark image, what you want, you're getting some sort of weird dark and white image here, which is not at all what we want. So that illustrates here our arithmetic operations here. So now let's take a look at bitwise operations and masking. So firstly, before we do this, let's create some images here so we can actually demonstrate bitwise operations and or so and not. So we're going to create two images here. One is a square and one is an ellipse here, using our CV2 functions here. So I'm not going to go too much into this code. You should be familiar with it from before. Although ellipse may be new to you guys, so we can just take a look at ellipse here. And it's a good exercise for you guys to look at the official OpenCV documentation to see how the ellipse function actually works. So now, forget about how we made these images. Now let's actually use these images here. So bitwise operations are functions that, how do I describe this? The best way to describe it is they look at how images interact. So binary images, we're going to input into this, and how they overlap. So if you want to get the regions that they intersect or don't intersect, or they both intersect or they both don't intersect and everything else, you can actually use these operations to get those regions. So instead of talking about it, it actually is better to always play with these functions and use them so you can take a look at what they do. So AND operation. Now, if you've done any logic in mathematics or computer science before, you know an AND operation basically takes where both of them are true. So remember, operations takes the square and ellipse and highlights white only where they intersect here. So this is only where our square and our ellipse intersected. So you can see it better here. You can actually see or is where they both exist and so an overlap as well as everything else. So that's why you can actually see the AND, which is just basically being this region here before. That's what this one is. So now let's look at XOR. So what is XOR? So XOR is everywhere where they both exist. It's not included, but they exist here and they exist here. So it's the opposite of an AND technically. And now NOT. NOT is not related to the others here because there's only one input into NOT, and it's everywhere that is not here. So it's a bitwise operation, and it's quite useful bitwise operation when you want to invert things. So I actually have used this function a lot when I was inverting different data sets for my machine learning algorithms, training data. So you can use this quite often if you just want to flip all the ones to zeros and zeros to ones. So those are the bitwise operations here. So demonstrated that. So we can summarize what we learned in this video, the practical video. You've learned how to use CV2.add and subtract and how they differ from just adding values to your images to improve or decrease brightness, or I should increase or decrease brightness. And you've learned to use some bitwise operations and so you've demonstrated how they work with the ellipse and our square, and how to use not functions to do a bitwise inversion of the image. So now let's move on to the other chapter, which is blurring and sharpening of images. Thank you. Hi, and welcome to the video, blurring and sharpening of images. So let's take a look at how we actually do this. So firstly, what is a convolution and how does it relate to blurring? Well, firstly, a convolution is a mathematical operation performed in two functions, producing a third function, okay? Which typically is a modified version of one of the original functions. So now that probably still doesn't help you understand what's going on. And neither does this formula here, which is just a mathematical illustration, a very simplified one of what's happening there. And in computer vision, we use these kernels to specify the size of which we are manipulating the function over our image, okay? And this is what a 5x5 kernel looks like. And I'm pretty sure this doesn't help you understand what is happening. However, what you need to keep in mind is that a convolution is an operation whereby we run a matrix over our images here. So it's like a square matrix of a specified size, and this one's a 5x5 here. And it's performing some operation on these pixels here using the inputs of this region here on the image, okay? So imagine this is the image here. This 5x5 region is the image we're considering. This function here is some function that's a 5x5 matrix here. We're multiplying it here, and we're getting an output of it. So now this probably should help you a little bit more. This is our kernel here in our elephant image here. And this is what a kernel looks like here. It's just imagine it's a simple one. It's just all ones here, and it's multiplied by 1/25 here, which is because it's a 5x5 matrix here. And we're multiplying it here so that we normalize, keep it something to 1. Otherwise, we don't want to increase the intensity of this operation because this operation is a blurring operation here. So by doing this, running this convolution over all the pixels of the image, like imagine we're sliding this across the image, we're effectively blurring the image here. And that's how we end up with this blurred image. Now, why do we blur images? Now, blurring images is something a lot of people seem to be confused. Why does this operation even exist sometimes? Well, I can tell you, blurring actually helps a lot of computer vision algorithms work a lot better because it actually smoothens the image, so it reduces noise or the detail or the sharp edges, which can be interpreted as noise in some algorithms like canny edge. Canny edges work a lot better sometimes on slight blur to the image as opposed to a detailed sharp image like this, because what happens is that when canny edges does this, it's going to identify sometimes way too much edges in the image. And even though you can adjust parameters of the canny edge algorithm to reduce the sensitivity, you may sometimes want to blur the image slightly, maybe not so much like in this output here, but just to a small degree so that it actually helps a lot with the canny edge algorithm. So there are other types of blurring. That was a very simple blurring here that averaged values over a specified window. However, there's Gaussian blur, which is similar but uses a Gaussian window, so there's more emphasis on weighting the points around the center. Remember, we have a 5x5. Let's take a look. 5x5 kernel here. With a Gaussian one, the points that are close to here are more emphasized, so or more important as opposed to the points here. Remember, normal or Gaussian distribution is a bell curve, so the points at the lower or the extremities are less weighted or less important in the blurring. Okay, so there's ultra-median blur, okay, and it's bilateral blur. I'm not going to read all these here, but we're going to actually use them in OpenCV in our practical chapter, so you can take a look at how they work there. So now let's take a look at sharpening. Now, sharpening is the opposite of blurring. It strengthens or emphasizes the edges in an image, and this is an example of a sharpening kernel right here. So our matrix still sums to 1. You can add it, check it here. So there's no need to normalize. That is multiplied by a factor to retain the brightness, like what we did right here. Okay, by the way, this was a blurring kernel right here. So this multiplying by 1 is sort of like an averaging across of all the pixels here. So that's how we actually blur it. So now let's move on back to this. So this is what regular image looks like, and this is what a sharpened images looks like. And you can see it's basically when people say an image is over sharpened, it looks a bit artificial, like all of these points a little too emphasized, a little too, I can say jagged sometimes if you want to describe it like that, just a little harsh and a little bit hard. So that's what a sharpened image looks like. So sometimes it does add the deal. So what have we learned in this video? Well, we've learned how images are blurred using convolutions, some other types of blurring algorithms, and how sharpening or what sharpening is and how it's done. So now let's actually move on to practical aspect of blurring and sharpening images in OpenCV. Hi, and welcome to the practical chapter on blurring and sharpening images in OpenCV. So now let's move on to our IPython notebook and let's start doing some blurring and sharpening. Okay, so now let's start the exercise on blurring and sharpening images. So let's open notebook number 7, title here, and let's bring up our IPython notebook with our convolutions and blurring code, okay? And our sharpening code as well, all right? So firstly, what we're going to do is we're going to load an image in that we're going to operate on, and we're going to create a tree-by-tree kernel using NP1s to create this basically this kernel here. And it's divided by 9, so we actually keep it consistent 1/9 our values, all right? So that way we don't brighten the image unnecessarily. So what we do, we use our CV2.filter2D, that operation to convolve our image with our kernel, okay? And we use a -1 here because a -1 specifies that we're keeping the same depth as our input image source. So basically this stands for destination depth, which is ddepth for short, which you'll see in OpenCV documentation. And just use -1 by default if you want to keep it, okay? So now we're going to run this operation on with our tree-by-tree kernel. Then we're going to run the same operation with our 7x7 kernel, and you're going to observe the difference here with the different degrees of blurring and how different size kernels affect blurring. So let's check it out. So this is our input image here. It's nice and sharp, as you can see. This is it with our tree-by-tree blurring. So you can see it's definitely more blurred. It's a lot like smudgier, I would say, on the details here in this building. And now let's take a look at our 7x7 kernel. Wow. So this is significantly more blurred. It looks like someone with who needs glasses a lot harder, how I imagine they would see. I do need glasses, but basically I might see like this as opposed to this. So you can just see how larger kernels end up blurring the images a lot more. And that makes sense because what's happening with the larger kernel is that you're averaging the values across range, right, like dimension, I should say, width or height, same thing. And that's why it's a lot more blurred. So now, these are some other commonly used methods of blurring, Gaussian, median, and bilateral blurring, which we're going to test out here. So let's take a look at each one. But let's start with this first. Let's start with the CV2 blur. And this is where we specify our input kernel here, tree by tree. And let's take a look and see how this looks. We're going to do the same here with Gaussian blur using a 7x7. And we're going to do a median blur here. So actually, for consistency's sake, let's just do tree for everything. And now let's take a look at how that looks. So we have our averaging here. So average, I should call it exactly. All right, just a regular blur, I should say. And we have our Gaussian blur here. Now, Gaussian blur, you can actually tell it's a bit better. It's blurred, but it's not significantly blurred. It actually looks a lot smoother. Then there's median blurring here, which I actually don't like. Just looks a bit almost like a painting, so it's actually not too bad. And this is our bilateral blurring here, which doesn't look like it blurred much at all. But if you look at the floor, actually, you can definitely see it did something here. It looks a bit artificial. It looks like it's just smoothing out the pixels over regions here. The regions that actually are kind of like one color. It looks a lot smoother here compared to the original. Actually, this isn't the original, but it's closest to the original. And we can see the sky looks roughly the same in this one, just a bit more blurred around the clouds. So that's a pretty cool observation. So now that you've observed those filters, you can see that bilateral is very effective in noise removal and keeping edges sharp. That's why areas that didn't have much details were very smooth, and areas that had detail like the building were actually very sharp. Okay, so I actually have a small little write-up in details about the bilateral filter if you want to experiment and use it more. However, now let's take a look at something else. This wasn't included in the chapter before, but it's something I've added in because it's quite cool. It's called image denoising, and other means of reducing noise in images. Pretty much this comes from computational photography because a lot of noise filters do what I would say is unintelligent blurring, which, except for bilateral perhaps, which reduces detail to an extent that actually isn't nice to look at. So let's take a look at what these different noise reduction algorithms can do. So it takes a little while. So this here is our noise reduced image. And you can see it's a bit artificial, I would say, but it's quite aesthetic, quite pleasing to the eye. And you can experiment with these as a homework lesson, just to see how it looks. One is specifically works with grayscale, different types of images, grayscale again, so you can check it out and see. And what I'll do, I'll put some notes here at the bottom of this Python notebook to indicate what these parameters do, okay? So these are the input arguments of the fast10 means denoising colored function. So if you want, as an experiment for a homework lesson, you can toy with this function and see if you can come up with some nice parameter values that can produce nice looking images. Pretty sure it's going to be dependent upon the image, so you kind of want to experiment. These tools are not super intelligent to figure out exactly what you want, so you can actually mess with it and see if it helps some of your noisy or low quality images. So now let's take a look at sharpening, which we've seen in the presentation previously. Now let's remember this sharpening kernel we made. So now let's actually use it on our input image and take a look and see how it looks. Ta-da! Alright, so it's not that good, but it's exactly what we wanted. Sharpened images basically stress a lot on our lines, and this input image is perfect to illustrate that because there's a lot of lines, intricate lines in this building, and on the floor here, or the road, I should say. So you can actually see how much it emphasizes on these lines, which isn't really a good look unless you were going for this type of artistic style, which could look cool, however, it definitely looks over-sharpened. So now that's it for sharpening, and that's it for this video. Alright, so just summarize what we've learned in that last video. We've learned how to use different blurring algorithms in OpenCV and how the different convolutional kernel sizes affect blurring. You've learned how sharpening is done in OpenCV and how to use the fast10 means denoising colored function in OpenCV. Thank you. Up next, we take a look at thresholding, binarization, and adaptive thresholding. Thank you. Hi, and welcome to the video on thresholding, binarization, and adaptive thresholding. So let's get started with what exactly is binarization. Well, binarization is quite simple. It's actually the act of changing the intensity values in an image to 0 or 1, minimum or maximum value it can take. So how exactly does this work? Take a look at this image here. It only works conceptually on grayscale images. Otherwise, you have to consider the RGB values individually, which you don't want to think about right now. So just think about a simple grayscale image and look at the difference between the image on the left and the image on the right. You can see there's just two colors here. It's just black or white, where in this picture, there's a lot of different shades of gray, 256 to be fair. So what happens here? Well, what we're doing here is that every value that is below 127 in our grayscale image is sent to 0, okay? And every value that is above 127 is sent to 255 or the maximum 1. I'm only using 0 or 1 conceptually to illustrate what binarization is, like binary, 2 values or 0, 1. So you can see, imagine this here, this on the left, this image right here is grayscale image, and these are the values here. So what happens? Everything that's over 127 is sent to 1. Everything below 127 is sent to 0. As you can see with these in red here, these are the 0 values. And these in green are the maximum values, which are going to be 1 or 255 here. So that's conceptually how binarization works. It's actually very simple. So what about thresholding? Well, thresholding is the act of converting an image to binary form. So binarization and thresholding kind of refer to the same thing, but thresholding is a bit more of like an overarching term that sort of describes different ways we can do binarization, which we will find out shortly. So let's take a look at this. This is the OpenCV function for thresholding, okay? We have the image, we have the threshold value, which is 127 here. We have the max value, that's the value it's going to be sent to. The clamp value, so 255 will be the max value, and the threshold type. And threshold type is what we're leading up to, because there are different types of thresholds thresholding algorithms in OpenCV. So threshold binary is the most common basic one that we've seen in the previous slide. It's just clamping everything below it to 0 and everything above this to 255. Then there's also this, which is basically the inverse of it. So imagine instead of clamping everything below 127 to 0, everything below 127 goes to 255. So it's basically like a flipping of the image, if you can conceptualize that. Then there's trash trunk, which we'll take a look in our code later on, trash to 0 and trash to 0 inverse, okay? And note, the image needs to be converted to grayscale before thresholding, okay? So let's take a look at adaptive thresholding. So the biggest downfall of simple thresholding methods is that we need to provide a thresholding value. And adaptive thresholding basically takes away that uncertainty, because imagine you're thresholding and you don't know what the actual thresholding value you want is. Otherwise, you can get images that are less than ideal. You'll probably get it either too white or too black. So if you want to just make it in between, you may want to tinker with that value. But tinkering with that value puts you in the process loop, and you don't want to do that. So adaptive thresholding is a way to take away that uncertainty. So this is the adaptive thresholding function, which we'll play with in our code later on. All right, and note the block sizes in this here need to be odd numbers, but you'll take a look in the code and see what that's like. So there are three main types of adaptive thresholding algorithms in OpenCV. There's adaptive thresh mean C, which takes the mean of the neighborhood of pixels when it's interpreting what threshold value to use. There's a Gaussian one, and then there's OTSU, which is my favorite thresholding algorithm. It's a very clever algorithm because what it does, plots a histogram of the intensities here, and it looks at the two peaks and sort of chooses a value in between here. So you kind of get a very good balance of what the threshold value should be. So what have we learned in this very short video? Well, we've learned what binarization is, we've learned what thresholding is and how it's implemented, and we've learned about adaptive thresholding methods. So now let's move on to the practical code where we implement thresholding binarization algorithms and look at some adaptive thresholding algorithms. Thank you. Okay, so let's get started with our practical implementation of thresholding, binarization, and adaptive thresholding. So let's open our thresholding notebook here, which is number 8. Bring this up. And let's take a look at our sample code for thresholding. So firstly, what we do, we grayscale an image here. All right, so this is our test image here. This is to demonstrate the different types of thresholding I mentioned before, which is trash binary inverse, trash trunk, trash to 0, and trash to 0 inverse. So before we start this, okay, what I want to do is just read through each of these comments here that describe what each of them are going to do. So in this one, this is a basic one you've seen in the slides before. Values below 127 goes to 0, and that's black, and everything above goes to 255, which is white. Now, trash binary inverse is basically the opposite of that. Anything below 127 goes up to the brightest, and anything that's above 127 goes to the darkest, which is black. And what about this one? Values above 127 are truncated or held at 127, and the 255 argument here is unused, by the way, just to note. By the way, what this does is a way just to cap maximum brightness values. So you'll take a look and you'll see for yourself. And trash to 0, this one, values below 127 goes to 0, and above 127 are unchanged. So it's not exactly a true binarization of the image, but it's a form of thresholding that you'll see. And this should be reverse thing I typed. All right. Of the above, below 127 isn't changed, and above 127 goes to 0. So basically just the inverse of this here. So now let's take a look at this and you can actually see for yourself what's happening. So let's start with the original image here and the trash to binary. So as you can see, this is a gradient image here. Starts at the darkest here, 0, and goes all the way to 255. So you can see the full range of grays here. And a lot of it is basically some white and some black at the bottom here. So you can see this is 127 value here. Everything below 127 goes to black or 0. Everything above 127 goes to white. So let's take a look at the second one, which is the reverse. And that is exactly what you expected here, okay? And I just had to check something to make sure. The reason why it's actually not exactly the flip of this is because we have a different threshold value here. Previously, this is probably my mistake in my code, but it's a good teaching tutorial here, is that in this one here, we use the threshold value as 200, not 127. So this is not a linear gradient here, okay? It's a lot bit larger in the white side or brighter side. So this is the 200 value right here, and this is the 127. So 127 is actually kind of far up here. And I thought this made sense since this grayscale image doesn't seem to be a uniform transition. It shows a bit more of the lighter regions than the darker regions. Anyway, so that's fine. So this is this of this, all right? Now let's look at trash trunk, okay? Now remember, trash trunk is an odd one. Let's just minimize this so it doesn't distract us. Trash trunk, let's read it again, was right here. Values above 127 are truncated and held at 127. So what does that mean? It means that imagine you're seeing 0 to 127 here, and 127 values, everything above it is just kept at 127. So it's pretty much, I don't know if this shows up in your video, but it's pretty much an illusion that there's a bright line right here. There's just constant 127 here, and below that goes to 127 to 0. Hope you understood that. And let's look at the fourth one, which is trash to 0, okay? And it's kind of similar to what we described just now. Everything below 127 here goes black to 0. Everything above remains unchanged. And lastly, the reverse of that is this one. So you can actually see that it's reversed. Everything above 127, it just goes clamped to 0. And everything between 0 and 127 remains unchanged. So those are the 5 different thresholding methods here you can use, binary thresholding methods you can use in OpenCV. But is there a better way of doing this? Okay, remember I said you have to manually enter your thresholding value, which is this first argument here. By the way, this argument here is the max value of the threshold. So you can put this whatever you want. I'd like to use the full binary values, white or black, so you can actually see it's done here. Oh, also, just so you know, whenever you load an image using ImRead and you have a comma and 0, it means you're loading it as a grayscale image. It's just a little shorthand technique. I may have mentioned it before in previous tutorials, but just so you know, in case you started or skipped ahead or forgot, that's why we have 0 here. So this automatically loads our image as a grayscale image. So, as I said before, adaptive thresholding takes away the necessity of using a threshold value here. So you can actually just set the algorithm and it does its own thing. It automatically chooses the threshold value for you. So let's start here. So in this one, I'm loading up a book, Origin of Species. That's by Charles Darwin, and it's a black and white image, grayscale image we're loading it as. And we take a look at the image, and we use traditional thresholding at first at 127 and a max at 255, just to see how it compares to the others. And then what we're going to do, we're going to actually blur the image a bit, just because it removes noise. It's not cheating, it's just a way to just help the adaptive methods work a little better. And we're going to use each of the 3 black thresholding methods to see how well they work, okay? These are some default values for this adaptive thresholding method. You can leave those untouched. What I'll do, I'll put a note at the bottom here of what they mean, in case you guys want to know. But in the meantime, let's test this out and see. So this is our first image here, the original image. This is our regular binary threshold with 127. It's done fairly well, but as you can see, if you wanted just to isolate the text, there's actually a lot of missing text here. So let's see if the adaptive methods work any better. And indeed, adaptive mean thresholding actually works a lot better, I would say. Now let's take a look at this one, clusters. One of my favorites, actually does work pretty well too. The text is pretty much there. However, it's not ideal, but it's still better. And this is Gaussian Otsu, I hope I'm pronouncing it right, thresholding here. And you can see with the blur, it actually does kind of like make it a bit fuzzy. And it's Gaussian method, so that's why it has a blur as well, okay? So that's it for this video on thresholding and adaptive thresholding and binarization. Let's go back and take a summary of what we've learned. So you've just learned how to do binarization and thresholding in OpenCV and how to take advantage of the adaptive thresholding methods. So now let's stay tuned to the next video, just on dilation, erosion, and edge detection. Thank you. Hi, and welcome to the video, section 2 on dilation, erosion, and edge detection. So let's get started. Firstly, what exactly is dilation and erosion? Well, they're very important tools in computer vision, actually only when dealing with binarized images. And here's an example of it. So imagine we have the number 5 right here, or an S, whatever you think it is. I believe I drew a 5. So anyway, let's look at the definition here. Dilation adds pixels to the boundaries of an object in an image. And let's take a look at erosion. Erosion removes pixels at the boundaries of an object in an image. So let's take a look at this. What is the image here? So imagine 0 basically represents black, which it does. And the 1s represent white, which is 255, if you want to interpret it that way. So this is the foreground and this is the background. So this here is the image. So if we use, let's look at dilation first. If we do some dilation on this thing here, what do we expect? Well, you're going to expect that we add pixels to the edges of this image, or the foreground of our image, which means we end up with a much thicker looking S, okay? So it's like going from normal font to bold. Now, what about erosion? So erosion, as you know what erode means, it means that we remove pixels from the boundaries of objects in an image. So exactly as we expected here. So all these ones on the boundaries here are going to disappear and be converted to zeros, which means that we are thinning our object right here. So that's how we get our eroded S or 5 here. So let's take a look at 2 more operations. These are opening and closing. So I left examples of dilation and erosion here on a real world example. This is actually the algorithm working in OpenCV on the word OpenCV that I wrote here. So you can see dilation adds or thickens basically the font or the letters I drew on the image. And erosion makes it much thinner, almost making some of them disappear entirely, like the E is barely there. We can still tell it's an E. And now let's take a look at opening. Opening is erosion followed by dilation. So it's this erosion here. So look at this image here. And then we dilate it here. So that's how we end up with this. So it's sometimes a good example if you want to like thin and then kind of like re-thicken an image. So if you want to like make it clearer, it sometimes helps. And similarly with closing, closing is dilation, which is we are thickening the image here, followed by some erosion. So closing is actually a useful operation, sometimes especially when you're doing OCR or cleaning up fonts or text and images. Sometimes closing works pretty well because you don't want to dilate it too much because dilating kind of thickens it too much and you end up with like the ends merging into each other here. So you probably want to just dilate and then erode. So this is a good example, practical example of how to use dilation and erosion and opening and closing. So now there is some confusion with erosion and dilation, and I've seen this question pop up so many times on Stack Overflow and other websites and other forums. People basically confuse dilation and erosion, and it's not their fault. It's because I think in the original OpenCV documentation tutorial, they actually kind of used a bad example where they kind of mixed up erosion and dilation in their example images. So remember, dilation adds pixels to the boundaries of an object, okay? So, but when you run dilation or erosion on an image like this, it's going to do the opposite. And the reason for that is because if the background is white and foreground is black, it's going to be doing the opposite. So it's going to treat the white as the object in question. So when we're eroding here, we aren't eroding the black OpenCV text here. We're eroding this, the background, I should say. So it's going to actually thicken this here. Okay, so it's kind of confusing, and I may have just mixed it up, but what I meant to say is that it's actually thickening the O here because it's actually working on the opposite. So it thinks this here is like the background here, so it adds pixels to this here as erosion, okay, because it's adding it to the wrong object if we think it is, okay? So there is some confusion. Always remember that erosion and dilation are meant to work on images that are like this, okay? You can just simply invert it. It's not a complicated thing. It's just, if you get something unexpected, it's probably because you're doing it on reverse background, white background, and black foreground type thing, okay? Or vice versa. So now let's move on to edge detection and image gradients. So edge detection is a very important concept in computer vision, especially when dealing with contours, and edges can define as sudden discontinuities or changes in light or luminosity in an image, okay? So, and they can encode just as much information as pixels because edges kind of outline the object or the shape of an image. And this is how edges are pretty much found. So imagine if this is a line here, this is an actual edge. So if you take the intensity across a blue line, this is what it's going to look like. And if you take the derivatives, this is what it's going to look like here, the maximum points across this dip here. So that is how we can detect edges coming in and out, these drastic changes here and here of lines in an image. So that's basic concept of how edge detection works. So we're going to look at a few edge detection algorithms now. These are Sobel, Laplacian, and Canny, okay? So Sobel and Laplacian aren't really used commonly, they're just used to sort of highlight and illustrate concepts. Sobel emphasizes vertical and horizontal edges. Laplacian gets all the oriented edges, but it's not too great. They're both okay. Canny, though, is the ultimate one. it works brilliantly. And how it works is that it applies Gaussian blurring, finds the intensity gradient of the image, then applies non-maximum suppression, that is, it removes the pixels that are not to the edges, okay, so it kind of looks cleaner, just like this, and then it applies some hysteresis thresholds so that we can actually just clean it up. You can actually look at the code and see, configure these upper and lower thresholds. So this basically determine sensitivity of detecting edges, okay? And this is an example of an image of a dog where we ran canny edges, and it looks pretty good, okay? So just to summarize what we've learned what erosion, dilation, opening, and closing are in computer vision. We've learned how edge detection works and why it's useful, and we've looked at a few types of edge detection, including canny edge detection. So now let's actually look at a practical aspect of these where we implement these concepts in OpenCV. Thank you. Hi, and welcome to the dilation, erosion, and edge detection practical aspect where we implement these in OpenCV. Okay, so let's start our actual practical exercise here on dilation, erosion, and edge detection. So open this file, type number 9, and here we go. So it's a rather simple exercise we're doing here. So what we're doing, we're loading the OpenCV text that I showed you guys before, and we're displaying it, and then we're defining kernel here, 5x5 kernel, and I'll show you how it's used afterward. We'll change it so you can actually see the difference. So left this out, dilate here. And now what we do, we can actually specify a number of iterations, which is how many times you erode the image. Similarly in dilation here. So what we're doing, we're using cv2.erode, cv2.dilate. For the opening, we use cv2.morphology here, and you can specify the algorithm being used. This is the default one, and the one that does open, the one that does close, and you can use the same kernel we defined above. So let's take a look at these, how these will affect the image. So this is our original image here. It's nice and clean. This is our eroded image. It does exactly what we expected. This is our dilated image, also does what we expected. Let's just space this out. And now let's do the opening. Remember, opening is erosion followed by dilation, which is why it looks like this, and we erode it, we dilate here. And then let's do closing, which is dilation followed by erosion. So basically this eroded, so it's quite good. So it's oddly similar to the original image. Okay, so that's a good experiment, that's fine. Let's now change the kernel size to 3 by 3, and let's take a look, see how that affects things. So you can immediately see there's less erosion, less dilation. Opening and closing pretty much similar. Remember before, that opening looked a bit messy, now it's actually a bit better. So now let's make this even bigger, so you can see more pronounced changes. Let's change it to 9 by 9. Wow, eroded it, it disappeared effectively. Now this one got a lot thicker, like a fat marker type font used. Now remember, apparently there's some pixels, yeah, there's a couple pixels here. That this is basically, opening is erosion followed by dilation here. So these little tiny pixels here that you're seeing, barely see it, so hopefully your video quality is good enough. We're eroded into these little blocks here. And now, as I expected, it's going to be quite good because it's already thick. As if we dilate something, even if we dilate it a lot, it's going to be fine. So now let's go back to our 5x5, and let's change one thing. Let's do 3 iterations of each. What do you expect? Yep, exactly. So you can see, you can toy with these little parameters to basically experiment with your own erosion and dilations and different kernel sizes and different number of iterations. So now let's move on to edge detection and image gradients. So what we're going to do first here, we're going to use cv2.sobel to get the x edges and the y edges here. And basically how this function works here, you basically specify 0, 1 here if you're doing the x edges, 1, 0 here if you're doing the y edges. And case size determines the kernel size used here. So don't think about these parameters too much. Just, as I said, Sobel isn't used a lot anymore, but it's kind of fun to use anyway. And what we're doing here, we do a bitwise OR on the Sobel x and Sobel y extracted edges. So we can just do Sobel all right? And you can take a look at that. And then after, we're doing a Laplacian edge detection algorithm on the same image here. And lastly, what we're going to do at the end, we're going to run canny edges on the image here, okay? And what I will do, I'll explain to you after what the threshold values of canny edge detection, so we can actually toy with them in this tutorial and see if we can get some better results. So let's run through this edge detection code and look at some of the edge detection algorithms and compare them. So this is our original image here. Now let's look at the Sobel X. Remember, it looks at the horizontal edges and it's not too great here. Maybe we can refine that afterward. This is Sobel Y, again, not too great. This is both of them, kind of poor. This is Laplacian, again, it's a bit messy, very messy, I should say. And now let's look at the canny edge detection, which is like wonderful. It's actually perfect, okay? So you can see how much better canny edge performs compared to the other algorithms. Now let's take a look at the experiment here with the canny edge code. So let's load our image here. We don't need that, we don't even need to import it, but might as well. Okay, so let us do a few different versions of the canny code, okay? So let's set this to let's do some wide thresholds. So what wide thresholds are going to do, so we're going to experiment with a few different canny values here. So this is going to be canny, let's go wide range here, 10 to 200. This is going to be canny, let's say like a narrow range here. And this is probably going to be similar to what our original image, actually it is similar, it's the exact same thing. So let's probably make it a little bit tighter. Let's make it 70 to, let's say 110, okay? It's not going to be much different, okay? How I will describe something to you guys is that the thresholds here specify lower and upper boundaries of gradient values. So it's a little bit hard to interpret unless you read the paper or look at the mathematics behind it. But you can get a feel of what it is and what it's doing by experimenting with different values, which is something I always encourage. So let's take a look and see how a canny performs. So this is the initial default values we have, which usually work pretty well. This is our canny wide, which should be capturing more edges, and it doesn't seem like it is. Actually, it's less edges. Do you know why that would probably happen? It's odd, but it's probably because of the definition of the gradient that it's using for the edge detection. So let's take a look at this one. Narrow actually captured definitely a narrower, less edges here. So it's actually a bit better, I would say. And where is the third one? Oh, it's basically replaced. I forgot to rename the window. All this, just remember, by the way, it's a good thing if you've seen this. If you don't rename the window to something new, imshow is going to basically overwrite the window with the same name, which is the first window here. So let's run that again so we can actually see, let's just call this candy tree. So let's see it again. There we go. So it actually is a bit different to the original here. So you can see how changing these thresholds create different edges or get different edges from the image. All right, so that's it for this video. Let's go to the learning summary for this chapter. So what we've learned here is how to perform dilation, erosion, opening and closing in OpenCV. And then we took a look at edge detection and how we use image gradients. And then we took a look at Sobel and Laplacian, and then looked at canny edge detection, which performed a lot better than the others. So I hope you enjoyed this video. And now you can stay tuned for section 3, where we take a look at image segmentation and object detection in OpenCV. Thank you. Hi, and welcome to section 3, where we take a look at image segmentation and object detection in OpenCV, where we take a look at segmentation and contours. So what exactly is segmentation? Well, segmentation is a process by which we partition or segment sections of an image into specific regions. And here we have some examples of this. All right, so beginning with this number, this handwritten digits here, you can see the numbers that are written are extracted automatically by some sort of magical algorithm that we'll discuss shortly. Likewise, for the car, you can see everything that looks like basically a panel or whatever is extracted here using some sort of method. Similar for the domino here, each area that's shaded black is extracted, and by extracted I mean highlighted by the green region here, and that is what we call segmentation. Now let's take a look at contours. Now what exactly are contours? Now if you're familiar with geography, you're probably thinking like mounting or altitude contours. Well, it's sort of similar in a way. However, in computer vision, or at least in OpenCV, we define contours as continuous lines or curves that bound or cover the full boundary of an object in an image. So imagine we have this piece of paper here that was scanned, okay? Now imagine we wanted to extract this sheet of paper from the background. Now, you've probably seen some things like this before. However, we're going to do this in OpenCV shortly in the next video. But firstly, let me explain to you what's happening here. This region here, called as the object, is extracted fully by some sort of algorithm here that we'll discuss very shortly. And this is called a contour. This green region, this green perimeter or boundary here is called a contour. And they're very important in things like object detection, shape analysis, and a host of other applications that you may or may not need to do in computer vision. So let's discuss the find contours algorithm in OpenCV. So this is an algorithm that seeks to find or locate regions of contrasting intensity, background and foreground type separation, so we can actually highlight the area around it. So generally, the contour to be found should be on a white or black background so that it contrasts with the image or object we want to extract. And better accuracy, we can use binary or grayscale images. So before finding contours is applied, you can apply thresholding or canny edge detection, which you'll see shortly. However, these are not strict guidelines. They're more rules of thumb. So you can actually do some experimentation on your own to see what gives you the best performance. It all depends on your read or your image domain that you're looking at. So let's take a look at how contours are represented in OpenCV. So when we use the find contours algorithm, what's going to happen is that we're going to extract several contours from an image. So this is a picture of me here in Norway, and this region here around my shirt, polo, long sleeve polo, is contour. So what's happening here is that this is the first contour in the image that it's found. And how we're going to represent it is that there are points here. So each point here is contour region here, or I shouldn't say region, it's a point along the contour perimeter here. So we have 1, 2, 3, 4, 5, 6 points here represented from this contour. And OpenCV find contours returns an array of arrays, or a list of lists. So imagine this is a list here. We have 5 contours in here, and each contour is actually an array. So an array is stored as a first value in this list, and that array has, or that list has, a bunch of XY coordinates like this that you will see shortly. So this is just one way to illustrate it. I think it's clearer here than in here. So we'll take a look at this in OpenCV shortly. So now, before we move into the code, let's take a quick look at how the CV2 find contours function actually works. So we have 3 main input arguments into this function. It's the image we're working on, the retrieval mode, and the approximation method. So firstly, before we go into what these arguments are, these 2 in particular, we need to look at what find contours actually return. So remember I said it returns a list of contours? Well, that's the first argument here. So contours, and then it returns something called hierarchy. And hierarchy describes the child-parent relationships between contours, which we'll discuss in the next slide. That means it's contours within contours if you want to get an idea of what's happening. So now quickly discuss approximation methods before we go into the retrieval mode, which discuss hierarchy, which involves hierarchy, I should say. So the approximation methods, they're basically 2. Now, if you use CV2 chain approx none, that stores all the points along the line. So you get, instead of the points of the vertices or the endpoints, you just get all the points, which can be quite a bit if your image is large. So it's a pretty inefficient way of doing this. So I advise you use simple chain approx simple, which gives you the same information. Now let's take a look at the hierarchy, which is discussed in the retrieval methods here. So these are the 4 main retrieval methods we're going to use when we use find contours. So This is short for return, so retrieve list retrieves all contours here. Now, retrieve external sends only the external or the outermost contours. So imagine we have a list of contours here. Retrieve list will give you all of these here, whereas retrieve external will give you 0, 1, and 2 alone. Now, retrieve comp retrieves all the second level hierarchy. Second level hierarchy will mean it'll give 2 and now tree. And retrieve tree retrieves all of these in full hierarchy. Okay, so what is hierarchy exactly? Now, hierarchy is stored in the following format here. Next, previous, first child, parent. Now, this is a description of how hierarchies are stored from first to last. So now, as I said, 0, 1, 2 are the first level hierarchies here. 2a is a child of 2. That's the innermost contour here. So now that means that, and it's a second level hierarchy. So that means that tree, anything contour tree and below, is a child of 2. And similarly, 4 and 5 are children of tree A. Okay, so that's basically the hierarchy here. So now let's take a look at how we draw contours now in OpenCV. So it's fine to just return contours and get all the coordinates, but if you really want to see what contours your contour algorithm picked up, you're going to want to use cv2.drawContours. So again, that requires the input image, the contours that we returned from the findContours function, the specific contour, which specific contour here relates to which contour you wish to draw. So you can actually have it like contour 0, contour 1. If you want to draw all, just use -1 in your argument here. And then you can also do like how we do all the other drawing or creating shapes, color, and thickness. So now just to summarize what we've learned image segmentation, what are contours, how the find contours algorithm or function works in OpenCV, and similarly, the draw contours algorithm. So now we've discussed enough contours. Now let's actually do some practical exercises with find contours in the next video. Thank you. Hi, and welcome to the practical section of segmentation and contours. So now let's move on to our IPython notebook. So our contours lesson is number 10, segmentation and contours. So just open this IPython notebook and let's get started. So before I run through the code, what I'm going to discuss here is the pre-processing pipeline that we do before processing the image in contours. So like I said before, previously in the slides, we need to grayscale our image and then run find canny edges, typically not as a strict definition, more of as a rule of thumb or guideline, so that enables the find contours algorithm to work more effectively. Now, this works more effectively when it is more complicated, colorful, or cluttered images. However, in my simple test image here, where it's just 3 black squares, it's not actually necessary to run these, okay? But we'll run it either way, and I'll show you the image as it goes through each step of the pipeline. And then after that, we take the edged output here, which is from canny edge, and we run this through find contours right here. And let's take a look at our arguments. So do you remember that these are the two main configuration arguments we have besides the image here? So retrieve external means we're getting all the external contours, not the internal ones, just the big outer ones. And chain approximate none gives us all the points, I should say, along the contour line. Remember, chain approximate simple just gives us the vertices. So I advise typically you use chain approximate simple. However, in this example, I'm just using chain approximate none. So now let's run our code and check it out. So here we have our first CV2 image here, just our input image. Now the next step we're going to take a look at is our edged image, our canny edge. So these are our canny edges here of the image. Good. So in case you're wondering how it changed to black and white like this, canny edges does that. That's the effect of canny edges on our image. So it sort of inverts it and highlights the edges in white. Next, this is our canny edges after contouring. This is only important to show because the find contours function actually edits our input image, and you can see those changes here. Anyhow, this is the final output after using find contours and draw contours together. It allows us to draw all contours, hence the -1 and the thickness of 2. So now you can see them visually. We remember the outer external contours here. So that effectively is our contour lesson, okay? So you can take a look, you can play around with these different things. You can experiment with grayscaling and canny edging. You can try different arguments here. You can actually plot different levels of contours. In the next section, we're going to take a look at more different things we can do with contours. Before we continue, I just want to discuss that we have the arguments here explained for each one. Actually, this one needs to be a bit better labeled, so let's do it shortly. In case you want to see how to make a list in Markdown, this is how you do it. And draw contours here, and some notes that in OpenCV tree, the find contours function outputs 3 values instead of 2, okay? So actually what you can do, there's a line here that doesn't show up in the Markdown for some reason. However, this is just a placeholder here for the third argument, which is a true and false boolean, whether find contours run successfully. However, it's been removed in OpenCV 4, so you no longer need to add a third argument. In find contours here. So this is actually how find contours used to work in OpenCV 2 anyway. So they went back to the initial design or method they used in OpenCV 2. So just to summarize what we've learned, well, you have learned now how to use the find contours algorithm in OpenCV, how to draw contours in OpenCV, and how to pre-process images for contouring in OpenCV. Next, we take a look at sorting and approximating contours. So stay tuned for the next video. Thank you. Hi, and welcome to the video where we take a look at sorting and approximating contours. So now let's start this video with sorting contours. And sorting contours is a very important pre-processing or image processing step when you're looking at contours and images, because firstly, sorting by contours, you can eliminate small noisy contours by sorting by area. You can remove all contours that are under a certain area. That's one way you can sort these contours. Also, you can sort contours by looking at the spatial position. So imagine you're trying to pre-process these numbers in order. You want to get them left to right, so you can actually keep the meaning of the digits being in this order. So those are some examples of how and why we sort contours. So now let's take a look at contour moments. Okay, so these are methods we can utilize to sort contours. So firstly, what are moments? Now, moments are a set of scalars that are basically the aggregate of a set of vectors. Now, if you have done some mechanics, or even statistics, you would know what they are, what they mean. Basically, you can think of it as measure of an image intensities, and that's given by this. And you can use those image intensities here to capture basically the image moments and thus get the centroid of the contours here, where Cx and Cy are the y and x and y coordinates of the centroid. And these are what the centroids look like in contours here. And just so you know, by actually using or finding the centroids, you can actually sort contours now by their spatial position. You can sort them up basically from top to down or left to right, as I showed you in the previous example. Also, there is a CV2 method to find the area of contours, which we'll take a look at in the next video. Those are the ways we can actually use or utilize to sort contours. So now let's take a look at a different method. Let's take a look at approximating contours. Now, what is approximating contours? Imagine you have a contour that's kind of like a noisy image. Suppose you're trying to get a shape, like say a triangle. And because the image is taken at an angle, or it's a hand-drawn triangle, when you return the contours, it's not going to return an exact triangle. It's probably going to return like maybe a 5 or even 4, 6, 7-sided object that resembles a triangle. It's very, very close to a triangle indeed. However, it's not exactly a triangle. So what we use a method called approximate poly DP. And that approximate contour method allows us to straighten those jagged edges in contours so you get a more exact or simple polygon image. And we can adjust things like accuracy and sensitivity and approximation methods. So just to conclude this video, we've learned how to sort contours, and you've learned why it's important too as well. We've learned what image moments are, how we can use them to find the centroid of a contour, which helps with our contouring, especially when sorting by like left to right or up or down. And lastly, we've learned about the approximate contour method as approx poly DP and why it's useful. Let's move on to the next video, where it's our practical exercise of sorting and approximating contours. Thank you. Hi, and welcome to our practical exercise on sorting and approximating contours. So now let's move into our IPython notebook, where we take a look at the exercise. So let's start with opening up the file, which is 11, sorting and approximating contours. So open this file here, and here we go. So let's look at sorting contours. Now, before we actually sort contours, let's do a regular contour detection on the images I'm using for this exercise. So let's load this image. So it's a bunch of shapes here. So it's square, triangle, smaller square, and circle. Now, let's run our canny edges. You can see the output or the result of that output. You can draw the contours over our images exactly as we expected and wanted. And now we can just highlight the contours over our existing image. So pretty cool. We've done that before, but just another way of doing it. And I'm also printing out how many contours we've found right here. Okay, just using len on contours. Len stands for length. It's a Python function. So now let's sort our contours by area. And to do that, we've built a little function here called getContourAreas. And what that does, it runs through all the contours here, takes the contours as an argument, creates an empty array. And what we do is for the contour in contours here, we basically just use the CV2 contour area function, and it gives us the area of that contour in pixels. Okay, so it's pixel squared. It's not an actual dimension, like a physical dimension like inches or centimeters, but it's a dimension we can use digitally to represent our contour areas. And then we store all areas back into this array here. We're going to do a similar thing where we load our pre-processing pipeline. Actually, we don't. We just get the image, and then we just get the contours here, because we got it previously before, so we don't actually run our pre-processing line and our find contours here. We're just using the contours that the contour variable that we created up here. So just take a note of that in case you're wondering, where's our find contours functions, okay? It's just to shorten the code. So this is the key thing I want to show you here. This called sorted here, this function takes contours as our argument here. The key is our contour area function that it runs, and we sort it in reverse order here. Now, this is actually what's sorting our contours here using contour area. This function here that gets the contour areas is just for illustrative purposes, so we can actually print the contour areas as we run through. And then we can actually iterate over those contours right here and draw them one by one, which is pretty cool and pretty nifty to see. So let's get started so you can better understand this code. So exactly as we wanted, we're drawing the contours one by one, and we're printing the contours here. The contour areas before sorting is in a random order, okay? So you can see it actually looks like smallest to biggest coincidentally here. However, we want it sorted from largest to smallest. And that's actually what we're running through here. We're running through the contours here that are largest to smallest order. So when I click enter or any key next on this image, it should highlight the circle here because the circle is the second biggest in area of the images. And that's exactly what it does. Now, visually it looks like the triangle has a bigger area, but let's just double check to make sure. Yes, it does. Then it's a square. So you can see we've effectively sorted our contours on areas. And by doing that now, and by printing the areas here, if you wanted to say eliminate contours of a smaller dimension here, what you can do is basically run through all of the contour areas here and eliminate or delete the ones you don't want, the ones that are below a certain threshold. So, okay, so now let's sort the contours left to right. And to do that, what we're doing, we're using two functions here. One is gives us the x coordinate here because the x-axis determines the left to right placement of an object in the image. And we use, actually exactly as I said here, we're taking contours only of a large threshold here. Well, this isn't necessary for this test image here. However, it's good for, I think I took this function from another function I made previously that had this noisier contours. Always good to have this stuff anyway, just in case the image is a bit noisy. So contours of a certain area, we get image moments here, and then we return this. Now, if you remember from our slide, these moments here, M10 and M00, gives us, indexed in this moments object, basically gives us the x coordinate of the centroid. That's exactly what's described here. And now we'll label contours here. What this does is just draws a circle around the center of contour image of the object. Basically, I'm being a bit ridiculous with my terms. What this actually draws here is the center of the object that the contour identified. So let me just be clearer with what I'm saying. And again, we just load our image here. We obtain the mass or the centroids of our contours here using this for loop and this function. Remember, this returns the drawings. Basically, this returns the circles. It just runs through all the contours and draws circles over the center of each of them. And then what we do here, we just start sorting it left to right. So we hold this open here. And what we do, every time you click this now, basically runs through our sorted contours here and uses our xcode function to sort in reverse order here. So by reverse order, we're sorting left to right, I believe. I'll just double check that. Yes, it is left to right in my comments. All right. And now, just so you know, we leave this open here. This is just a click to show the image here, but we leave it open, this window, because we're using the same name here. And as we go through, as we step through, every time we step through, it means we're doing CV2 wait key. Every time we click, it runs this loop one more time, and it's going to draw highlight of the contour over the object in the image, left to right. So I'm hoping I didn't confuse you there. These other things here, just putting the text over the image, so you'll see it shortly. Now, it's a bit cumbersome to describe all of this code by talking about it, so it's best we just run it now. So let's take a look. As expected, we have the centroids of the contours here, so that's pretty cool. Now let's sort it left to right. So now get the first contour, second contour, third, fourth. That's all we've done, all that little relatively complicated code, but it's kind of straightforward to understand if you want to go through it on your own. Gives us that. So now let's take a look at something maybe slightly easier to understand, which is the approximate poly-DP algorithm. So I'm not going to explain all of this code again because it's a bit easy now. You guys should be familiar with this as well. Just so you know, we're iterating through each contour here. We find contours again. We threshold and binarize image because it helps the contours here. Instead of using canny edges, we can just do that. And it's a grayscale image as well. So we're converting to grayscale, I should say, then doing this. So let's run this through. So this is a crude house I've drawn. Now, what if you wanted to extract a house basically in a proper dimensional way, okay? So you don't have this jagged edge here and a slanted door here. Well, you may have a slanted door still. It's pretty badly drawn. But let's take a look. This is what the contour is extracted. This is exactly what you would expect, okay, from a good contour algorithm. However, by using approximate contour, we now get this triangular roof here being a straight line, the base of the house being a straight line here. And you can actually see, well, the door isn't that, it's straighter, but it's still angled, obviously. So that's basically use case of the approximate poly. Now, here's something else I didn't discuss previously, but it's the convex hull. Now, convex hull is similar to the approximate poly-DP. And what it does, basically, it looks for curvature, convexity defects, and corrects it. So convex curves which are bulged out, or at least flat. And if it's a bulge on the inside, it deems it as a convexity defect, and it fixes it. So let's take a look at this image of a hand, and what we're doing here, we're going to run the convex hull across it. And instead of having the convex be inner defects here, like these inward curves, it actually straightens those lines, so you actually get full outward enclosure of the object at hand being upon here. Anyway, so that's convex hull here. I hope you understand this code. You can go through it on your own time. I know it's a little bit complicated, but it's a very good lesson to use in Contour. Thank you. So now just to summarize what we've learned in this video. We've learned how to sort contours in OpenCV. We're sorting left to right and by area. We've learned what image moments are. We can now find the centroid of a contour using OpenCV. And we've learned how to approximate contours using CV2.approximate poly-DP. And as well, we've learned how to use a convex hull, which I didn't mention here, but it should be noted we are using CV2 convex hull function. So now let's stay tuned for line, circle, and blob detection. Thank you. Line, circle, and blob detection. Okay, so what exactly is line detection? Well, there are two main algorithms for line detection, and those are Hoff-lines and probabilistic Hoff-lines. And Hoff-lines, basically, this is the function here in OpenCV. So we take the input as a binarized image, and then we have this row accuracy and theta accuracy and a threshold. So the threshold here is a minimum vote that it needs to be considered for a line. So consider this a sensitivity marker, all right? And we'll take a look at the other values when we start using the algorithm in OpenCV. Now let's take a look at probabilistic Hoff-lines. So probabilistic Hoff-lines is a bit different, where it's a bit more complex in that it takes like a random vote samples from the image of the line so that it can actually determine whether it's a line. So it's a little bit more accurate, and you can actually just toy with these two in OpenCV to see which you prefer. All right. So the idea is actually exactly as I said, to take a random set of points sufficient enough for line detection and also returns the start and endpoints of the line, unlike the previous function which just returns the line itself. So now let's take a look at circle detection. So don't worry, by the way, if you're confused a bit by those Hoflines parameters and stuff, what we'll do, computer vision is always, even though you need to understand maths and the theory, which helps immensely, it's also a very practical, kind of like an art, toying with different methods and parameters and stuff, so you can actually see what works best. So circle detection. So this is an example of circle detection here, where it highlights circles of these bottle caps. So we use another Hof algorithm called Hof circles. And this is the Hof circles algorithm, cv2.hofcircles. We have the image and a bunch of different input arguments here. So the method here, where we only have Hof gradient available. dp stands for inverse ratio of the accumulator resolution, minimum distance between the centers of detected circles. These are always like good parameters depending on the image domain you're looking at. When I say image domain, depending on the type of image or type of circles you want to detect, you can have a lot of like false positives, or you want to increase sensitivity to get them, okay? Now, parameter 1 is the gradient value used in the edge detection. Parameter 2 is the accumulator threshold for the Hof gradient method. And lower allows for more circles to be detected, which is false positives. Here we describe the minimum radius, which is basically the minimum radius of the size of the circle we want to pass as a circle. And max radius similar as well, okay? So what about blob detection? So blobs can be described as groups of connected pixels that all share a similar common property. And what I mean by that is that they can all share the same size, same pattern, same shape, same color attributes. And to do this, we use OpenCV's simple blob detector. So now this is the input stage to the processing pipeline of the blob detection. It creates a detector. All right, you'll see this in our code shortly. Then we have the input image and feed the input image into the detector. It obtains the key points, and then we draw the key points over the blobs that it detected. And this is an example of how the blob detection works on these daisy flowers here. Pretty cool, isn't it? So what have we learned in this video? We've learned basically types of line detections, which is on Hof probabilistic lines. We've learned about circle detection using Hof circle, and we've looked at blob detection as well. So now let's take a look at a practical part of this video, which is using line, circle, and blob detection in OpenCV. Thank you. Part of this video where we take a look at line, circle, and blob detection in OpenCV. So now let's move to our IPython notebook that contains our video. So the file we're looking at for this lesson is number 12, which is titled line, circle, and blob detection. So go ahead and open this IPython notebook file. And here we go. So the first thing we're going to take a look at is Hoflines, the first Hofline algorithm. So this code looks a bit funny. So let me just show you exactly what's happening here. So we're loading an image, we're grayscaling that image, we're running canny edges on that image, and then we're running the Hoflines function here, okay? And in Hoflines, what I'll do in this lesson, I don't have it here, but I'll add in the parameters here, exactly what is considered for everything for Hoflines, okay? So you have an idea what's going on. In the meantime, just take these parameters for granted. We just have some notes on it here if you want to see. Accuracy is down to 1 pixel, and basically the npi is just which take the accuracy, as well as the line, how many points on line we want to set, okay? So those are the parameters we're using here. And what we do, we iterate through each line here and convert it into the format required by CV lines. That's how we draw these lines here. It's actually should be CV2 lines, okay? So let's run this over our image, and wow, look at that. We've got the lines of our Sudoku image right here. It's pretty cool. Let's actually take a look at the initial image here so we can actually see how it looked beforehand. So let's do this and call this original. And yeah, there we go. So let's run this. So we have the original there. You can see there's lines, length of various thickness, and basically there are lines across numbers here. So we'll have to find a way to illuminate that sometimes. And here we go. So we got all the lines in the image, which is pretty cool. All the angles and lines here. It's nice. So now let's use probabilistic Hoflines on that same image. So again, we have a similar preprocessing pipeline. And again, similarly, what we do is that we iterate over the lines here. All right. And then we draw those lines using cv2.lines. So here we go. We can see actually lines are detected, but it's now points and not actual lines we're drawing. So this is a bit different. So you can take a look and experiment with this on your own, changing different parameters to actually get the full lines if you want. Now let's take a look at Hof circles. So you can see all the parameters I explained here. So now let's take a look at how Hof circles work. Now Hof circles is an algorithm that I don't love because it takes a lot of time to run and it requires a lot of tweaking to get right. So you may or may not find it very useful in your applications. So let's run it on the OpenCV logo here, and I've got one circle. Depending on how you adjust the parameters, you may get a different circle or two circles. So as I said, it requires a lot of tweaking Hof circles. Blob detection is a much cooler algorithm in my opinion, and it works a lot better. So let's take a look at this on the sunflowers here. And you can see, yes, so it actually highlights the centers of the sunflowers here, which is pretty cool. Remember, it identifies similar regions in an image and associates them with a common blob, and then draws those blobs over them. And you can see how it works here. Remember I talked about a pipeline? It has simple blob detector where we create the detector, we get the key points from the image here, and then we use those key points here as an input argument here in cv2.draw key points. And what we do, we use that to draw the blobs that we highlighted. All right, so this is the explanation of draw key points, how it works a little bit. So that's it for this video. So I know we ran through that video a bit quick. However, because this is a condensed computer vision course, we're basically teaching you a lot of the high-level concepts and implementations of these different algorithms. And it's up to you to take some initiative and toy with these on these sample images. Now, it's not going to be tedious. It's actually going to be quite fun. And especially if you have a goal or objective of doing something, it's actually very, very good to learn and experiment with different methods to do that. So I hope you enjoy and have fun and learn a lot from doing this. So now just to summarize what we've learned, we've basically learned how to implement half-lines and probabilistic half-lines in OpenCV. We've learned how to use half-circle as well, and we've learned how to use blob detection in OpenCV by creating a detector by making it with simple blob detector _ create. So now let's move on to our next video, where we take a look at object detection with Haar cascade classifiers. So this is going to be pretty cool, so stay tuned for the next video. Thank you. Hi, and welcome to the video where we talk about object detection with Haar cascade classifiers. So what exactly is object detection? Well, object detection is the ability to detect individual objects in an image. So take a look at this image here. This is an image with lots of objects in the actual picture here. Now there's 2 or 3 guys here, there's a dining table, there's multiple bowls, and our object detection algorithm is actually working pretty well. Now, as a human, you can tell that there's probably a few more objects that haven't been identified here, especially individual objects that they're wearing right now, or things in the background, or maybe even cutlery or additional like napkins and stuff on the table. However, computer vision algorithm that does object detection, this is pretty good. And the reason why this is pretty good is because object detection is extremely hard, because objects can vary widely within a class. Think about different breeds of dogs. Think about a Chihuahua or Great Dane or Dalmatian. All those dogs look drastically different from each other. They can actually be considered almost different animals by a computer vision algorithm because they look so different. What about various angles? The angle you see an object. Remember we discussed why computer vision is so hard in the beginning, and we went through a whole host of reasons? Well, many of those reasons are what makes object detection very hard. Things like lighting, clarity, different types of object classes, and things like categories that can confuse humans. Is it a knife, sword, dagger, those sort of things. So you can see generally why object detection is a very challenging arena in computer vision. Now, however, object detection is almost like, at least very good object detection is the holy grail in computer vision. Being able to identify almost any object in a scene will drastically improve a whole host of things such as scene labeling, navigation by robots or self-driving cars, body recognition. Well, that's actually done pretty well in Microsoft Kinect right now. Things like medical imaging, so we can actually look at different types of scans, CT, MRI, X-rays, and diagnose and pinpoint exactly what's wrong with that person. Facial recognition, which is actually being done pretty well now, as well as handwriting recognition, and also recognizing objects in satellite images. So doing things like national security and I guess for drones as well, this can be extremely useful. And there's a whole host of other applications where object detection can be applied. So just remember, object detection is different to image recognition. And why? Well, firstly, image recognition, that's the image on the right here, deals with identifying what the image has. So we don't actually try to pinpoint where the cat is in this image. We just want to know that the image has a cat. That's what image recognition does. And image recognition is quite useful for things like maybe filtering, like pornographic images. You want to filter those yes or no. Is it pornographic or whatever? You can actually do a lot of things like cats versus dogs. Think about it like Google search. They would need to use image recognition quite a bit as opposed to object detection. And object detection basically does a different layer of difficulty where it actually doesn't seek to identify that image has a face, but it seeks to localize, means identify where exactly the face is and draw a bounding box over it, highlighting the region that contains the object. That is what makes object detection harder and special. So now let's take a look at one of the most successful object detection algorithms, one that was developed almost 20 years ago, and that is the Haar cascade classifiers. Now, this is one of the most effective and quick object detection algorithms that was primarily used for facial recognition. It uses something called Haar features and runs it through a series of classifiers or a cascade to identify objects, and they're trained to identify just basically one object in an image, like a face. However, we can run multiple of them in parallel to do things like face and eyes or different types of things like pedestrians and cars together. So now let's quickly describe how our cascade classifiers are built and trained and developed. So essentially we have positive images that contain a face, and negative images that don't contain a face. That's used as our training data set. We use to build the Haar cascade classifiers. So what we do, we then extract single value features by sliding various rectangular blocks over these images here. Basically, these blocks move left to right and then go down, and then they have different options of blocks to use. And how we compute the values, the single value from these blocks, is that we calculate it by subtracting the sum of pixel intensities under the white rectangles from the black rectangles. However, as you can see, this will result, because we're passing the window across the image multiple times and up and down all over the image, it results in a ridiculous number of calculations. For example, a 24 by 24 pixel will result in 180,000 features generated. That's a lot. So researchers devised a method called integral images that computes this with basically 4 reference arrays. So what we've done here, basically, firstly, we should know that these 180,000 features are redundant. Majority of them add no real value. Okay, so you can see these are relevant ones here, but these are irrelevant. Relevant meaning they contain the face. That's what we're looking for. So what we did, or what researchers did, was use the boosting algorithm of choice was AdaBoost, and due to its ease of implementation. And what we did, we just used this to build a bunch of weak classifiers to build a strong classifier. And I wouldn't go into the detail of how AdaBoost works because that'll be in a machine learning course. However, it's just a robust way to take multiple classifiers and get a very strong classifier out of it. And this ended up resulting in a reduction of features from 180,000 to 6,000. However, that's still quite a bit of features. So what researchers then did was, out of those 6,000 features, they used the most informative features to first check whether the region can potentially have a face or not. So it's basically like a first pass, first check. So false positives here are no big deal because you just check those afterward. So doing so eliminated the need for calculating 6,000 features at once. And this concept is how we developed a cascade of classifiers for face detection. So the Viola-Jones method, which is a method that is primarily used in a lot of digital cameras and phones maybe for the last 20 years, basically uses these cascade classifiers here. So firstly, it's stage 1, 1 feature, stage 2, 10, stage 3, 20, 25, 50, and so on. And they all basically go ahead to basically figure out whether this is a face or not. So what have we learned in this video? Well, firstly, you've learned what object detection is and how it differs from object recognition, or image classification, I should say, and basically different use cases and why object detection is so important. And you've also learned how one of the most basic but very important object detection algorithms are cascade classifiers. So now let's move on to face and eye detection. And this will be done using HAR cascade classifiers in Python using OpenCV. Thank you. Hi, and welcome to the video where we take a look at face and eye detection, and we're going to use HAR cascade classifiers to do both. So let's move on into our IPython notebook where we execute this lesson. Okay, so let's start with code number 13, which is face and eye detection with HAR cascade classifiers. So just go ahead and open this notebook, and we can see the code is actually fairly short for each of them. There's different variations of the same thing. So let's step through this code first before we actually run this. So firstly, when using HAR cascade classifiers, you always need to load your HAR cascade classifier. So I have a few classifiers in a folder called HAR cascades in your images folder, which you would have seen, hopefully. And this one I'm going to use is called HAR cascade frontal face default. It's one of the best facial detection HAR cascade classifiers. And they're all stored in .xml formats. And they're fairly big. They're like between 10 and maybe 100 megs, some of them. And the image I'm going to load is one of you've seen in the previous section of slides, where it's a picture of myself. And what we do, we convert it to grayscale. And the reason we convert it to grayscale is that you don't need color. It can work with color, but you don't need a color image to detect the face. Whether the face is in color or black and white, the face itself is still fairly recognizable. And what it helps do, it helps speed up the process of the detection. And so what we next do here is that we use this function here called face classifier .detect multiple scale. That comes from this object here. And that basically runs through our image without some parameters here, which we'll discuss later on. Some of these parameters are fairly good settings for this. And what it does, it stores faces. Now, faces here is a tuple of coordinates, the top left coordinates and the bottom right coordinates of the face, which we can then use later on here using the rectangle function to draw a region over the face so we get this the rectangle or the bounding box over the face. So let's take a look and run this. So now you can see it's a fairly simple process. The only thing I didn't explain was these two lines right here. If there are no faces in that are found in the image, it's just going to print no faces found, so we don't actually need to do this, to be fair. Okay, this is probably going to be skipped because there's nothing in faces here, and let's destroy the window. So let's take a look at this code. Right, so we have my face here. This is the original image, and actually, I kind of like missed a big important part of it there because it actually found my face. So this is my face right here, highlighted in pink in the image. So this is pretty cool. So we can see it worked fairly well. Now let's try it on a different image here, namely this is the input, and let's see what happens. No faces found. So you can see it works as we expected. One thing I made a mistake with, these files are actually a lot smaller than I mentioned. They're like all under 1 meg, actually some are like 100K. I was confusing it with some neural networks I trained previously, which are indeed quite large, definitely over 10 megs, most of them, some of them actually 200 megs. But those are very complicated neural networks, so forget about that. Just remember these files are very small. Now, let's combine face and eye detection. So remember I said you can run multiple HAR cascade classifiers in parallel? That's exactly what we're going to do. And let me show you how it's done with our code. So we'll load our two HAR cascade classifiers here, and these are the objects we created. We grayscale our image again, and then we run the faces algorithm again. Sorry, the face detection, I should say. And we get our faces here. And if no faces are found, we just print no faces again. But what we're going to do now, we're just going to draw the region here as well. And we basically just draw it over a color and crop a color in grayscale image. The reason we crop a grayscale image of it is because we're running the grayscale one in our eye classifier here. It's ROI gray. Okay, so if this isn't clear, what we're doing, we're taking the face that we found from here, faces, and then what we're doing, we're just drawing a rectangle like we did before, but we're using a cropping method to crop the grayscale region out of it here. We run the grayscale version of our face, only our face. It's a tinier, much tinier image now. And then we run it through our eye classifier and get the eyes, and then we draw the eyes again here. So let's take a look at this. All right, that's what we expected. That's the first version. Now it should find my eyes. There we go. So we got the first eye, second eye. Good. I've got two eyes, and I got both of them correctly. Now, what we're about to do is pretty cool. We're going to do some live face and eye detection using your webcam. So what this does here, basically I've created a function here that does this here, and it returns the image where the eyes and face is detected. And then what we're going to do, we're going to open our webcam here, run this function with our frame, our extracted frame from our webcam, and highlight the region where the face and the eyes are here. So let's take a look at this. Mind you, I'm not video ready right now, but you can see it actually gets my eyes and face. And look what happens when I run my hand over. You can see the image flips and all the regions that had my eye and face gone. Now, the reason I flipped the image was just because I wanted to illustrate the image in mirror type effect. So you can just flip an image so it's more real world to you. So your left is your left and that kind of stuff. It's not that important. Just wanted to show you guys it. So you can see now we have done a few different cool classifiers here, face, face and eye, and live face and eye. And you can see how it runs pretty quickly. Now let's discuss tuning of cascade or HAR cascade classifiers. So these are the two regions here that tune the sensitivity of our HAR cascade classifier. So take a look at scale factor. Scale factor specifies how much we reduce the image each time we scale. So remember we talked about image pyramiding? Well, image pyramiding is sort of used here, where we scale the regions of the window that we're looking at, so we can actually detect smaller faces in images here. However, if you use smaller values like this here, remember you're just doing a lot more different versions of that scale, so it's going to take a lot longer to compute. What about minimum neighbors? That's another parameter we can use. Now this specifies the number of neighbors each potential window should have that it can consider the positive detection. So typically we use this as a sensitivity setting, and we set it to between 3 and 6. Now what happens is that low values will sometimes detect multiple faces on a single face. So what this is saying is that if there's one face, you may get 2 windows over that face if that value is low. And if they're high values, it may end up missing a face sometimes though, okay? But high values will ensure less false positives. So if you absolutely need to know if a face is there as opposed to not a face, you can up this value. So that's it for this video right now. So just to summarize what we've learned here, we just learned how to do face and eye detection using hard cascade classifiers in OpenCV, and you've learned to do this using a webcam as well. So now let's move on to car and people detection in the next video. Thank you. And pedestrian or people detection, okay? So stay tuned when we move into the IPython notebook to load our video. All right, so now let's load code number 14, car and people detection. So let's bring this up, and here we go. So now here's a note, if for some reason, if your video playback is what we're doing here, we're loading previously saved MPEG videos, or AVI videos, I should say, that are here, and we're using FFmpeg to load this. So sometimes FFmpeg needs to be installed separately or found in one of these OpenCV folders here and dragged to a different folder. Sometimes it works out of the box, depends on how updated your versions are. So these are just some notes that will help you, just in case these notes were developed for all the versions of OpenCV. You probably just need to just remember, this all depends on the version number. There will be a version 420_64.dll. So you can just look at that, and if you have an error where it doesn't load, you can just use this fix. So it's quite a simple fix. Just take a note and if you need to do it. So now let's look at people or pedestrian detection. So what we're going to do, we're going to load a hard cascade classifier called hard cascade full body. This detects full bodies of people, so people walking, typically like pedestrians, will be easily identified using this classifier. And what we're doing here, we're loading this video file here. So we're using the CV2 video capture function and pointing to the video, the file directory or location of that video file. And what we're doing, resizing the video, making it half its size so we can increase the frame rate that it's processed at. We grayscale that video, and then we load each frame from that video into our body classifier, and then we just draw a rectangular box over it, okay? And then we also have a break here where if you press 13, or basically which corresponds to the enter key, it will exit this loop, so you can stop the video before it's completed. So let's load this video, and you can see, this is pretty cool. So you can see all these people walking here, it identifies them fairly accurately, not all the time, but it is pretty good. So now, let's take a look at car or vehicle detection. So again, we're using exactly the same code, same format. You may have noticed that there's a sleep function here. Sometimes this is necessary when we load videos, sometimes it's not. You don't have to put it in, it just was a fix I noticed when all the versions of OpenCV on some systems, you needed it. However, it's not really needed in most cases with the latest versions. So what we're doing, we're pointing it to the cars.avi file. We're loading a hard cascade underscore car. That's a hard cascade classifier that's trained to detect cars. And again, we're drawing frames over it and grayscaling it and passing it to our detector or car classifier detector. So let's test this out and see how it works. Now you can see it works fairly well, but it misses a lot of the vehicles. There's a lot of cars being missed. So you may want to increase the sensitivity of the parameters in the detector. So that can be a homework lesson for you guys, and you can try it out. Now you can see, generally though, hard cascade classifiers aren't that great, which leaves room for a lot of improvement. And that is how we have a lot of advanced, basically I would say deep learning object detectors, things like YOLO or SSD or RCNNs or faster RCNNs are all quite good and quite better at these tasks than hard cascade classifiers. Hard cascade classifiers had a place when it was used for facial detection, and it worked quite well. However, in these more advanced cases, I would say we will need deep learning methods like the ones I just listed, which we will see later on in this course, okay? So just to summarize what we've learned in this video, this was a simple video. We just used another 2 hard cascade classifiers to do car and people detection. So you've got exposed to a lot of hard cascade classifiers, which are good, but as you can see in our last lesson, they leave a lot of room for improvement, which we'll actually use more advanced classifiers later on in this course. So now let's move on to section 4, where we take a look at machine learning in computer vision. Now, just before I move on to this topic, I want to speak a bit about machine learning. Machine learning brings a whole host of advanced or more accurate abilities to computer vision. So I hope you're excited for this. You'll get to see a lot better image classifiers, image detectors, or object detectors, I should say. So stay tuned for these videos in section 4 and 5 and 6, and you'll start using Keras and TensorFlow to do some pretty cool things. Thank you. Computer vision. And we're starting with machine learning in computer vision. So what exactly is machine learning? Well, machine learning has been synonymous with artificial intelligence over the last few years, and it basically entails how we can make software or computers learn. So essentially, machine learning is actually statistical analysis of statistical predictions repackaged. And the reason it's been repackaged is because it's shown enormous growth over the last 5 to 10 years. And that's mainly because a lot of these machine learning libraries are becoming so easy to use in high-level programming languages like Python. And combined with all the breakthroughs in different research, different algorithms, things like sklearn, which has made machine learning so easy to use within Python, combined with cloud computing and the use of GPUs in training complicated deep learning networks, it has made machine learning so popular in such a demand field. That is why data science, that career of data science, has been exploding over the last few years, because now we have the tools to analyze all this data we've collected over the last 10 to 20 years. But what is so special about machine learning? Well, think about something here. Think about machine learning versus explicit programming. And what is explicit programming? Well, imagine we had to determine what person would likely buy, say, our premium life insurance package. Now, there are several factors you can look at. You can look at age, income, gender, career, education level, job title, number of children, and a lot of other data. However, setting hard rules to determine which person is likely or not, and how do we even measure likeliness? Do we give it a score? Is it a yes or no? We need something that can take all of these inputs and output basically a probability or like a level or ranking of a score to indicate how willing they will be to buy insurance. Well, machine learning solves this because imagine explicitly if we had to say someone over 65 making over this amount who is male or female has a bunch of these careers. That's like very, very complicated set of rules. And imagine you have to give different levels of ranking like 1 to 5. You can see how complicated that can become. So now let's talk a bit about the 4 types of machine learning. And arguably the most powerful machine learning algorithm is neural networks. And neural networks are the same thing as deep learning, but we'll discuss that more later on. However, let's look at the 4 main types. There's supervised learning, unsupervised learning, self-supervised learning, and reinforcement learning. Now, we're particularly going to spend a lot of time on supervised learning, but let's discuss what each of these are so you have overall knowledge of what machine learning is and what it can do. So let's take a look at supervised learning, which is the most popular form of machine learning that's implemented today. Basically, what supervised learning does, it takes a bunch of input data, these are called features usually, and once it into our machine learning algorithm or model, it outputs either a label or a number indicating something that we desired. So example with willingness to buy insurance. Imagine this is all our data here. We have age, income, blah, blah, blah. We just input this data into an algorithm and we get bang, a score saying how likely that person is to buy insurance. That's pretty cool. So how does our algorithm learn, or how does it actually do what we want it to do? Well, we have to give it example data. So what does that mean? Is that we give it a lot of label data. Label data means example data like we'll teach a child. So you basically tell the machine learning algorithm, let's say if we're doing a spam example, these 10,000 emails are spam, these 10,000 emails are not. The machine learning algorithm looks at a bunch of different attributes in that data, and now we can send a brand new data input to that model and get an output. So that's essentially how supervised learning works. Now let's look at some supervised learning examples in computer vision. What we can do with supervised learning is that we can classify types of images. So you can do things like identify whether image has a cat or a dog, or basically is a pornographic image or not. You can do things like object detection. Object detection is these things here, figuring out these different objects in the sky. And image segmentation, which is separating different layers of the image. So we identify this is a laptop, this is a cup in the foreground, this is a wire connecting the laptop, this is a desk. So you can do those things. That's called image segmentation. So now let's move on to unsupervised learning. So what unsupervised learning is concerned with is finding interesting clusters or clusters that belong together in input data. So in this case, we don't have label data. We are just giving an algorithm a bunch of data and we're telling it, figure out what belongs together. So for this example, you can think of these 5 inputs here. We have chocolate, vanilla, beef, pork, and chicken. And we send this data to an unsupervised machine learning algorithm. Consider something like k-means, which is one of the most popular unsupervised learning algorithms. And what it spits out is clusters that are close together using some sort of distance metric. Now that's exactly what happens here. Let's assume it's examining ingredient components or chemicals in these food groups here, and it figures out that vanilla and chocolate belong to one cluster, which is like a dessert cluster, and these 3 belong to a meat cluster, which is this one here. So that's pretty cool. That's how it works. Now let's look at self-supervised learning. Now self-supervised learning, it follows a similar concept as supervised learning. However, the data isn't labeled by humans. And so how are these labels created? Well, it's often done using heuristic algorithms, things like autoencoders. Now these things are a bit beyond the scope of this course and get quite complicated, but an example of this is something that can predict the next frame in a video given the previous frames. So that's how we can use it in the computer vision world. Now let's talk about reinforcement learning. Now reinforcement learning is potentially very interesting. However, it's not totally mainstream in the AI world just yet because its applications are somewhat niche for now. However, there's a lot of potential to apply this to other learning fields, so especially in robotics as well. But how it works is the concept is fairly simple. Imagine you're just teaching someone, and when they make a mistake, you give them a penalty, and if they do something good, you give them a reward. So that reward-based learning is essentially how the algorithms in reinforcement learning learn. So how is machine learning done? So we talked a bit of things like I may have mentioned training or learning, but what exactly is it? So how is it done? So let's take a look at supervised learning, the supervised learning process in machine learning. So firstly, remember I said we need label data. Now that label data is often called the ground truth or human label data. It's essentially the examples that we give to an algorithm that tells it this is what it is. Figure out a model that can predict this now from new inputs. So how it works here is that we split the data. Let's use a cats versus dogs image example, since this is a computer vision course. And we split it into a test data set here and a training data set here. So what's the difference here? Now, the training data set is the data we are giving the machine learning algorithm to learn on or train on. So it takes this data and it looks at different things in it. Now, if it's deep learning, you can look at a lot of complicated different things. If it's a less complicated algorithm, it's going to look at maybe different pieces of image. So it's going to look at different pixel values in different areas. So that's what it's doing by learning or training. So what is the test data used for? Now, the test data is to test or assess the performance of your algorithm on brand new data it hasn't seen before. So you can get an accuracy level of how it performs on real world, or you don't have to say real world, but just unseen data. So firstly, after we have the data here, we basically fit that training the model on this training set, and then we evaluate the performance on the test data set. That's what I talked about. So that's the supervised learning process. So what exactly is this model I'm constantly referring to talking about? So basically, a machine learning model is just a bunch of mathematical equations where we give it some input data and it creates an output out of it. So now that doesn't really help you too much, but that's essentially what a model is. And different types of machine learning algorithms create different models. All of these things are basically weigh things essentially on different inputs here to see how much should contribute to the output score. And then things like deep learning can consider different combinations and different how to move together. So it can get quite complicated if you look at the maths behind it. So remember I said the inputs are multiplied by something called weightings, and that's how we get the output. Now, this is essentially a very simplistic form of what a model actually looks like. You can see it here. We have weight 1 for input 1, blah, 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 get an equation here, and basically gives us the output in the end. So this is a basic level of what the equations look like. So now let's refer to some machine learning terminology that I'll often use in the next few videos, and you'll often hear if you're practicing this in the workplace as a data scientist. So this is some basic machine learning terminology that you'll often hear me talk about. So you have things like target data. Target data is essentially the ground truth labels or the human labeled data that we have in the training data set. Those are our targets. I can also refer to targets of the test data, but just remember, there are ground truth labels that are referred to as a target data, okay? Now, prediction is essentially what you think it is. It's just basically an output from the machine learning model given some inputs. Classes are essentially categories that exist in your data set. So remember in our cat first dog classifier, those were 2 classes. Similarly, gender one will have 2 classes, it could have more as well. Now, classifier or classification refers to a machine learning model that outputs categories or classes. It doesn't output real value continuous numbers. It outputs all probabilities, or it could output probabilities in some cases by tweaking it. It outputs categories that your input data should belong to, like cat or dog. Regression is the opposite in a way, but not essentially the opposite, but it's different, where it actually outputs the continuous real value numbers. So imagine a model that's trying to predict someone's height or weight. Height or weight isn't really in categories. Essentially, it's measurements. So it can output like a height of 172.6 centimeters and a weight of 50 kgs or 120 pounds. That's what regression does. And validation of test data. Now, they're usually different things. However, in a lot of machine learning training algorithms, they can be considered somewhat the same thing. It's basically the data we test our machine learning model on. So it's supposed to mean unseen data, not the training data, any other data but the training data, okay? So let's quickly summarize what we've learned in the video. Now, this video dealt with a lot of different things, and it dealt with machine learning in a very high-level way, but I assume you now understand what exactly machine learning is, the types of machine learning, the step-by-step process by which we train an algorithm, in a supervised machine learning algorithm, I should say specifically, and what exactly machine models are, and some general machine learning terminology. So now we take a quick look at deep learning and neural networks in our next video, so stay tuned. Hi, and welcome to the video on deep learning and neural networks. So firstly, what exactly is deep learning? Well, let's take a look at the power of deep learning. Now, firstly, machine learning has been around for decades, even though it's only recently become very popular. Now, what brought about the data science revolution was the simultaneous increase of computer power, cheap data storage, cloud computing, and most importantly, very high-level developed software and tools and programming languages that made deep learning or machine learning very much accessible to the masses of statistics students, mathematical students, computer science majors, economics majors. Anyone who can understand high-level maths and some basic computer programming could take control or make use of deep learning now. And around 2010 is when we sort of reached a bottleneck on performance of many of the traditional machine learning models, things like logistic regressions, SVM, all of those things were sort of capping out or maxing out on their abilities with complicated data. Now, what changed? Deep learning came on the scene, and deep learning just ravaged all of those benchmarks and scored tremendous scores even beating human-level performance. So you can see it right here in this chart. Error rates on the ImageNet Visual Recognition Challenge in 2014 to 2015, the machine learning algorithms using deep learning surpassed human-level accuracy. So what accounted for deep learning's performance in this arena? Well, machine learning algorithms didn't work well on very complex nonlinear data. Deep learning was able to achieve this, as you can see in this first point here, by having these deep, complicated networks that can pick up these nonlinear relationships. And deep learning solved this and ushered in a revolution in AI and computer vision. So now we can do such amazing things that we didn't think possible 10 years ago. So it took our models from, yeah, that's pretty nice, to something that's, wow, a human can do that. And you can do this so quickly. You can do a lot of impressive tasks on automated ways so much faster with deep learning computer vision networks. So what exactly is deep learning and neural networks? So let's take a look at this. So in neural networks, you can think of it as a black box brain that takes inputs and gives an output. So you can imagine this feeding an image into some sort of complex model here and tells you it's a dog, similarly for a gorilla. So it's different and a lot better than most traditional machine learning models because, as I said before, it learns non-linear mappings to produce far more accurate output classification results. So this is how a very basic neural network looks like. We have input nodes here. Remember, this is our same input data that I showed you before. This can represent things like income, age, sex, or in a computer vision world, this will be pixel 1, pixel 2, etc. Now, this is the layers here that are important here. These hidden layers are basically trained and they have different weights that are multiplied by the input values here, and they combine all of these different weights here to give different outputs. So one output doesn't matter. So these are the layers, as I said. We have the input layer, the hidden layer, and the output layer. All deep learning networks have a similar architecture. And these are some examples here, very high-level examples of what it can output given some input data here. So how do we generate a prediction? As I said, you can have something, say, representing feather color. You can describe a color here, or give the color values as input. You can give the weight of the bird, and it outputs the species and the sex of the bird. So that's pretty awesome. So this is what a real neural network example looks like. You can have multiple hidden layers, and that's what makes it deep. The number of layers here refer to the deepness of a neural network, and that's what deep learning is about. And we have all these inputs here and all these output layers here. So it looks relatively simple. This is a computer vision example here. We have our input image here, going through our hidden layers here, and it gives a final output right here, being 4. So that's awesome. So it's a handwritten digit, by the way. So what is deep learning? So now I refer to the deep before, deep being the number of hidden layers, and that's exactly what I say here. You can look at this architecture here. So it's another one for a computer vision application here. You can see it learns different features as we go through the deepness of the network, or the deeper layers, I should say. And now there's a good point to note that deeper isn't always better. You can have a lot of problems, especially in training a deep network. So it's also going to learn maybe something that's too complicated in a way, so it overfits some of the training data. Overfitting is something we'll discuss later on. But yeah, that's what it is here. Deep refers to the number of hidden layers. That's what deep learning is. So now let's talk about training neural networks. So let's talk a bit about the training process of neural networks. So I'm going to talk this through, and you can try to follow by reading the points, but imagine we have our training data here. Remember, training data is our human labeled images, or for example, we'll use images in this case. So what we do is we input one image or a batch of images to this neural network here, and then it'll give us some output here, because what we do is we initialize some random values, some random weight values here. We can have different ways we can set these random values, but this, for now, consider it's all random values. So obviously, if you feed some image or images here, you're going to get output data that is obviously wrong. But how wrong is it? That's what we use something called a loss function to do. We put a value on our loss, so it can be something like mean squared error or a different type of thing, basically scoring how bad it is from the correct label. And then what we do, we use something with backpropagation to perform a mini batch gradient descent. So what that does, basically based on the loss, we update or change these weights here to now compensate to lower the loss function here. So the next time we send these images again, we hope to get lower loss here. And that's essentially, each time we do that for a batch of data, it's called an iteration. And until we complete it, it's called an epoch. So that's what we're doing training. So we keep sending these batches over and over and over. And once we finish, that's an epoch that we've completed. And we should have some now decent weights that are lowering this loss constantly. And the lower the loss we have, the more accurate our model becomes. That's what loss measures. Remember, loss measures inaccurate you are. So by lowering the loss, you're getting more and more accurate. So that's why we have to do large number of epochs. And that's why neural networks take a while to train. So this is a graphical illustration of the training process here. So remember I said we have our input data. This is our neural network here, or hidden layers, if you want to consider it there, because that's where our weight values are. We have the output predictions. We have the loss function, which compares the predictions with the true targets here. We have our optimizer. So that's the backpropagation algorithm that gives the new weights here. And the new weights are then fed back into the layer here. So we update the weights of these values here in the hidden nodes. And then we send the image again. So we keep doing the cycle over and over. So what is backpropagation? So backpropagation is a pretty cool algorithm here. So as I said, we calculate what it does. We have the loss here. So then it feeds the loss back into the network here. So it's called backpropagation. And it uses that to calculate the gradients now of the hidden nodes here. So we change the gradients being the weights here. And we just feed it down the network here. And then it just updates. So now the weights are set in the direction to lower the loss in the next batch. Okay. So what have we learned here? We've learned what is deep learning and what makes it special, what are neural networks and how it is structured, the architecture. And we have seen a high-level view of the training process of neural networks. So now let's move on to the introduction to convolutional neural networks in our next video. Thank you. Hi, and welcome to our video on the introduction to convolutional neural networks. So in this video, we'll discuss a lot about what makes convolutional neural networks so important to computer vision. So firstly, why are CNNs or convolutional neural networks needed? It's because neural networks don't scale well to image data. So remember how our images are stored in arrays? We have 3-dimensional arrays like this for color images and 2-dimensional arrays like this for grayscale images. So let's look at that. Remember we have this. So now, imagine we had a simple image classifier that takes a color image with input 64 by 64. So now imagine now the input size to our neural network is going to be 64 by 64 by 3. That's how much different input values we have. So this is going to be a very complicated neural network. Imagine we went to 640 by 480. That's going to be 921,600 weight values. That's going to be a very big and massive network. It's going to be computationally very slow to calculate and train this type of neural network. So we need to take advantage of image data. And what is consistent in image data is that we have different patterns or different colors that are correlated. So that's a very important concept. And there must be a way we can take advantage of this. And that's where convolutional neural networks take place. So this is what a convolutional neural network structure looks like. And we'll delve into each one of these in this video and what they do. But effectively, this is the convolution. This is what happens here, where it takes a segment of the image, extracts certain features, or learns features in that section here, and then there's a bunch of different things here that finally lead to our output. Now, convolutional neural networks take advantage of the 3-dimensional volume of images, essentially, okay? So images consist of height, width, and depth being our RGB color components here. So if we treat our image data like this, like a 3-dimensional array, which it is, we can effectively take advantage of a lot of the correlations within image data. So let's take a look at this now. So why 3D layers? As I just said, this allows us to use the convolutions to learn image features. And this concept allows us to use far less weights in our deep network, allowing for significantly faster and better training. So this is what the convolutional layers look like. We have our input here, which is our input image. We have our convolutional layer here. We have the ReLU layer, which is basically combined with this, just the activation layer. We have our pooling layer, which sort of downsamples the image here. We can have another convolutional layer with ReLU. We have pooling again. Then we have something called the fully connected or dense layer that leads to our outputs here. And the outputs being basically probability scores of what the object is in this image. So in this case, we can see it's not so much a panda or a dog, but definitely a cat, which it is. So let's talk about the convolutional layer, which is the most significant part of a CNN. So what exactly is a convolution though? Now, a convolution is a mathematical process or term that's used to describe combining of two functions to produce a third function. And this function is what we call our feature map. So a convolution is the action of using a filter or kernel that is applied to the input, and in our case, the input being our image data. And it does that to produce the feature map. The feature map is essentially pieces or segments of the image. So we'll take a look at this now. So what is a convolutional process? Remember I said a convolution is a mathematical term that produces a third function. This is our input, this is our convolutional matrix here, or kernel, and this is the output or feature map. So let's see how we apply this to this to get output here. So now let's simplify this to ones and zeros here to make our life a little simpler with the calculations. So imagine we have this grid here, this 5 by 5 grid here, ones and zeros here, and this 3 by 3 matrix here with ones and zeros and a -1 here. So let's see how we can multiply these two to get our output feature map. So this is exactly what we do. We put our kernel over here and we slide it across 1 pixel at a time, or whatever we set it to. And essentially this is the calculations it does here. So we have 1 by by 0 plus 0 by 1 plus 1 by 0, and so on. This here, which gives us this here, which gives us the value here too. And as we slide it across this one here, we'll get a value for the third one. Slide it across this box here, we get a value for this. Move it down 1. So you can see how by passing a tree by tree kernel over a 5 by 5 input layer here, input image, we get a tree by tree output. So this is exactly what we do. As I said, we keep moving and sliding around over and over and over. So what are the effects of the kernel? So depending on the values of the kernel matrix, we produce different feature maps. So applying our kernel produces scalar outputs as we just saw. Now convolving with different kernels produces interesting feature maps that can be used to detect different features. That's a key point here. Now convolutional keeps a spatial relationship between pixels by learning features over small segments as we pass over the image. So what does that mean? That means that you can go back to this here. If this is a 5 by 5 image here, and we get a tree by tree output here, where we learn some sort of thing from the image here, this is our feature map here, it basically keeps the spatial relationships, maintains the spatial relationships, I should say. So we keep it consistent. So whatever was in the top corner of the image here is still represented in the top corner here. Whatever is in the bottom corner here is still represented over here. So now, why do we need many filters, not just one? We can design our CNN to use many filters, as much as we wish, and in different sequential combinations. So now let's assume we use 12 kernels, 12 convolutional layers here, okay? So this is a 28 by 28 image here, and this is our kernel here, and this represents here our output from each pass of this kernel here, or over the image, our output here, represented in 12 of these kernels here. And you can imagine them stacked like this together. That's how we envision or imagine our kernels that we produced, okay? So now remember I said we have ReLU and convolutional layers combined. What exactly is ReLU? And what exactly is an activation layer? So remember, in neural networks, what makes neural networks special or synonymous to our brain or neurons is that once it reaches a critical point, the neural fires. But what is that critical point? Well, let's look at this here. ReLU is a rectified, stands for rectified linear unit, and it simply changes all the negative values to 0, leaving all positive values unchanged. So effectively, anything that's positive, it fires. Anything that's negative, it basically clamps to 0. That's how it's represented in this function here. So by applying ReLU to this here, this is our output. It's quite simple. So that's what our activation layer does. This is how, after we produce our convolutional feature map here, we apply ReLU to it here. So that's how it moves forward. So what about pooling? Now pooling is also known as sampling or downsampling, and it's simply the image process where we reduce the size or dimensionality of the feature map here. So imagine this is our feature map that we produced before. It was a tree by tree. In this example, it's a 4 by 4. And if we do something called max pooling is typically the most popular type of pooling we use when building convolutional neural networks. This is what happens here. So this is what it's downsampled to. We just take the max value here. So all this time you can see all our layers are doing is basically encoding complicated patterns, but sort of compressing it, okay? And by doing that, we're learning many different attributes of the image here, of our input images, and storing them as compressed, basically generalized detectors that fire on different reasons, okay? So now let's lastly look at a fully connected layer, also known as a dense layer, which you'll find out shortly in the code. Now, fully connected simply means all the nodes in one layer connected to all the outputs in the next layer here. The FC layer, which FC stands for fully connected, outputs class probabilities where each class is assigned probability. So imagine in our cat example, we have 0.05, 0.04, and 0.91. All of this sums to 1. Similarly, in this example I use here. So now let's talk about overfitting. So we're finished with discussing the layers of this convolutional neural network. We're now talking about how we train and what's a good model in a convolutional neural network or any kind of neural network. So let's discuss the concept of overfitting. Overfitting is the concept where we tweak our model so precisely on our input data that it generalizes bad on new data. So this is an example here of classifying points from left to right here. All these blue points here in one class and all the green points here in the other class. But you can see that this point here, even though it's in the example data, it's here, generally you'd want to consider this point to be in green. This is what an ideal balanced network looks like. And you might think this is a good network here, but what if this blue point, which is slightly shifted here in new data, is it still going to be blue? It should all be green given the cluster of data here. This can be an anomaly or mislabeled data. You don't want to learn too much on training data so that these examples take precedent. You want to have a generalized network that's ideal so that it can treat new data quite well and give them accurate classes. Underfitting is now the opposite of overfitting, where we have a model that's basically just too simple to generalize well on new data. Now let's talk about regularization methods. Now regularization method is one of the ways we avoid overfitting. Now overfitting is something CNNs and neural networks are very prone to, so we have developed many methods to sort of reduce or avoid overfitting. So the first one we look at is dropout. Now dropout refers to just dropping nodes from the hidden nodes and visible nodes we saw in our neural network. If you just drop out some of the nodes during the training process, we sort of find a way to not learn too much about the input data so that we can generalize better. Now there's also something called L1 and L2 regularization, which are applied in many other machine learning algorithms as well. And what they do, they basically just penalize very large weights on our nodes so that we actually don't have extreme responses to certain input data. Also, we can look at some cross-validation, also known as k-fold cross-validation, which is a method of training where we split our data into a number of folds and train on them and then test on another fold here. So you can see we keep one fold, we hold one fold back, we train on these 4 folds here. This is our training data set here, all of this here. And then we just keep doing it by piece here. So effectively what that does is that we just keep one piece of the training data out of our first training loop or epoch. Now, another training method regularization method we can use is something called early stopping. So early stopping is a way we just set the parameters or some threshold criteria, typically loss. And once loss has stopped decreasing and starts to increase, we basically stop training at this point here, because what's going to happen is that we're going to basically, this is validation loss that we're looking at, or test loss. Sometimes test loss comes down gradually and this is good. But then if it starts shooting back up now, what's happening there is that it's basically overfitting on your training data and performing poorly or generalizing poorly on your test data or validation data. And lastly, a good method I find to use is data augmentation, where we just make slight variations in the input data like this, so that it sort of like magnifies or amplifies the amount of input data we have. So what have we learned in the video? We've learned why convolutional neural networks are better suited for image classification, how they are structured, their layers, their architecture, the purpose of each part of the layer, why overfitting is bad, and some methods of regularization that are used to avoid or reduce overfitting in convolutional and neural networks. Thank you. And now let's move on to the next video, where we take a look at creating a convolutional neural network using Keras and TensorFlow 2.0. So stay tuned. Hi, and welcome to a video where we take a look at how we create a convolutional neural network using Keras and TensorFlow 2.0. So firstly, what is Keras and what is TensorFlow 2.0? So firstly, Keras is a high-level neural network API specifically for Python, and it makes constructing neural networks or convolutional neural networks extremely easy and extremely modular. It has the ability to use TensorFlow or CNTK or Theano backends. However, now with TensorFlow 2.0, it is very closely integrated with the TensorFlow backend. It's actually built into TensorFlow 2.0 to be fair, but now all of the features, all of the modularities are built together, and it's all credit to this guy, Francois Cholet, who has been he's been tremendous in making deep learning more accessible by making and developing Keras over the last few years. So what about TensorFlow 2.0? Now, TensorFlow has been developed by Google, it's developed in-house by Google Brain in 2015, and it has now included the Keras API within the TensorFlow 2.0, okay? Now, what TensorFlow is essentially a low-level computational engine that is used for high-performance numerical computation, and it crosses a variety of platforms and uses CPUs, GPUs, and TPUs. It is applied to many other languages like C++ and now JavaScript and TensorFlow Lite, and I believe Java, I'm not entirely sure, but it started with Python. It's a Python API, and it is relatively simple to use as well. However, Keras is far easier, and it allows us now to build complicated neural networks that utilize, as I said, GPUs and TPUs and CPUs scalable fashion, so we can take advantage of large computing warehousing power. It allows us to view the training process and a lot of other things with the computational graph provided in TensorBoard. So why use Keras instead of pure TensorFlow? Well, like I said, Keras is extremely easy to use. It has a very Pythonic style of coding. So if you're very familiar with Python, using Keras is very straightforward and very easy. Modular means that we can add or remove different layers quite easily as well. We don't have to think too much about it. Also, we can just change different things like cost functions, optimizers, different initialization schemes, activation schemes, regularization schemes. You can just toy with a bunch of different things. So it makes just toying and prototyping convolutional neural networks or neural networks so easy. So it just speeds up the process so much. So unless you're doing cutting edge academic work, or you need some kind of groundbreaking performance with using maybe some sort of pure low-level TensorFlow or something in C++, using Keras offers so much versatility and its ability to quickly create efficient neural networks. So how do we go about building a CNN using Keras? And it's often referred to as TF Keras, TF for short. When we import TensorFlow, you'll get an understanding of what this is. So these are imports here. So when we're importing Keras now in TensorFlow 2.0, we didn't have to put TensorFlow.keras.models, but now because Keras is built into TensorFlow, we can just quickly import TensorFlow.keras.models and get all our TensorFlow layers and features and different algorithms, different loss functions, optimizers, all from these imports here. So this is the basic building blocks we'll use here to create a simple convolutional neural network. So this is the structure of how we use Keras to create a model. Firstly, we create a sequential model. Sequential meaning one layer comes after each other, so it's all linked in a straight line. There's no what do you call feedback loops or types of things. Straightforward neural network or convolutional neural network. We can just do model.add to add a layer, specify what kind of layer it is. We can specify kernel size, the size of how many convolutional layers we want, type of activation we want, and the input shape, which is the image input shape is referring to here. We can then add max pooling and create our max pooling window size. We can then flatten that layer, feed it into a dense or fully connected layer that outputs the number of classes here using different activations. Now we can compile it here by specifying the loss function, the optimizer, and what metrics we want to look at. So you can see how simple and straightforward using Keras is to create a convolutional neural network. It's pretty much as straightforward as it can get. So now this is the other part here where we actually train the model. So we can specify the batch size, epochs, how much information we want to see while it trains, and point it to our validation or test data here, and specify our input training data here. And it's basically that easy and that simple. So what didn't we look at here? How did we get our input data? How did we get X train, Y train, X test, and Y test? That's something we're going to have to learn by using Python itself. Now, how did we get information about the details of the model I'm creating? How do we specify things like which loss function optimizer, what activation functions to use here, those sorts of things? We don't know. We didn't talk about it yet. And how many layers is enough to design an optimal network? These are things we'll discuss in a later video. But for now, let's take a look at how we actually train a convolutional neural network. And by the way, just going back to the slide, the reason I mentioned these things is I want to get you started thinking about these things, because thinking about designing convolutional neural networks is extremely important in the ability to create some cool networks. So once you're aware of these things, you don't have to think about it too much yet, just be aware of it. And as we progress to more complicated convolutional neural networks in this course, you'll start getting exposed to what these things mean. So now let's take a look at the training process here. So remember, I said this is the general structure of a convolutional neural network. Now this is the training process here. Ignore this for now. It's just for you to reiterate what we learned before. So the training process is we get the data, prepare our data set, which is basically pre-processing of it to get it ready for our CNN. We design and create a model, which is what we discussed before. This here, what configuration, how many convolutional layers, what different activation layers to use, blah, blah, blah. Then we just train our model. We take our results, analyze our results, and then if the model looks good, we can actually test it on some real world data. So what have we learned in this chapter? We've learned what is Keras, what is TensorFlow, why Keras is so important, how do we use Keras to build a CNN, and we looked in the last slide, the training process of a CNN, and we just talked briefly about different ways we can tweak CNN designs. So now let's go into Python and in our next video and load and prepare data for our Keras CNN. Thank you. Hi, and welcome back. Now let's get started with loading and preparing our image data before we actually start training our deep learning networks. Alright, so let's go ahead and open this file, 15, creating a CNN using TensorFlow 2.0. And here we go. So it's loaded now. Alright, so now let's get started. So what I've done, I've created this notebook where I've put a lot of different steps in between, and a lot of these steps have important notes in between so that it can help you guide you through this project on your own. So the project we're about to do is creating a model based on the MNIST handwritten digits dataset. So first step in this whole process is loading our data. Now, loading our data is probably a minor part of it. However, if you're loading actual image data from a raw dataset, it can be a bit tricky sometimes. So firstly, what we do is that we import our TensorFlow.Keras datasets module that's listed right here, and then we import the MNIST dataset. And then we use the MNIST dataset, which is not a dataset just yet, but it's an object that contains the data, to load our data right here. So we apply this function load data, which is part of this object that we're importing here. And then that basically gives us our data right here. It returns a tuple of data. You can read about how the data is described here, or you can click here and actually get more information about the sample datasets that Keras provides. And what we can do, we can actually look at the shape of each dataset here, because what we get is 4 different datasets. We get X-train, Y-train, X-test, and Y-test. Now, what are these things? X-train is the bulk of our data. It is just our raw data that we're going to use to train our model on. Y-train corresponds to the same number of entries as X-train. However, it's the labels for X-train, and X-test and Y-test are similar. It's a test dataset that we use to test the model that we create using this data, X-train and Y-train. So by printing the shape of X-train here, we can see we have 60,000 rows or 60,000 entries or individual sets or pieces of data. And 28 and 28 here are the dimensions of our data. Remember, this is an image dataset, which you will see shortly, and this data contains 60,000 entries here. And what this does, this loads our dataset. It may take a couple minutes maximum, depends on your internet speed if it has to download the dataset. But mine is already downloaded, so you can see it just took about 5 seconds to load our dataset here, and we are actually printing the shape here as well. So now this is step 1, loading the raw dataset. Step 2. Now, you don't always have to do step 2, but it's a good practice. It's examining and taking a look at the different dimensions and shapes and the number of entries of the data. So we can see, I'll just run this here. Shouldn't take too long. And now you can see the shape of the data, which we printed out before. So we have some little words here to go before, so it helps explain to you what you're looking at. So we have 60,000 entries for X-train at 60,000 images that are 28 by 28 pixels that are all grayscale, by the way. If it wasn't grayscale, you'd have a 2-dimension 28, 28 comma tree being the RGB colors in it. This one you can see, as I said, 60,000 samples of our training data. Number of labels should be the same, 60,000. Again, in our test data, 10,000 and 10,000 samples. Remember I said you always want to have more bulk of your data in the training data set. Usually a 70-20 ratio is good. However, you can do 80-20, even 90-10 sometimes, depending on the quantities of data. I'm showing you the dimensions here as well of X-train, how much labels, and similarly for X-test. So now let's do something a bit more fun. Let's take a look at some of the random images in our data set. So this is some OpenCV code here. What we're going to do, we're just going to run through 6 images here using a for loop right here. From 0 to 6, we are going to generate a random number between 0 and the number length of X-train. So this is going to generate a number between 0 and 60,000. Okay. And then we're going to just get that X-train sample right here by using this as the index. We get our image, we resize our image just to make it bigger because 28 by 28 is going to look tiny on my laptop screen. And then we're going to show the image here. So let's just run this code. And you can see it looks like a 0. All right. Let's see another one, 6. Remember, these are handwritten digits, so they're all going to be different to each other, like different types of 0s, 6s, 7s, 9s, 3s, 7s, and so on. Now let's do the same thing. Now, I haven't introduced this to you before, but you can also use matplotlib to show images as well, okay? How you do it, use a plt_imshow function. This is what you're going to show here. This is going to be an x, y type dimensions here, 28 by 28 grid. And you're going to use CMap, so color map, and you're going to just use gray. This is a grayscale image. And this is a subplots here. What this means is that we're going to have tree by tree. And the last digit 1 simply means that we're just talking about the first plot here. That's why it says 2, 3, 4 in increments there. That's because you're talking about different plots when you're referring to this here. So this just refers to the first plot, second plot, blah, blah, blah. So now let's show our plots. Now the code is already run, but let's just run this here. Oh, just so you know, a lot of times, the first time you run a matplotlib plot, you're going to need to do it a second time, just because the first time it actually doesn't show the image. So there we go. So now we have 1, 4, 2, 5, 2, 7. Very neat way of putting images, displaying images without using OpenCV. And because it's a matplotlib plot, you actually get the axis scale here, which is 28 by 28. As you can see. So now let's move on to step 3. Step 3 is preparing our dataset for training. So let me run through this code and I'll talk about this, go through it. So firstly, let's just get a number of rows and image columns. As you can see, it was 28 by 28. And you know what we're doing here. We're just taking the first image from X-train and getting the shape. This is the rows and this is the columns here. Quite simple. We've done a few times before. Now let's get our data, not date. Let's change this. Whoops. In the right shape needed for Keras. Now, what I should have started this chapter off with telling you is that we're using Keras within TensorFlow 2.0, which is why if you go back to our top, our imports are from this module here. It's TensorFlow.Keras.datasets. Previously, when we used to use Keras before TensorFlow 2.0, you would have to import TensorFlow separately as well. Actually, you didn't have to import TensorFlow separately unless you were using a TensorFlow operation. You just have to remove the .TensorFlow part and you can directly import from Keras. But we no longer need to do that in TensorFlow 2.0. Just something to note. Hope I didn't distract you too much from your learning with that, but now let's move back to this. So now, as I said here, we need to add a 4-dimension, thereby changing our original image shape from this to this. So what we simply need to do is we use a numpy.shape function because these are all numpy arrays. All of the data we get from Keras. NumPy is a very fast, efficient numerical computation module within Python. It's built off Cython, so it's super fast. And what we do, we just put the shape here. So we have, this is a 28 by 28 here. This is a 60,000 rows we have here. And this is just the 4 dimension we want to add, which is just 1 dimension here, just because we just need to get it in this format for Keras, okay? And then we just store the shape here. This is going to come in useful later on. And what we do as well, we change our type to float32, because Keras needs float32 type digits to do the numerical computations involved in deep learning training. So we just change it, just change the NumPy array as type float32. Don't remember what it was before this, but it most likely was unsigned int 8, which is uint 8, okay? I believe it's that. If it is not that, I will correct it and put a note at the end of the video, okay? Originally. So now also, we do need to normalize our data. Now, normalizing is not always necessary, but it helps a lot with the deep learning computations. And what we do, we're changing the range of the data from 0 to 255 to now limiting the scope from 0 to 1. So that's simply done by just dividing by 255, and we just put 255.0 to keep our float type. Now, this isn't necessary most times, because that's because we did this operation before. If we didn't do this operation above here, and we simply divided by 255, it would give incorrect values because it would just be 0 or 1, because it wouldn't actually be to give the decimal form here. So just something to note with Python. When you're messing with different data types, be careful. If you want to keep something as a float data type, always put it as a decimal form, okay? And then what we do, we just print out the shapes here and end. So you can see that we didn't actually change anything, and the shape we wanted is now what we were getting. So let's just run this quickly. And yeah, so this is the shape we wanted. Our NumPy array for xtrain is now in this format, and yes, our samples are the same, so it's good. And remember, we did this for only xtrain and xtest. We didn't need to do this for ytrain or labels and ytest, because what we're doing with our y labels here is that we're going to do something called one-hot encoding our labels. This is an image I've created here that shows you what one-hot encoding is. So you know how we have 0 to 9 labels or classes? What we want to do, instead of having it in one column, we're going to put it into 10 different columns here. And this column is going to be, the first column is going to be representing 0, second column 1, and so on. So anytime something's like a 4, instead of having it as a 4 here, we're going to have it as 1 here, and all the rest zeros. Likewise for 5, likewise for 2, and blah, 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 and 6. And the reason we do this is, firstly, well, because Keras requires us to put our label data set in this form. And secondly, it's because there's no real ordinal relationship, so we kind of want to keep them independent. Otherwise, you can get some bad performance or unexpected performance if you were to keep your labels like this. Now, I don't believe in Keras you can do it any other way with your labels. Maybe you can, I just haven't had that much experience with using it to see if we could, okay? Anyhow, just assume for now you always do have to do this. And you can do this by using toCategorical here, which is a built-in function in Keras. So that's pretty cool. Also, pandas. If for those of you who are familiar with pandas, pandas has something called getDummies, which does something similar as well. So now let's move on to creating our model, which is the next part of our video. So just to quickly summarize what we've just learned, you've learned how to load data from Keras's default datasets. You've learned how to reformat this data or reshape this data in the format required by Keras for xtrain and also for the label data where we use one-hot encoding. So now let's move on to training our CNN and analyzing its performance in our next video. Thank you. Hi, and welcome to our video on training our convolutional neural network and analyzing and even testing its performance. So now let's go into our IPython notebook and bring up this chapter. So now we're continuing from our previous IPython notebook, which was 15, creating a CNN using TensorFlow 2.0, and we're on step 4 now, which is creating our model. So I'm going to step through this one a bit slower than I might usually go, but it's just because I want you guys to understand exactly how we construct and build our convolutional neural network using Keras and TensorFlow 2.0. So quickly, let's just read through the notes here. We can skim these notes for now because I've put a lot of comments in this code here so you guys can understand what's going on. So what we're doing, we're constructing a simple but effective CNN that uses 32 filters. What are 32 filters? Remember, those are the convolutional kernel filters, and the size of the kernel is going to be tree by tree. And we've added 2 layers of convolutional operations. So we have 2 conv layers, and the second one has 64 kernels, or 64 filters, I should say, that are sized tree by tree as well, not tree by 2. And let's go back to this. And what we're doing then, we do some downsampling to 2 by 2, and then we apply a dropout of 0.25. This can change anything we want, to be fair. Anything that's good, maybe between 0.1 and 0.6 are good dropout p-values. And then we flatten our max pooled output, and then it connects to dense or fully connected layer, which has an output size of 128. But we don't have 128 classes, we have 10 classes. So what we do, we then apply another layer of dropout that sets it to 0.5, and then this 128 output from this fully connected layer here is then connected to another FC dense layer that outputs to our 10 categorical units. So in case you didn't follow, what we're going to do here is just simply construct this model. So these are our inputs for all the different layers and model types and optimizers as well that we're importing from our TensorFlow.keras packages. Okay, so now you don't have to remember exactly where these things are from. You'll see these packages, these functions in a lot of example CNN or neural network code. Remembering with import them isn't too important, but when you're importing layers, they come from the layers.keras.layers. Optimizers come from here, so it's kind of straightforward. So now let's move on to creating our model. So before we do anything, we create our sequential model. Sequential meaning each layer comes after the other. There's no recurrent or feedback loops in this network. So then what we do, remember we went through this in our slides, we add a layer. When we do that, we just use model.add from the model object we created here. And then we specify what types of layers we're adding. So we're adding a convolutional 2D layer, 32 of them, that's a quantity. Kernel size is 3 by 3. Activation unit we're going to use is ReLU. Remember, ReLU is the best for CNNs. And input shape is going to be the input shape that we defined higher up here, 28 by 28 by 1. So that's pretty cool. And now what this does, having a kernel size of 3 by 3 reduces our size to 26 by 26 here. And then what we're doing, I'm going to kind of say this, repeat this a bit from above here. Remember this describes our CNN. So I'm repeating this a little bit now, but that's okay. All right, it'll help you by me repeating myself and reiterating it with code, helps you understand what's going on. So this is our second convolutional layer. Remember I told you we're adding 2. Now this one, we're going to add 64 filters, or 54 convolutional layers. Layers or feature maps is actually a better way to call it. And we're same tree by tree size kernel and activation unit tree by tree again. Now, because this comes directly after the first layer, we don't have to enter shape here, input shape. It assumes the input shape is the output of this here. That's a kind of convenient feature that you want, that you like in Keras. A lot of other deep learning libraries aren't so simple to use. So then what we do here, we just simply add another max spool layer right here. Spool size 2 by 2, then we add a dropout, then we add a flatten. Well, actually, we don't add a flatten. Flatten, we do add it with the model.add, yes, but what flatten does is that it flattens our tensor object before we feed it into our dense layer or fully connected layer. So you can read this a bit here. A flatten operation on a tensor reshapes the tensor to have the shape that is equal to the number of elements contained in the tensor. So what does that mean? That means that if our CNN, remember when it goes from 12 by 12 by 64, it's going to flatten this out. So it's just going to multiply these numbers out. So this is now our output from the flattened layer. Now this will all make sense when you see the diagram after. And I'm holding back the diagram a bit just because I don't want you guys to actually get too into the diagram as opposed to forgetting the code. It's sometimes better if I showed you the diagram first, but regardless, we're in code right now. So just forget the diagram for at this moment. So now what we do here, we do model.add, and now this is our first fully connected or dense layer here. Again, the activation we specify is ReLU. Anytime we're using an activation layer in one of these layers here, it will be specified as ReLU here. Don't worry. Then we have max, we have the dropout here as well, 0.5. Then we have our last fully connected layer. Now this is the one that outputs our class probabilities here, okay? So what we're going to do, we're going to have model.add dense, number of classes here, and we're going to use softmax here because we use softmax when it's a multi-class output, a problem. If it was binary, like yes, no, or cat, dog type network, we would use sigmoid here for the activation. And then what we do, which I didn't mention before, is that we do compile this model here. So we just use model.compile, and what this does is constructs basically an object using the layers that we specified here before. We also have to specify our loss. We use categorical cross entropy loss when it's a multi-class problem again. If it was a binary problem, we would use binary cross entropy here. So now for optimizer, remember optimizers? There are things like stochastic gradient descent or Adam and those types of different, I guess it'll be gradient descent methods that we use. We're just going to use a simple basic one here, stochastic gradient descent here, the default algorithm, and we're going to use a learning rate specified here as 0.01. That's not too low. We could have gone lower, but let's just use it now for this problem. And the metrics we're going to monitor, if we're monitoring metrics here, is going to be accuracy. Now, you can use accuracy or you can use loss. Either one of those two are usually fine. And then what we do at the end, which is a good habit to encourage you guys to have, is just to print the model summary. The model summary is actually a pretty nice way of visualizing the network. It's not a visual representation, but it's quite convenient. So we can actually see how we go from input layer. Remember, our input is our first layer into this was 28 by 28, 1. That's our input shape right here. And this is our output shape when we use a tree by tree kernel on it. And this is how many parameters this neural network is going to learn from this layer here. Remember, we had 32 convolutional filters here. Then we have our feature maps. Then we have 64 here. And now this is how many parameters we now have here. Then we have max pooling, dropout. Those don't have parameters we have to learn. The dense layer does have quite a bit of parameters here, as you can see. And then we have a final dense layer right here. This gives us a total number of parameters of 1.2 million roughly, which is quite substantial, but they are sometimes much more complicated convolutional neural nets. And to be fair, this actually isn't too bad. It's a fairly simple network. Now, this is a diagram I created here. This is very useful for you guys as beginners. It shows you exactly how we go from our input layer, kernel, or filter here. So we have 32 filters. This is how it looks 3 dimensions when it's stacked. This is our input, our output size, 26 by 26 by 32, 64, 24, 24, right here. Now, how it outputs looking from going into the downsampling or pooling or downsampling here, max pooling, remember that? Then we have our flattened layer, FC, and our final FC fully connected layer or dense layer right here. So this is quite cool. Now, let's move on to the big deal here, which is a training our model. Now, this part isn't too complicated, actually. It's just following some simple code right here. I'm just going to step through what is important here. So what's important is epochs. That's probably the most important thing. Batch size is fairly important. However, it's more for something you can experiment with. I tend to try to go for batch sizes that are somewhat reasonable, not too big, not too small. So it's kind of hard to give a guideline of what this is, but I tend to keep this between 16 and 128. You can use 128 batch size when you have a lot of data, like in this example, a lot of data and small images, 128 is fine. If you're using larger images, like something that's like 200 by 200 pixels, that's relatively large in the convolutional neural network space. It's not large compared to like a 1080p image at all, but it's large relative to this type of application. And in that case, if it was that size, I would tend to use a batch size of maybe 16. And why? Because batch size is dependent upon your RAM or memory. So if you have a lot of RAM, you can use larger batch sizes. If you have not too much RAM, maybe 8 to 16 gigs, you may want to use smaller batch sizes. So that's my side on batch size. Now let's talk about epochs. Now, epochs are very important. Epochs are how many cycles you wish to run your deep learning network on our data. So typically you want to go to at least 10. Sometimes you can get away with 5 if it's a super complicated network and you have a lot of data, but 10 is usually the minimum you want to run, at least to get a feel of what the network is doing. But many times I've seen people run 50 to 100 epochs to get optimal neural network out of their data. So let's now skip that explanation here because I've explained what epochs, iterations, and those things were in previous slides. Now let's take a look at how we actually train the network. So we train it. If you're familiar with sklearn, it's the same type of thing. We do model.fit. We specify the training data, training labels, batch size, epochs. Verbose equal 1 means we're just going to get some information while we train, and we then specify our information, I should say, like the performance and how it's progressing. And then validation is our X and Y test dataset. And then in the end, similarly to sklearn, you can do model.evaluate here, and it just gives you the performance using accuracy on the X test and Y test labels here. So you can actually assess, and then in the end, you actually get a score, which is a loss here, you can get a loss score, and accuracy right here. So without further ado, I'm going to run. You can train this network here. You can see my results here. You can see how long it took. It took roughly about 2 minutes to train, sometimes longer, sometimes 3 minutes here, to train through each epoch on my system. And you can see the accuracy going up. First accuracy on our training data was 82%, and 91, 93, 94, 95, goes all the way to 97. Okay, actually, yeah, 97. And then you can look at the test accuracy as well. That's a validation accuracy, 0.93, which is quite good, 0.95, 96, all the way to 0.98, so that's quite good. In the end, we got 98.6% accuracy in maybe just over 25 minutes. That's pretty good. That's pretty much close to world-class performance on the MNIST dataset right here. So what I'm going to do, you can run this on your own and wait about 20-25 minutes to get your results, but what I'm going to do, I'm going to hold off on this right now before you actually see how it looks, and I'm going to skip to plotting. Actually, I don't have the results to plot here, so I'm not going to run this, but I actually have run it before, so you can take a look here. So with this plot, when we store the model.fit results here in history, that's saving the history results of the training progress here. That's how we're able to plot these nice cool charts here, that you can see your loss going down, test and validation loss. This is the training loss here, test of validation loss going down with each epoch. Probably would go down even further if we were trained 50 epochs, but didn't have the time. And now, you can do similarly for accuracy. So by the way, you can just get the loss and accuracy from the history dictionary file here. So you can just take a look at the code to see how we got that data out of it and then how we actually plotted it here. So now let's go down to the important part here where we save our model. So you can save your model simply by just using model.save, specify the file name here. Typically a good standard I like to do if you want to include data is good as well. Just say the dataset, which type of model it is. So I call this simple CNN, and I specified how many epochs. This was very, very useful to me when I was training dozens and dozens of models for projects. You want to remember which model you save. So in the end, I would just put the date here of version. And it takes like a few seconds to save, maybe less. And if you want to load it, you can actually load it back here using load model function here. So I've saved this model previously. So I'm going to reload it here. Loading takes a little bit longer than saving. And there we go. So it's already loaded here. So what I'm going to do now is test our model on our test data. So I'm not going to explain this code in too much detail. You should be somewhat familiar with OpenCV. You may not be familiar with this make border function here, but what this does, this specifies a border around the image, which you'll see shortly. But what this function does is basically just pulls random images from our test data set and applies our model. Now, what I actually do want to do, just to explain to you guys, is how you actually test a single image on your model. So let's see how this is done. Look at this code right here. So what we do, we firstly just find a random image from our test data set here. So we get a random number, we get a random image here. Can we just put this into our model using classifier.predict? Remember I called it classifier when I loaded, no longer it's model. So what we do, we have classifier.predict input im. But what did I do right here? I changed the shape of the model from the normal image that was loaded here. This would have been a 28 by 28 image here. And what I did, I had to reshape it using this here. This means it's the first value or first image here, the image and the fourth dimension here. So we reshape it here. And that way we can now feed it into the classifier.predict classes function and get a result out of it. And then I'm using this function, I create a draw test here just to put, once we have the prediction here, we're just going to put that as a value predicted. So if it's 1, it's going to put a 1 using put text on the image. So let's see how this works. Pretty cool. This looks like a 2 and the classifier identified it as a 2. This is a 9, looks like a 9, 2 again, 0, 1, 4, 1, 1, 3. It's a 4, looks like a Y to me, but it's actually a 4, and it could be a 7 as well, but it's probably a 4. And that's how a model works. So now we can actually even test this on some real data. So what I'm doing here, this is a preprocessor function I created that had some quite useful little functions just to help us with some real data. So what this real data is here, some numbers I wrote on a paper. Forgive my bad handwriting, but it's good to test machine learning classifiers on. So what this does, this uses OpenCV's fine contours to extract the image here, get it a box around it, resize it, and preprocess it the way MNIST did. And so let's now get to 1. So extracted a 1 out of it here, and it actually identifies it as a 1 as well, using the predict function, the predict classifiers function, which is right here. Let's see if it gets a 3. It does. 5, 4, 0. Perfect. So it works. So now that's it for this video here. What you've learned quite a bit in this video. So you've learned how to build a full CNN, a convolutional neural network in Keras using TensorFlow 2.0. You've trained the model, you've analyzed the results. Now, we didn't do in-depth analyzing of the results, but we did analyze it to a degree where you could look at accuracy loss, training accuracy. We've saved and loaded models, and then we've tested our model in some test data. 2 types of test data, some actual test data from the dataset, and then some totally unseen real-world data that I've just showed you there. So what I encourage you to do is take a look at this code on your own, step it through, make sure you understand everything that's going on, because it's very important before you move on to the next video. So what are we doing next? In the next section, we're going to do some deep learning for more advanced image recognition. We're going to do some facial recognition and some gesture recognition. So it's going to be pretty cool. And the first video here is understanding CNN design and training. So stay tuned. We're going to do some deep learning for more advanced image recognition. We're going to do some facial recognition and some gesture recognition. Hi, and welcome to video where we take a look at understanding convolutional neural network design and training. So now let's proceed to understanding the basic structure of a convolutional neural network. So as you have seen in the last chapter, convolutional layers then use the ReLU activation, which then use max spooling then the dense or fully connected layer before we go to the last layer where we output the classes. Now, all CNNs basically follow this simple structure here. And however, the differences can be, we can have multiple convolutional layers, you can have multiple dense layers, you can have dropout in between, you can have max pooling in between different layers as well. And in the convolutional layers themselves, you can have different parameters we can mess with, things like stride, things like kernel size, how many convolutional filters you want. So these are just things to think about, but essentially they all basically follow the same structure we use in the last convolutional neural network in chapter 4.5 and 4.6. Well, we actually saw it in 4.6, so that's the one I'm referring to. So now these are some basic design rules you're going to want to know, and you're going to want to probably look back at this slide every so often in future when you're building your own convolutional neural network. So typically, the input size should be a square. So we've seen in MNIST it was 28 by 28, can be 64 by 64, can also be 222 or 229, I believe. That's CIFAR image sizes. Just so you know, this isn't necessary, but it simplifies our design, so you don't have to think about some things when you're actually using square images, and it speeds up our matrix calculations a lot as well. So also, here's another thing to think about. Input should be divisible by 4, which allows for downsampling. So you can see these are both divisible by 4, which helps with downsampling. It doesn't actually, it's not a rule, but it's just a good guideline to stick with. Also, typically, convolutional filters are 3 by 3 or 5 by 5. You can have bigger filters as well. VGG, I know, has a lot of different combination of filter sizes in its design. You can use different number of strides. Typically, you're going to want to use a stride of 1 when 2 or more if it's larger inputs, like the one for CIFAR, which is 229 by 229, I believe. Also, just so you know, you've seen what zero padding is. Zero padding is used to typically allow the output convolutional layer to be the same size as the input. That way, you can chain multiple convolutional layers together. You can have like a sequence of maybe 4 or 5. And if you use zero padding in between, you don't actually reduce the size of the image. So you actually still retain a lot of information still. So that way you can actually build more complex layers in the network later on. Pooled kernel size is typically, as max pooling, typically 2 by 2. It's a general good guideline to stick with. And also you should note, dropout is a very easy to use and useful technique to avoid overfitting in CNN. So it's something I use quite often. It does increase the training time, unfortunately, but we're going to have to live with that. So now let's look at the other things you can think about for design rules. The more hidden layers you have, the more features, particularly high-level features, a CNN can learn. So I like to use a minimum of 2, which is what we have in the diagram right here. Diagram below, this one. However, typically you can use at least 3 if you have a complex image data set. So the reason for that is because low-level layers, as a first layer here, learn simple details like edges, mid layers learn simple structures, and higher layers, these are the last ones here, learn more complex structures. And this is a simple flow which we've seen before. We have conv pool. That's the one for this one right here. So that's generally some basic guidelines in designing CNNs. So now let's talk about loss functions. Now, loss functions are integral in training neural nets and convolutional neural nets, as they measure the inconsistency or difference between the predicted results and the actual targets, which you've seen before. They're always positive, and they penalize big errors as well. The lower the loss, the better the model, and many common loss functions are things like mean squared error and mean absolute error, that's MAE, and mean bias error, hinge loss. There's a bunch of different ones. MSE is a very easy one, a common one that we use. Now let's look at how we choose loss functions. So remember we have things like categorical cross entropy and binary cross entropy. That's when you use it for different basically 2-class problems, binary or categorical class entropy. I'm not going to go into the details of what cross entropy and those things are. This is just general rules of thumb in this section. Also note the final activation layer when you use 2 or more classes is softmax. If it's just 2 classes, you use sigmoid. Now let's talk about optimizers, so how we choose optimizers. So now generally I will always use either stochastic gradient descent, SGD, with a decent learning rate of say 0.01 or maybe 0.001. Adam also in the adaptive rate optimizers. Adaptive rate means that they change their learning rate dependent upon the results it's being fed back in. So Adam is quite good. RMS prop is actually quite good too. They're all pretty good actually, to be fair, but I would like to start off using this and then maybe adjust things, or then start using this Adam as well. Now, what is loss and accuracy? Now, I mean, probably know this already, but loss and accuracy are important. And what loss is, remember we have loss functions which are trying to minimize the actual predicted results, the error in it, from what is actually the true labels. So loss you would expect. How does loss and test loss relate to each other? And accuracy as well. And this can help you understand overfitting as well. So as you train, the more epochs you train, you expect your training loss, that's the one in red here, to go down naturally. It's always going to happen, okay? And accuracy is probably always going to go up for training accuracy as well. But what can happen with test accuracy and test loss? Look at the green one here. This is test accuracy. Test accuracy in this case never seems to get higher than, say, 45%. It's always hovering around this section here, despite the training loss and accuracy getting to better values, okay? Loss going down to 0 and accuracy going up here. And you can actually see the test loss actually here is going up slowly. So what's happening here is that your model is overfitting to the training data, and it's not basically working well on the test data at all. It's actually getting worse here because the loss is going up. So what's effectively happening here is that you need to add maybe some more dropout, some more complexity to your model, even look at different things like data augmentation, because your model is overfitting. That is why these graphs that we plotted in the previous video section are so important to analyze. So now let's talk about epochs. So what exactly are epochs? So remember I mentioned this in the section where we were looking at the code? Well, an epoch occurs when a full set of our training data is passed, forward propagated, and then back propagated through our neural network. After the first epoch, we will have a pretty good set of weights. However, by feeding our training data again and again into a neural network, we're continuously improving the weights and lowering our loss on the training data, at least, in our neural network. This is why we train for several epochs or iterations. So iterations are something different here. Usually at least 50, but I mean, at least 10 is usually quite good. 50 plus is ideal. What about batches? So what exactly are batches? So unless we had huge volumes of RAM, we simply can't pass all our training data into our neural network during training. We need to split this data into segments. So that segments are called batches. So batch size is the number of training samples we use in a single batch. So example, say we had 1,000 samples of data, 1,000 numbers in this case, or the last case you remembered. So let's say we specified a batch size of 100. In training, we take 100 of the sample of that data and use it to forward and backpropagate it through our network to update our weights. If our batch size was indeed 1, which is a much smaller batch size, we're just simply exercising or doing stochastic gradient descent at that point, okay? Now, it is a bit debated whether batch size matters or whether it's important to have larger batch sizes or not. To be fair, in my experience, I do get better results when I use slightly larger batch sizes, which means that better hardware is going to give you better results, sometimes faster. However, it doesn't really impact it that much. So once you use a batch size that you can fit all the data into one pass, load your data, and then pass it through the network, it should be fine. Okay, so maybe a minimum of 16 would be good, dependent upon the image size, if your hardware can support it. Now, let's talk about iterations. So many people confuse iterations and epochs, including myself at one time. However, the difference is quite simple. Iterations are just a number of batches you need to complete one epoch. So again, in the same example, if we had 1,000 items in a data set, and we set a batch size to 100, we need 10 iterations to complete one epoch. It's that simple. So what have we learned? We've learned some general rules and guidelines when designing CNNs. You've learned a bit about loss functions and optimizers. You've actually learned what overfitting is and how to analyze the graphs. And you've learned a bit about what batches, epochs, and iterations are. So now let's move on to the next section where we take a look at gesture recognition using the sign language MNIS. So stay tuned for the next video. Thank you. Hi, and welcome to the video where we take a look at gesture recognition using the sign language MNIS dataset. So now let's move into our IPython notebook to get started with this exercise. All right, so let's open file number 16 called gesture recognition, and I already have it open here, so I'm just going to click on it here. So this is the sign language, the MNIS sign language dataset that we're going to do. This is the American Sign Language. I guess you can call it signs or language, I'm guessing, or symbolic language. Either way, this is what we're going to be training our neural network or CNN on. Okay, so now let's get started. So firstly, let's import the libraries we'll be using, and that should be done about now. Seaborn is, by the way, a plotting library or visualization library. Along with Matplotlib, we're going to be using it to do some visualizations that you'll see shortly. And what we're going to do, our data is not in the same format as we had before. It's in a CSV file. So if you know how to use pandas, you know there's this very simple function called pd.read_CSV. We call it pd because that's how we import pandas here, as pd. And we're going to take a look at that data right now. So let's load this first. Takes a couple of seconds again. And now you can do train.head. Head gives you the first 6 entries in our data set here, the first 5, I should say. And what's happening here is that we're going to have the first column here is a label. So we have label 3, 6, 2, 2, 13. What does that mean? Firstly, this is what it means. This is label 0, 1, 2, 3, 4, and so on, all the way to 24, I believe, because they left out the letter J and the letter Z, okay? There's a reason for it, kind of forgot right now, but I'll read it in between this lesson and remind you guys of it. Okay, well, I just actually had to look it up myself, and the reason for it is because both J and Z require motion, which we can't do here. I mean, we can do it, but it's not represented in our image data set here, so we're just going to ignore it for now. But take a look at this, by the way. You can see we have columns. Columns mean pixel 1, pixel 2, all the way to pixel 784. So what's the significance of 784? Well, 784 is actually 28 by 28. So this follows the same dimensions as the MNIS dataset, which is 28 by 28 grayscale pixels. These values of the grayscale value in the dataset here. So if we were to reconstruct this into an image, you'd have to get pixel 1 to 28 as a top row, then pixel 29 to 56 as a second row, and so on, and stack them up. And that would give us our images, which we will do in code shortly. So now, firstly, let's remove labels. To get labels out of it, we just do this, train labels, get the values, and assign it to labels here. So that's done. This is a pandas technique and how we extract columns. And let's just see the unique values in our labels here, which we can actually see using NBUnique, or you could have used pandas as well. But since we have gotten our labels here, we're just going to use NumPy. And we get 24. You can see the values here, 0, we left out 9, and it goes all the way to 24 instead of 25, or 26, I should say. Now we're going to use Seaborn here. This is the plot size we're going to use. If this is too big for your screen resolution, you can adjust it to suit. This is the width and this is the height. And we're going to do a count plot. This gives us how many values in our data set. So before in our MNIS data set, we had equal numbers of 1s, 2s, and 3s were roughly equal. We actually didn't explore that data like this. And the numbers weren't actually even. However, they were very, very close to even. This one is slightly more imbalanced, but this is totally fine. We can work with this. They're all roughly between, I would say, 900 to 1200, or actually it's above 1200 here. So that's okay. So then what we do now, we drop our training or label data set from it, because what we just want to remove this column here, just to get the pixel data as our training data set here. So we do that. And then what we do, this is how, remember I said we were going to reshape the data to basically stack the 28 upon each other? That's what we can easily do with this function here, this NumPy reshape function for I in images, and we just reshape I. That means we're going to do all the images in our data set in a quick batch, and then we're going to flatten it here, and then do it again here, all right? And if you wanted just to check it, you can actually run this on an image by image basis just to make sure it works, okay? So let's run this now. Let's run the label binarizer, which does hot one encoding, which you've seen before. Just another way to do it, and we can check it out to make sure it works. Can't really see the full extent of how many values are in this row, but it should be 24. You can actually check one if you wanted to see. You can just do this, and you'll see it should be 24. Exactly. All right. Actually, I'm going to leave this code in case you guys wanted to see. Yep, everything is in order. Let's just bring this back up here and comment it out in case you guys still want to see it. Okay, so now let's inspect this image here. So we're going to actually use plot show here to visualize the data right now. We didn't use CMap gray here because I wanted to show you guys how it looks. If you were to visualize this as a color image here, it tries its best. It's going to look funny, but this is how it sort of looks this is Matplotlib's interpretation of it. So you can see this corresponds to, I'm not even sure what that symbol is. I'm not saying now, it's a C. Yep. Okay. So that's pretty cool. Now we can actually do the same with OpenCV. OpenCV, we're going to actually bring it up as a grayscale image. So we're going to take a look at 10 random images in our dataset here. So this is a good idea of what our image dataset looks like, our training image dataset. So what we do next, we simply take our data here and we just apply the sklearn train test split function. Because remember, we just have our data in the other form. But what we're going to do, we're going to actually take our data here, images that we created. You can actually see that it's somewhere here we created. And we're going to split it up here, all right, into 70-30 ratio. And what we're going to do, we're going to train our model, test on this. And remember, we held back some data here. If you wanted, this is a Kaggle project, by the way. Kaggle projects, they usually have a separate test data set that we submit the results to. We're not going to actually do that today. We're just going to train on our training data set. However, we are just going to do it in a Kaggle practical project way, where we have 3 data sets. We have our training data set, our test data set that we know how it performs on, and then a totally unknown test data set that our model is going to try to predict it's on, so we can assess and compare its performance with other people and other classifiers or models out there. So now let's begin to train our model. So this is we just do the inputs. We declare our batch size, try and bigger batch size now, define number of classes, number of epochs. So let's run these here. Don't know if I ran this yet. I didn't, and now let's run this. This takes a little while, maybe about 5-10 seconds, just because it's importing these things. And now we're going to scale our images here. All right. And then now we're going to reshape them to the format that Keras likes. And just we're going to make sure this looks okay, just to be sure. And now we're going to create our model. So I'm not going to go into this model in detail. This is going to be sort of like a homework practice exercise for you guys, just to go through and understand the model that's designed here. Actually, a very simple model, to be fair. And let's just run this code to create our model. And then we're going to compile our model. And it didn't actually do it here, but let's just print the model summary in the end. So let's compile our model, which we did already. Print the summary, so you can just see the actual shape. It's a very simple model, 85,000 parameters. It's quite small, which is why I can probably let this train here. Now let's fast forward this video as a train. So let's run this. And you can actually see the training process as we go. Actually, I wanted to discuss this in the last video and I forgot to. What's happening here is that you actually see the ETA, how much, it's like an estimation of how long it's going to take to finish this epoch. The loss, you can see the loss going down steadily. And you can see the accuracy hopefully going up steadily as well. So I actually find it's pretty cool. Sometimes when I'm a bit bored, sometimes I just leave this and just stare at it for like a couple minutes. It does amuse my colleagues when I used to do this. I don't know why, just because maybe I looked a bit odd doing it. But I find it quite fascinating because it's like almost like a little game saying, oh, my accuracy is going up, my loss is going down. I wonder what's my validation accuracy going to be, especially when it's down at the end here. It's quite cool to anticipate what those results are. So I'm going to leave this, let it run, these 10 epochs, and I'll fast forward the video from here. All right, so we're done with that. It's a few minutes later, and you can see our accuracy and our validation dataset is quite good, 99.79, and they're perfect, actually. We could even run it a bit more to get closer to 100%, if that was possible, might have been. But either way, that's pretty cool that we got so close to being 100% accurate. So I recommend you save your model again here. And now let's do some plots here. You can actually see the accuracy plots on both the test and training dataset move into directions we wanted to. A lot of times in reality, your training dataset may actually show lower accuracy than your test dataset. We just happen to be lucky here. And now we can actually do one for validation loss if you wanted. I just actually did not do it here. Okay. Now what I'm about to do is actually evaluate its performance on the unseen test data that we have before. So you can actually run this piece of code here and it generates the predictions for the test images that it hasn't seen before. And now you can get an accuracy score here. So 80%, so that's not great, but it's pretty good still. It's reasonably good, I should say. It just depends on the actual data, on how well better models or superior models have performed, but this is tolerable. So what I'm going to do now, I'm actually going to test this on our real-life webcam data. So firstly, I'm just going to create a function that just looks up the labels here. So we have our labels matching the letters, and it just returns error if it's not there. And then what I'm going to do, I'm going to test it on actual webcam input here. So that's this code here. What this code does is just extracts a region where my hand is going to be in these shapes. So let's look at the shapes above that I'm going to try it with. Let's see, maybe we should try it with probably A, and A can be fairly easy. Then we can look at maybe a V as well, okay? And maybe even a C or B, all right? So let's see if we get those things. Let's remember what this is again. Yeah, I remember those symbols now, so let's go. All right, so let's test this on a webcam here. This is some pretty cool. This is why we taught this course with OpenCV in the beginning, so you can actually understand and build little things like this, all right? Okay, so I'm just going to run this code here. There we go. Let me move my microphone out of the way. Hopefully you can still hear me. All right, so let's test this out with an A, and we get an M. Let me actually bring up what an M looks like, so you can see it while I try to match these. Okay, so let's try an A or M. Apparently gets that right. That's cool. Let's try I. No, it doesn't work. It's an O or Q. It's very not good. Let's try a V. Thinks it's an X. Not good. Let's try an F. Try with a different end. Still doesn't work too good. Let's try a C. Thinks it's an E. It's an upside. I think I got a C just now, didn't I? Okay, so let's close this. So what you can tell quickly is that it did not work good. It didn't work well at all. And there are many reasons for it. Firstly, the pre-processing of I was feeding raw images into here and just resizing and grayscaling it and then reshaping it into the format before. However, if you go up above, let's look at the OpenCV samples, actually, this one, you can see maybe my background was too cluttered, maybe I need to flip my images, maybe my hands were just not good at sign language or whatever, but you can see it actually did not perform well at all. And that's a big reason why, a big weakness in, basically I should say, machine learning or even computer vision, in that real-world data doesn't actually match quite often the data set, the distribution that you trained your machine learning algorithm on. It's a very common problem, and you can see it here. So what does this mean? This means that performance is just generally, have the notes here, less than adequate in our training data because our real-life data is different. So what we're going to do in the next video is create our own gesture recognition system or engine using our very own data that you'll create by yourself or on your own using a webcam and OpenCV. So let's stay tuned for the next lesson. So to quickly summarize what you've just learned how to create a CNN and train it on our sign language MNIST data set. You loaded our data, you trained the model, you analyzed and tested the performance, and you understood why it was such a poorly performing network. So now let's move on to creating or building your own gesture recognition system with your own data. That's in the next video, so thank you. Hi, and welcome to a video where you're going to get to build your very own gesture recognition system with your very own data. So let's go back to our IPython notebook, the same one from the previous lesson, that's number 16, and let's start that lesson. So firstly, let's create a simple function that makes a directory if it doesn't exist, because more than likely, I may not give you this directory setup by default. I'll still decide later on before I give you guys the file, but in case you want to run this from scratch, it's always good to have this function here. So what we're going to do, we're going to use OpenCV to build our data set. So this is going to be a little bit confusing, this code here, but what it does, if I run this code and you see how it operates, you should be able to understand what's happening. Basically, the algorithm for this code is that what it does, you hit a button and it starts recording your hand gesture symbol in a region in a box I highlight on screen for your webcam. And what I'd like you to do is move your symbol in many different directions, go in, go out, tilt it left, right, pan across the frame, and then and then you hit, well, enter actually is key, a command, when you're finished. And then you do it again for the second symbol, and then you hit enter when finished. Oh, sorry, actually you collect first the training data, then collect some test data, collect some training data, then some test data, and then you hit enter to exit. So watch me do it first before you guys do it, and you'll see how it's done, how we collect our very own data. However, I do have instructions on screen, so it's not super difficult to follow. So let's run this here, okay? I'm just going to lower my microphone a bit and move it out of this scene, so hopefully it doesn't bother you guys too much. All right. Okay, so let's run off webcam collector. So what's going to happen here is follow instructions. You have to keep your hand in here symbol from the beginning, first of all, and hit enter when ready. So what we do, I'm going to hit enter now, and now we're recording. The number below you see is the samples we're recording. So I'm just moving this around, tilting it back and forth just to get some good images. Now, usually what I'll do, I'll stop when I reach 500, roughly. Okay, almost. There we go. Now, what I'm doing here, I'm recording now the test data. So our test data is supposed to be a little different, not too different. And there we go. So I recorded 100 and something, 150 to 200 test data, while I recorded 500 training data. So that's actually not too bad. Now let's do a symbol like this, and I'll hit, this is our second symbol. We're only training it for 2 symbols today. You can adapt this code to train it for multiple symbols if you wanted to, okay? So let's go. So let's train it on our training data, which is a fist, basically. I'm not entirely sure what I'll call this symbol. Maybe like yes or no, maybe. And when we reach 500, let's just go back, tilt it back in front. Let's go to the file on the screen. Okay, so let's now train the test data. So testing, tilting, trying to be a little different, maybe. Okay, that should be enough, and hit enter to exit. So what we've done there, we have just collected our test and training data set. So if you want to inspect it, let's see what happens here. So let's take a look at the folders we created before. Look in the file manager. You can see you created some folders called hand gestures training 0, hand gestures test 0, hand gestures training 1, hand gestures test 1. Okay, that directory setup here is the default directory setup that Keras uses. You can take a look here. I'm just going to drag my file Windows Explorer here. You can see you get hand gestures here, and you can see there's 2 folders, test and train. That's the default directory setup Keras uses. You can actually call this anything you want. You'll often see it called validation in some cases. Let's take a look. Each class of image has to be stored in its own folder and given a label. Typically, we use numerical labels 0, 1, and so on. 0 is our first hand symbol here. You can see this. I can't really see too much. We can probably zoom in a lot. You can see my face in the image here, but that's generally how it looks. And you can see all the 500 something images we created here and all the different variations, all stored as a 28 by 28 pixel grayscale image. Similarly, we have our other fist looking symbol. Let's just zoom into this one here. So, this is just our own data set. If you wanted to collect this to make it a really, really robust CNN, you would collect from different people, different backgrounds, different size fist, blah, blah, blah. So you can just take a look also at the test data set here. Similarly, you can see this changes to this style. You can see all the test images here. So now that we have our data set, we're going to use Keras's data augmentation now to enhance our data set. Now, data augmentation is the ability to take one single image, like images we trained in our fist, and put so many different slide variations like this here into our training data set, so that every time we do our training sampling, we're making variations or edits like this to our original image. This way, we actually add a lot more. It's a way of we can actually increase, or theoretically increase, the amount of data we have without actually having that data. So now moving back to our code, you can just see we follow our imports, number of classes, we set our image dimensions here. Normally we can actually take it directly from the image, but we just do it manually here. Set our bat size as 32. We're a bit all over the place with our bat sizes for the same size images here, just giving you different examples of different systems, what it could be. We set validation directory and our training data directory here. The folder we created in our base directory, hand gestures train, hand gestures test. And this is a part where we actually specify the data augmentation parameters. So we always set a rescaling here. This is general rescaling to make it between 0 and 1. We can do our rotation range. We know what rotation is. You can do our width shift, that's moving it left and right, height shift up and down, horizontal flip, you can flip it around to reverse it. That's quite useful in this case, in case your webcam inverted. However, because the sign language dataset relies on orientation, you should just put a note below or somewhere. You can remember this note. This isn't probably a good idea. So you may want to make sure your data that comes in is the same data that comes in from the webcam so that you actually don't do this. So actually, in reality, I'm going to make this false. It's not going to impact our, actually I'll leave it as true for now. But just so you know, it's not going to impact our binary classifier very much. So that's why I'm leaving it as true. You don't do any data augmentation on your validation dataset except for rescaling. This is what we want to do the augmentation on. And then what you do, you create generators here. So what we do, remember we imported something here called image data generator. Actually, we imported it twice. That's redundant. So remove this one. But yeah, so we have image data generator here. That's where this function comes from. All right, here. And it creates this object here. And what this does here, train data gen, is we take the images from the directory we're pointing it to. And it's a generator pointing to those images here. And we just specify some different parameters here where we have the bat size, the target size, color mode, the class mode. Just make sure these are consistent for both training and validation. And we just run this code here. So it's not super difficult. Just try to follow the same orientation, same like boilerplate code that you see here. So now let's create our model. We're going to use the same model as we did before. So let's just run this. And we print out model summary before. You can see it's 82,000 parameters. And now we're just going to compile this model using a different optimizer, RMS prop. We're going to use binary cross entropy. Again, the same metrics. And notice we actually manually put in these samples here. Those samples come from here. Actually, this is different sets of samples to what we did before. So please note that when you're actually doing this on your own, you're going to want to update it with your own values here. So otherwise it's going to return an error. Okay, so now let's run this model. Okay, shouldn't take too long. You can see it's quite quick. It's taking a bit longer than expected, but I'll fast forward the video for this when it's complete. Okay, so we're complete here with our training and see our validation accuracy is 90%, so that's quite good. So now let's just save our model like we usually do, and let's reload our model here just to make sure we have it. And what we're going to do, we're going to actually use now same code we did before to test our model to see how good it looks. So notice I spelled scaled wrong here. Let's run this code and check it out. Okay, so let me just get my microphone out of the way. Okay, so that's class 0. That's correct. Class 1, 0, 1. Let's see if it works consistently. It's not super consistent all the time. It's pretty consistent here. Let's do this. 0 works well. Works remarkably well so far. Very few fluctuations from 0. Okay, so it's pretty good. It's only when it goes in the upper corner here. Maybe my training data for this one wasn't too much. But overall, this model is working pretty good. So I just have this extra code here in case this code above ever crashes. You actually can use this sometimes just to close your OpenCV screen and get back to webcam. Forget about it for now. What I must say though is that you can see you just created your own model and it worked far better than the other model before that was using the MNIST American Sign Language dataset. You've just now created your own model from scratch using your own data. And this is a very good example project to carry you forward for your very own projects that you want to implement, especially using data augmentation to enhance those small data sets that you might have. So now let's just recap what we've learned. We've learned how to use OpenCV to collect out and generate our very own dataset. We've learned to use data augmentation and how it works. We've created our own model using the same CNN we used before, and we've tested this model to fairly good success. So now let's move on to something pretty cool, which is facial recognition with deep learning. So stay tuned for the next video. Hi, and welcome to Facial Recognition with Deep Learning, which is video 5.4. So let's get started with this video. So what exactly is facial recognition or face recognition? It's pretty much a buzzword right now with a lot of cell phones advertising facial recognition. You know about Apple's Face ID, all that stuff. But what exactly is it? Well, facial recognition is the ability to distinguish and recognize between individual faces. That way you can provide a measure of security by using things like facial unlock. It's only supposed to recognize your face, just like a fingerprint ID. Our faces are particularly unique, and they're actually a pretty good form of security measures and almost as like unique as your DNA imprint, unless you're a twin, okay? Which actually twins actually have the same DNA as well. That's why they have the same face. So what makes this special though is that our brains are remarkably good at this task. But what is hard for computer vision is that it's actually a pretty difficult problem because there are very subtle differences between faces. What I'm going to highlight in this image here is the difference between good and bad facial recognition. Obviously, I'm not George Bush. This is me here. And this is good facial recognition. You want something to identify, localize the face and tell you who it is. All right. So that's pretty cool. And that's what we're going to do in the next few videos. So why is facial recognition hard? Well, firstly, convolutional neural networks learn medium and high-level features quite well. However, these features don't really pick up the subtle differences between faces, which are things like just like a different size eye or different size nose or different cheekbones. We could look at these different faces here. So you need to have a way to extract these points and use it to train your CNN. So previously, a lot of shallow methods were used, shallow meaning that they looked at low-level type features. They were built using handcrafted local image descriptors. These are things like SIFT or local binary patterns or histogram of gradients. These are all basically just descriptor or feature descriptor methods. Now, I know we didn't teach this in this course. However, what feature descriptors are is a way of looking at interesting points in an image and only looking at the surrounding areas or regions around these points. You're going to take things like colors or histograms of gradients at those points, and you're going to use those to extract features from the image. So extracting features from only the interesting points and use that to train other classifiers or detectors otherwise. So problem with these things is that they never really had good performance in the real world. They were adequate in terms of like figuring out who you were, but if there was someone who was closely or similar to you, a lot of times it would fail. And to be fair, even training a regular convolutional neural network, even if it's a deep network like one of the complicated ones like ResNet 50 or VGG19, just throwing them a lot of faces, giving it to them to train, does not work well in practice, and you'll see why in the next slide. So traditionally, CNNs are very bad at facial recognition out-of-the-box CNNs, and here's the reason why. So let's look at actor Joey Tribbiani right here, played by Matt LeBlanc. That's his real name. Now, these are the images here. Now, all of these images are him. However, he's facing different directions here. His head is tilted back to the left a bit. Now he's looking down even more here. Again, it's the same image pretty much. And now his head is basically tilted the same way, but now he has a big smile and all of that is going on. So what's going to happen is that if you train a CNN, it's going to start looking at low level or all the features and learning a bit of irrelevant features, such as it may think anytime they get some training data with someone whose head is facing this direction, it might be Joey Tribbiani or Matt LeBlanc. So that's not good. You don't want your CNN to look at these sort of irrelevant features when training a facial recognition algorithm. You want it to look at everything. Low level, high level, medium level. So when I said CNNs end up learning low level features or irrelevant features, I meant they could learn things like someone's like a type of hairstyle or something can be someone else. I mean, yeah, those things are good, but in the real world, a lot of times these things fail. So now let's introduce one of the best attempts at this, which is VGG Face, which was developed by Oxford University researchers, and it was trained in over 2.6 million images with over 2,600 different identities. And you can look at these links here to take a look at the actual research and datasets here. Now, recently, last day, I believe, 2019, there was VGG Face 2 released. However, I've messed with it in Python a bit. It's not easy to use in Python as this one, although there's a very cool package from Keras that can work. However, we're just going to take a look at this implementation, which is quite good for our tutorial. Now, let's talk a bit about VGG Face and introduce the term Siamese networks. So now we spoke about the issues that regular CNNs face when trying to do facial recognition. So how did these Oxford researchers overcome this? Well, they used and developed something called Siamese networks, which are a way to use CNNs to extract pairs of features from different images and compare them. So you use something called Euclidean distance to compare them, but you don't only need to use this, you can use cosine similarity as well. So how do these networks actually work? Now, this is just a very basic diagram here that explains it. You give it a reference image, which is myself here. Give it a test image, which is President or ex-President Obama or former president. I'm not entirely sure what the terminology is. You feed these images into a Siamese neural network and output similarity score distance metric. That's all it is here. And this Siamese neural network here, it's actually a convolutional neural network that computes these differences here. So what I would like for you guys to do, if you're very interested in how this works, take a look at the papers that are published, listed here on this Oxford University site. So how this works now is that instead of using hundreds of thousands of images of a person to train a classifier, which you would normally need to do, we can do something called one-shot learning here, which is super useful and super cool. Essentially, imagine that you have a new employee that joins your company. You just take one picture of that employee, load it into the database of employees you have, and you can actually just quickly create some sort of facial recognition tool that works quite well and will work on that single one image from that employee. You don't need to feed it hundreds or thousands of different images of that one person to train this convolutional neural network, or this neural network, I should say, to use for facial recognition. It works without it. So what have we learned in this video? We have learned what is facial recognition. We've learned why facial recognition is difficult for conventional convolutional neural networks. We've taken a look at VGG Face and how it works, and that delved us into how Siamese networks work. So now let's move on to the next video where we actually start implementing a VGG facial recognition similarity comparison in Python. So stay tuned. Hi, and welcome to a video where we start implementing VGG Face tool for facial similarity comparison. Alright, so open IPython notebook number 17 called Facial Recognition with VGG Face. So I already have it open here, so let's just get started with this lesson. So in this section, what I'm going to do, I'm going to run through the code that helps us load and use our VGG Face model. So I'm not going to explain every single line in detail, how it is stuff you've seen before, so hopefully you can quickly follow. There's a new library I'm going to use here though, it's called Pillow, which is a very useful Python imaging library. Pretty cool, it has a lot of good tools in it that I use sometimes, better than OpenCV in some cases. You'll see how I use it in this exercise as well, and everything else is stuff you pretty much have seen before. So let's firstly just import all these things. Let's run this first block of code. And now let's define our VGG Face model. So this is a model here, the exact same model that the Oxford researchers used. You can see it's a relatively simple model. It just has a number of convolutional layers here. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, VGG 16. Hint, why it's named VGG. 16 convolutional layers here, all with zero padding at the end here. So we sort of maintain the size going through. And if you want, you can take a look at the research paper in the link in the previous video, so you can take a look at the CNN in detail if you wanted to. But either way, we just define the model, same model that those guys used right here. So let's run this now. Takes a couple seconds to run, and there we go. So now we're not going to train this model, okay? What we're going to do, we're going to download the weights, which I provided in the course already, but if you don't have it, you can download it at this link here or this link here. And what we do, put a line here, we can use this tool here called import from model here. I actually need this because I'm just using the model with load weights here, which model was defined. Either way, you actually just load the weights here. The weights point to a model that we already trained. So instead of using model load, we just load the weights. Now the weights will match the model that you defined up here. So you don't have to think about it too much. So now I'm going to talk a bit about cosine similarity. So cosine similarity is, remember we talked about Siamese networks, and Siamese networks are this CNN that's above here that gives us two outputs, and we have to use them. Once we send images in it, it uses something to find a distance metric between them based on the descriptors that those CNNs extract. So what we're actually doing with cosine similarity, remember we were getting a vector of descriptor outputs from our Siamese network, and what the Siamese network is using internally as well is a distance metric that we're going to use here, which is cosine similarity, and it simply measures the cosine of the angle between the two vectors that are projected in the multidimensional space that we're looking at here. All right, so it may seem a little bit confusing, but you can actually look online on YouTube to get some very nice tutorials that explain cosine similarity if you're having trouble understanding it. It's just a measure of distance, similar to Euclidean distance. Euclidean distance here would measure the actual distance here, distance AB. Cosine similarity is going to measure the angle here. So sorry if I was pointing here before. I actually meant to point here. Sorry about that. So anyhow, that's just now. We're going to define some two functions here that we're going to use in our little experiment using VGG face. First one is just a preprocessing function here. This preprocessing function is actually quite simple. It's just a way to take the image from the image path we specify and return the image in a way that we can actually input it into our CNN. We can propagate it using this function here, okay? Just to get the image in the correct form. Remember we had to change images in different forms in our CNN previously when we were training. Remember that? So that's what we're doing here. And now this is our cosine similarity function here. We have a source, we have a test representation, and we just do some basic mathematics using NumPy here, and the last line here to just get the cosine similarity. And now, lastly, in this little tool here, we create the VGG descriptor object. So that's just done here where we have model, and we have our inputs, which are the model layers from the first layer, and then the outputs as well here. And this one, I don't expect you guys to understand too much what's going on here. It's just the way we're utilizing the model for our purposes, okay? And now what we're going to do, we're going to define our verify face function where it takes two images here as inputs and then compares them and then tells you whether or not they're the same person based on the threshold that we've defined, okay? Our threshold is 0.4. Anything under 0.4, we're going to say is the same person. If it's over 0.4, we're going to tell the user, which is us, which is our own code, to be fair. It just tells us that it's not the same person, okay? And we're just going to use some little matplotlib things here just to plot out the images below. And we use our function right here. So as I said, remember, we're using VGG descriptor here to forward propagate our image in here. We point it to the directory, we preprocess the image, and then we just get the output of it here, the vector of outputs. So we have image representation 1 and 2, and then we just use the cosine similarity to find the difference between those two images here using our VGG face descriptors. Okay, so let's run this code. Okay, so we've executed this function. This is just to define this function here. And now let's actually compare it. So I'm pointing it to two pictures of my wife. And now let's run this and let's see if it tells us if it's the same person or not. So let's take a look. And yes, the cosine similarity is under 0.4, which indicates that it's the same person. So now let's try it with a different picture of her. Whoops, I accidentally revealed to you the cosine similarity already. But if you didn't see it before, let's take a look at what it is. And it is 0.31. So they're a bit dissimilar, but it's still close enough that we are using VGG to tell us that they're the same person. So this is pretty cool. Okay, now let's compare to Jennifer Lopez. So let's take a look at these two pictures here. And what do you think is the cosine similarity? Let's take a look. 0.425. And that means you're not the same person because you're different enough to be, again, over our threshold. So now let's compare Jennifer Lopez to Lady Gaga. Obviously, they're not the same person visually, but let's see, 0.47. So they're definitely not the same person. So that is pretty cool. Okay, so that is the end of our lesson here. So what exactly have we learned in this video? Well, you've learned how to load VGG and load the weights into the model. You've learned how to create the similarity function, which was the cosine similarity that we used. And you've learned what cosine similarity is actually. And then you learned how to use VGG face and the cosine similarity function, which we defined to compute the distances or basically find the similarity of faces. And it actually worked quite well in our examples. So now let's move on to the next video where we actually build our working deep learning facial recognition system. So stay tuned. Thank you. Hi, and welcome to section 5, where we take a look at how we actually build a deep learning facial recognition system in Python using VGG face. So now let's move on into our IPython notebook. So we're actually continuing with the same IPython notebook that we used in the last video, that's titled 17 Facial Recognition with VGG Face. So, we've been scrolling through this notebook, going through the similarity of faces, all of it, and now we've stepped down into the facial recognition with one-shot learning. So let's take a look at this, okay? So now I put some instructions here for you, okay? What we're going to do, we're going to firstly use some code here that extracts faces from pictures of people. All right, so this is some OpenCV code that I've wrote here, not only OpenCV, but it actually does a bunch of other things. It uses horror facial detector to extract the faces and then stores it in a folder here, which is titled people. I'm going to bring it up shortly for you guys. And what it's going to do, it's going to run through this directory here, people here, and then it's going to store the faces in the directory called group of faces, and it's going to put the name face underscore, whatever the name was in the original directory. So let's just run this quickly. This one is Jennifer Lopez, Lady Gaga, my wife, me, and there we go. So just those 4 faces, all right? And let us bring up my Windows Explorer so you can see the directories of where and how it was stored. So remember we had people were stored in this directory here, this the 4 of us, and groups of faces, let's go to this one, is where it stores our faces. So we actually have 2 faces here from previous time I ran this code. So these are just the 4 you should be seeing here, all right? So now let's move on to the code where we load our VGG face model here, code that you have seen before, and we're loading the preprocess function that we use. We don't need to load it twice, but just in case you didn't load it before. So let's run this, and it's going to print model loaded at the end when it's finished. So now we can actually start using this model on our webcam. So what's going to happen? How does this actually work? What did we do so far? So what we're doing so far, remember the 4 faces we loaded and extracted from those images and stored in group of faces, that directory? Well, imagine this group of faces being your employee database. And what we do, every time you want to add someone new to that database, you just add a face here, and you can just use your same facial recognition code here to get the person out of it, all right? So it looks at the images here and identifies it based on any new image it sees in the webcam. It's going to match it back to one of those images here in group of faces. So let's take a look using the same similarity functions we defined, by the way, in case you guys are wondering. That threshold is defined here. Just put it at 0.35 just to be a bit more stringent and strict. But let's take a look and see how it works, all right? Hope it works. Usually things don't always work the first time. And there we go. So it says it's me. Let's move my microphone out of the way. All right, so this is pretty cool. It actually is working. Nice. It has a nice little arrow pointing at me. Now, if my wife or someone else who is like Jennifer Lopez or Lady Gaga were in the room here with me, it would actually identify them correctly. So you can actually see how cool this is. Imagine you have an office with all your pictures of employees and you have different CCTV cameras that are like face level around the room. You don't want to have a top-down camera unless you use good top-down facial images to train it. But yeah, you can have it in that office and be picking up people's faces and tracking them all over the office, the whole building if you wanted. So that would be pretty awesome actually. So what about this? Can we train this to identify faces, in like a TV show? Like let's look at the Friends TV show. So let's take a look at the folder called Friends. That's these guys here from the Friends TV show. You remember this from the 90s, very, very popular, and early 2000s, I believe. So these are the 6 main friends, Chandler, Joey, Monica, Phoebe, Rachel, and Ross. And we're going to now train this, or use this, to identify those characters in our video. So we're going to do the same thing we did before. We're just going to extract the faces out of it here and store it in this directory called Friends Faces. So let's run this, and then we're going to get the face of each one of the 6. And those are the images that we're going to store in this directory called Friends Faces, okay? And then what we do is that we just run this. What I've done here, this is basically the same code that's kind of copy and pasted right here. But instead of using the webcam, I'm using video from the Friends TV show. So let's take a look and see if it works. All right, so that's pretty cool. So it identifies Joey, Chandler. Now, the reason why it's probably not detecting Chandler all the time is because our horror cascade classifier is sometimes missing it as a face, maybe because of the angle he's at. Let's see, got Monica correct right there. Ross and Phoebe, it's not detecting Rachel's face at the moment. Let's see if it does end up getting a face sometime. Okay, so it never ended up detecting Rachel's face. That's due to our horror cascade classifier being maybe not as sensitive as it should be, but it worked flawlessly for all the other characters, as you saw. So that's it for our facial recognition video using VGG face. I hope you enjoyed this video. And now we're going to move on into a quick recap of this video and then introduce the next section of video. So just to quickly go over what we've learned how to extract faces from images and store those faces into a new folder. Then we've learned to actually use VGG face on ourselves, or myself, or yourself, on your webcam. And then we learned to use VGG face on a video, doing the similar method we did before, where we extracted faces from some actors and actresses and then ran a video, test sample video. And it actually worked quite well. It picked up all the faces that we needed to pick up in video except for Rachel for some reason, but that was because of our facial detector, not our facial recognition system. So now let's move on to section 6. Section 6, we take a look at ImageNet, transfer learning, look at object detection, and even go into neural style transfers. So this is going to be pretty cool. So the next video is going to be based on pre-trained ImageNet models. So stay tuned. ImageNet, transfer learning, and look at object detection, where we take a look at pre-trained ImageNet models. So firstly, let's take a look at some famous CNNs. Now, if you're a computer vision enthusiast, you've surely heard of some of these famous CNNs, things like LayNet, AlexNet, VGGNet, VGG 16 and 19, ResNet 50, Inception, version 3, and Exception, and there are quite a few others like MobileNet as well. So what made these things so famous? Well, the performance on ImageNet is what made them famous. And ImageNet refers to a dataset that is the ImageNet Large-Scale Visual Recognition Challenge, which is basically a computer vision contest or challenge that's composed of 1.2 million training images with 1,000 object classes. And it's the official de facto benchmark to test how good your deep learning CNN actually is and where we've come. So you can see this is the progress on ImageNet over time, over these last maybe 20 years or so. Now, LayNet never competed in ImageNet. LayNet was actually on MNIST, okay? But you could look at AlexNet and look at ResNet. Look at the performance increase in the error rates here. Went down from 15.3 to 3.6. And look at complexity as well. Complexity has kind of roughly stayed the same in terms of number of parameters, hasn't it? VGG has a ridiculous number of parameters, 138 million. But when architectures got maybe more intelligent with ResNet, performance got better without actually making the parameters larger. So we can actually now load and experiment with these trained models in Keras. Now that's a huge advantage because some of these models would have taken weeks to train, and that's not an exaggeration. I remember some of them were trained on a parallel array of GPUs for 2 weeks before reaching that level of performance. So you can do this. We can actually do this in Python right now. We're going to do it quite shortly now. But what I'm going to mention here is that if you wanted to go to Keras applications here, you can take a look at all the pre-trained models that are shipped with Keras. So now let's move on into our IPython notebook and get started with actually experimenting with ImageNet pre-trained models. So I want you guys to open notebook number 18, ImageNet-VGG16, ResNet50, and Inception V3. So let's load this notebook here. It's going to come up in a few seconds, and there we go. So now the first time you load some of these notebooks, you're actually going to have to wait for it to download the weights. Now I have downloaded my weights before, so this is not going to come up again on my system, but you're going to see this message here on your system if this is the first time you're importing and loading the weights from ResNet. So you can actually see this is how we import weights or networks or pre-trained models, I should say, from Keras's modules and libraries and functions. So you can actually just point it to here, .applications.resnet. We're going to import ResNet50 to use, so we can use it here like this. And we're going to just use some little applications and things here. So let's do this. And let's see what it says. Shouldn't take too long. Okay, so we've loaded it now. Now let's go on into our ResNet model here. Okay, so what we're going to do, we're going to test ResNet on some of our sample images here. Now, this sample image is a dog. Let's see what it actually predicts. So I'm just going to go through the predicting process here. All right, sorry for moving up and down too much. Just going to load our image here using this function here. So we're going to got it from this image tool here. All right, so we're just going to load it here, and we get the image in our target size as well, specified here, and actually have it twice here. That's why I was a bit confused for a second. And then we just run through the array. We just bring it into array. We expand the dimensions. We pre-process the image here. Another function in Keras just gets it in a format automatically ready for prediction. So let's take a look at the prediction. All right, so these are the outputs right here below. We have a German Shepherd, or a Kelpie, or Malinois. So I know you didn't see the image here. So actually what I'm going to do is that I have that same image in a folder here. And this folder has some images here we're going to test here on ImageNet. So this is just a simple way just to load and to get an image and test it. So I'm going to actually bring up the image of the dog so you can guys see what it was before we actually move on to the next video here. So this was our sample image we looked here, and it actually is a German Shepherd, but you know German Shepherds look quite similar to German Shepherds, so it actually, as a third good guess, I'm not even sure what a Kelpie looks like, but it's probably something that looks similar to this as well. So you can see it worked pretty well. So now let's test this ResNet image classifier on a bunch of other images here that I've loaded. So you can see this is a mountain bike or a bicycle. It's actually a racing bike, but it actually gets it pretty quick, good here. Definitely not a Dalmatian. I'm not sure why that's a third one, but it's a fairly high percentage. Could be a plow, I'm guessing, maybe a plow. This bend here or this bend here could have looked like a plow to our ResNet, but it's definitely a bicycle, and it got it right. Let's see what the other image is there. This is our dog that we saw before. This is definitely a lion, 99.999%. Wow, it's pretty sure this is a lion. Not a collie, not a cheetah. Okay, very low percentages that it could be those. But a collie is not a bad guess. Dog that kind of has big kind of mane around its head, I believe. And a cheetah, well, maybe because it's a cat-like animal. Let's see what else this is. Yes, definitely a ship liner, not a dock. I'm not sure why. Maybe there was some ship and images of docks. There were ships in it, so that could have been confusing it. And it's not a container ship because there's no containers on this. It's like a cruise ship type of style here. So let's see what else. The tiger, definitely a tiger. Tiger cat, not entirely sure what the difference is. Maybe it's a type of cat that has stripes like a tiger. And a jaguar is a good close to guess. And this one is a yacht, and you can see it looks like a catamaran type yacht, somewhat, I guess. Yeah, I'm not even sure what a trimaran is or a yawl, but it was low percentages in those, relatively low. So that's pretty cool. So now let's actually compare VGG16 with ResNet50. So now let's firstly load the weights for VGG16. This takes maybe about 5 to 10 seconds, depending on the speed of your system. And while this loads, in the meantime, what I'm going to do, because I didn't mention this before in the previous slide, is that once we have the loaded model and we predict the image that we pre-process in a small little pipeline right here, what we do, we take this object here, this Preds VGG model object, that's our output predictions, and we run this into decode predictions to get text out of it. We get a top tree, that's what top equal tree is. We just get the first value in this array here, and then we can just use this now, feed this output here into our draw test function that I created. Draw test takes three inputs. This is the name of the window. This is the actual prediction outputs, and this is the image here. And let's go back up to draw test here. And it's a simple OpenCV function I built here that just puts a big border over the image and puts the text over the image here, along with the number of predictions here. So where we have this little loop here. So since we're taking the top 3 predictions, we just put the text over it, that image here, so we can display it. So now let's run and compare ResNet versus VGG16. So it takes a little while to run and initialize, maybe about 5 seconds, and here we go. So it's the same image in case you guys think I'm cheating. And we can see, let's make this back to here. You can see how it compares. So you can see both identified as mountain bike. VGG was a little bit more sure that it was bike. Bicycle built for 2, not entirely sure. Maybe it's like a double-seated type bike. Either way, it's better than a plow. I'm not entirely sure what an Alp is, but you can see maybe VGG is slightly better in this case. What about this one here with a dog, German Shepherd? You can see what it actually, we can see. I need to actually adjust this module to get the full percentages out of it here. We're going to change the border width here a bit, but that's okay for now. Or maybe reduce the size of the text, but they both got German Shepherd quite good. Now let's look at this one. You can actually see the full predictions here. They both say lion, which is exactly what we wanted to see, so that's ideal. And now this one says liner for both dog container ship, almost exactly the same top tree, so that's quite cool. View that. This one is tiger. You can see tiger. VGG is actually a little less sure that it's a tiger, a little more sure it's a tiger cat, so it's probably not ideal. However, the top tree and both are the same. And the last one is the yacht, and they both say catamaran. ResNet is a bit more sure. VGG is a little bit less sure. However, they both have the same 2 second top predictions. However, they're in different order. So that is quite interesting. So now let's do a quick recap. What we've learned what ImageNet is and why it's important. We've also learned about some famous CNNs and what made them famous, which was their performance on ImageNet, on the ImageNet dataset. We've learned about how to load these pre-trained models, these complicated, highly trained models in Keras, so we can use them on our own data and images. And we've actually experimented and compared the performance of ResNet50 and VGG16. So now, in the next video, we're going to take a look at transfer learning, which is a very important skill in deep learning and convolutional neural networks. It's going to help you save a lot of time. Thank you. Hi, and welcome to a video where we introduce the topic of transfer learning. So what exactly is transfer learning, and why do we need it, or why is it useful? So firstly, as I may have mentioned previously, training deep convolutional neural networks is often a very, very slow process. Networks like VGG in particular are very, very heavy with parameters. VGG has 138 million parameters, and ResNet also, while it has less parameters, has 50 hidden layers, which add this complexity and training time to the network. So while these networks attain excellent performance on vast datasets like ImageNet, they're extremely performance or computational intensive to train. Sometimes you actually need an array of GPUs, that's multiple GPUs, training these networks on these huge datasets for multiple weeks on end to reach a good point of performance and convergence, okay? So that isn't possible, especially you can't train these types of networks on your CPU laptop base. So even your GPU, if you're taking advantage of your GPU on your laptop, it's not going to be quick enough at all unless you have a very, very high performance gaming laptop with a 1080 NVIDIA 1080 mobile GPU. Maybe that can be okay, but you're still going to need to train these things for days on end to reach a good point. So how do we get around that? Well, what if there was a way to reuse these previously trained models for your own classifiers? So as you've seen, Keras ships or includes some pre-trained image networks for weights for networks such as ResNet 50, VGG16, Inception, and MobileNet, and many others. And these weights have already been tuned to detect thousands of low-level, high-level, mid-level features in that ImageNet dataset, which contains thousands of 1,000 classes of images. So what if now we can use these features that they've learned from those images in ImageNet to train our own classifiers? Well, we actually can, and it's quite simple. So that brings us to the topic of transfer learning. Transfer learning is basically transferring knowledge from one trained network onto another. So here's a definition from a deep learning textbook that says, you can click this link on right here, brings you to the deep learning textbook that I quoted this from, where it states transfer learning and domain adaptation refer to the situation where what has been learned in one setting is exploited to improve generalization in another setting. And that's exactly what we do with transfer learning. So in transfer learning, in applied to computer vision, we take a pre-trained deep CNN, one of these three or maybe one of the others, and use it, the already trained network, I should say, typically on ImageNet, or pretty much always on ImageNet, because Keras only ships with the ImageNet weights for these networks. And we use the convolutional layers, those trained convolutional layers, to aid our image classifying tasks. So what we're doing, we're taking our already trained CNN and training it on our new data set. So we're not actually training though the previously trained network. What we're doing, we're just going to train the top layer. And I'm going to explain it to you with some diagram in the next few slides. But what I'm going to say is that what we do is that we freeze the lower layers of those pre-trained CNNs and just train the top layer or the fully connected layers only. You can even train more, depends on what layers you want to freeze and what layers you don't want to freeze. And then actually, as I say it here, sometimes you can go back and train the lower layers if you want to improve your performance. But imagine you're taking a VGG network that's been trained extensively and you're just going to train the top layers of it, where just like a minority of parameters, like maybe a couple 10,000 parameters or more, or less, depending on what layers you freeze. And it trains much more quickly on your data set as well. So you can extract some amazing performance by taking advantage of transfer learning. So this is an example of what we do. This is not a complex network. It's just illustrative purposes. What you do in transfer learning is that you freeze the weights of a pre-trained convolutional neural network here, and you just take your input data set, unfreeze, change the top layer, use the top layer of what your number of classes are, how much fully connected nodes you want as well, and you just train this new model you've kind of meshed together on your data set. And then this is exactly what I said. You train only the weights in the red here. So just to reiterate, transfer learning is where you freeze the pre-trained lower convolutional layers that are well-trained and capture universal features such as edges, blobs, curves as well, maybe even more complex patterns and stuff like that. And what we do, we replace the top FC layer of those pre-trained networks with your own, mainly because you want to be training to fit a different number of classes. So in this case, you're going from 1,000 classes to, say, a binary simple thing you want to do, like say it's a cats versus dogs type image data set you have. And we can use a smaller learning rate to take advantage to help distorting the newly initialized weights. You don't want to jump over the global mean. So you just want to use a small learning rate to help that, okay? So this is just a general process here. Freeze lower layers, add our own fully connected top layer, use a small learning rate size, and you're good to go, okay? So what have we learned in this chapter, this basic chapter that introduces the topic of transfer learning? Well, you've learned the need or the importance of transfer learning. We've learned how it works, how we freeze the lower layers and just train the top layers, and which is generally the step-by-step guide of doing it. So now let's move on to the next video where we actually implement transfer learning using Keras TensorFlow and in Python on the Sapphire 10 dataset. So stay tuned. Hi, and welcome to a video where we take a look at implementing transfer learning in Python using Keras and TensorFlow, and we're going to use the dataset Sapphire 10. So now let's move into our IPython notebook to get started. All right, so now let's open our transfer learning lesson. That's notebook number 19, transfer learning with Sapphire 10, which I already have open actually. So remember, Sapphire 10 has 10 classes of data. We have airplanes, automobiles, birds, cats, deers, dogs, frogs, horses, ships, and trucks. Those 10 classes here. So let's load our Sapphire 10 dataset here by importing it. Import the tools we need from Keras and TensorFlow. Import OS because we're doing some directory manipulation later on. I'm not entirely sure why I needed it. But basically what we're doing, we're just mashing all the code together. We don't need this optimized anymore. We're going to use SGD, stochastic gradient descent here. And made a simple CNN. I think we've used something similar like this before. We just get our data here, load it, get the shapes out of it, just bring the shapes, scale it here, change the data type, add one hot encoding, and there we go. So just quickly give you guys a recap on how we build and you create our CNNs here using Keras and TensorFlow. So in a couple of seconds, you're going to print the model out, probably taking a bit longer than usual just because we have all these imports to do. But we wait patiently for it to complete because that's how we are. All right, so we're done. So we can take a look. We have 1.2 million parameters in our CNN. It's not too bad. Image size is 32. Okay, it's fairly good. So now we're going to train our model. So what I'm going to do, where's the epoch size parameter? All right, so 10 epochs. So let's train Sapphire 10 for 10 epochs and let's see what sort of performance we get Now, this is with no transfer learning. This is just raw, basic, normal CNN training from scratch. So let's take a look at this. Okay, just illustrative purposes of this lesson, I'm not going to train this for 10 epochs. Maybe I will, and just add this on to the end of the video. But for now, let's just see the performance we get after training for 1 epoch. That took 178 seconds, and we can see we got an accuracy of 0.21 on the training data set and a validation accuracy of 0.34. Not horrible, but again, these are 10 classes, so that's just a little bit better, twice as good as guessing. So now let's just move on to starting to use transfer learning. So we're going to apply those concepts we took a look at in the previous video section. But before we do, I've saved a model that we trained previously, so let's load this model and test it on some of our Safari images. Now this looks like a bird, but it's definitely not a horse. Car, airplane, got that right. It's a car, not a truck. It's definitely a truck, not a frog. It's a boat, not a truck. Boat, not a horse. That's a boat, not an automobile. That's not a cat, it's a car. It's not a deer, it's a bird. So you can see performance is abysmal. It's crap. So what can we do? Let's now look at using transfer learning to get better accuracy much faster. So let's import our Keras functions here. We're only going to train this for 1 epoch here. We're going to use a pretty small learning rate, as you see here. This is 100 times smaller, actually, than the learning rates we've previously used, which were e to the -2. We have momentum here, which I didn't explain momentum right now, but just look at this, use that default value. We're just going to load our data set here, and we're going to resize it, because the reason why we resize here is because we're going to use a VGG16, okay? And it requires an input shape of 48 by 48 pixels. So I know Safari is larger usually, all right? But we're just going to resize it to this size here, just to get our images in the correct size that we want to use. Because I know Safari, I think it's 32 by 32, I believe, anyway. So just one hot encoding there. And there we go. Now let's import VGG16, and you notice we have include top being false. We don't include the top layer of VGG16. We just include all of the base layers that we're importing here, and we specify we want it trained on ImageNet weights. So then what we're going to do now is that we're going to extract the last layer from the third block of the VGG model and call it last here. This is a way we can use base model here, get layer, specify the layer we want to get, go use .output, and we can just extract that layer here. So that's done right now. And then what we're going to do, we're going to construct now the top layer we want to create. So this is the way how we do it. Just use X as our model here. So we just create this here. So we have all of this here, batch normalization we're going to use, some dense layers here, we apply dropout as well, and then we're going to specify 10 classes here, and this is our final top layer here with 10 Safari outputs, 10 Safari classes. We use softmax as our activation for the last layers there, and there we go. And then finally, before I move on, we use this model function here to take the base layer here, input, and apply it to the top layer that we created before. Now every time, you may have noticed we put X at the end here in brackets, that's how we stack these layers on top of each other. So now the top layer is basically all of these here stacked on top. All right, and what we do finally is that we construct our full model here. Okay, it's just fully full. And we use a model function that we imported up here before. And our model function basically takes these inputs here and combines them together. And what we next do is that we actually have to now freeze the layers in our base model here. That's our model that's been tied together with the top model that we created here. And we freeze it. So the reason we freeze it is so that we actually don't make those layers, those parameters trainable. You don't want those things to be trainable. You just want to keep the top layers there. So now we're ready just to print the model summary. You can see because it wasn't the full VGG model we trained there, it's actually a much simpler version. However, these are all fully trained already. So that's why the trainable parameters are only these last few parameters here. If you add this up, 65, 65, 10, 2500, should give you 134. Non-trainable parameters, those are the parameters we froze here from VGG network that we extracted. All right, there. So now we're ready to just point to our data set here with our image train generator, create those little pointers there. And now we're ready to start training. And what you're going to notice immediately, some warnings are going to come up, but you can ignore those things. You can see, yes, it's going to take a lot longer to train still. It's going to take roughly about maybe 3 to 5 minutes to train this per epoch. But immediately you can see the accuracy is much better. It's 91% on our training data set. And if you scroll back up to see our base CNN that we used previously, forget my errors there, scroll past it, our accuracy was 0.21 after training for 178 seconds. So you can immediately see that using transfer learning has allowed us to have a huge jump in accuracy right from the get-go. So if you want, you can train this for a couple epochs, maybe 10 epochs if you have the time. It's going to take you roughly an hour to do, and you'll see your accuracy should be in the 90s for your validation data set. All right, so that's it for this lesson. Let's do a quick recap. You've learned basically how to load and train on the Safari 10 dataset, which we've seen is quite simple, it's a straightforward lesson. And now you've seen actually how to implement transfer learning by freezing the layers, building the model, and training the top layer of the pre-trained CNN to get vastly improved results. So now we can move on to some very cool stuff, which is object detection. So you're going to learn to use some deep learning object detectors, RCNNs, SSDs, YOLO, what are those things? And then in the next video after that, you're going to implement one of those things in Python. So stay tuned for those exciting lessons in our next videos. Thank you. Hi, and welcome to a video where we take a look at some deep learning object detectors such as RCNNs, SSDs, and YOLO. So let's start. What exactly is object detection? Well, it is actually the holy grail of computer vision. It allows us to do things like this, and you would have seen this before in our face object detectors and pedestrian and vehicle object detectors in earlier videos. However, those were limited to just one class, and if you were to add multiple classes, you would have to pile on multiple object detections, and that would slow things down significantly. So we're taking a look at now some deep learning, some very advanced object detectors that make things like this possible. This is pretty cool, isn't it? Car, dog, horse, person in the back over here. So what exactly is this? Now, object detection, as I said in earlier chapters, is a mix of object classification and localization. Classification means determining what the object is, and localization means identifying the region or the bounding box of the object. And it's used in face detection quite often, which we've seen in previous chapters. Now, the difference with object detection and classification is that object detection doesn't just tell you whether an image contains a cat or not, but it actually tells you where the cat or the objects or animals could be in the image. So that's pretty cool. Now, non-linear methods of object detection included what we discussed earlier, which was Hara cascade classifiers, and another one we didn't discuss in earlier chapters was histogram of gradients HOG with linear SVMs that support vector machines. It's a machine learning classifier. And the reason we didn't discuss these is because they are pretty much outdated now, because deep learning object detectors are significantly better and it can be used in a wide variety of applications that make it very powerful. But the reason why these aren't useful, although they are technically very useful when you're detecting just one object, that's why they're still very useful for face detection. However, when you try to apply this for multiple objects detectors, it actually breaks down. It doesn't work too well, and it can often be quite slow, and that's because it involves an approach called sliding windows, where you have to slide this window at various scales across the image, and that's why it is not a very efficient method. So in 2014, deep learning object detectors had a huge breakthrough with something called regions with CNNs, or RCNNs for short, and this achieved remarkably high performance in the Pascal-VOC challenge. That is object detection dataset that has been used to compete and score in computer vision journals and researchers to assess how good their object detection methods are. So basically ImageNet version of it. And in 2014, as I said, RCNNs achieved remarkable success. Now let's take a look at how RCNNs work. So RCNNs attempted to solve the exhaustive search problem previously performed by sliding windows by proposing bounding boxes and passing these extracted boxes to an image classifier. So now how do we get these bounding box proposals? And that's where we use an algorithm called selective search. So imagine we have an input image here and we just extract interesting regions here. We send these regions now to a CNN to classify, and then we get different classifications of what it thinks it is. So now let's take a look at the selective search algorithm. This attempts to segment the image into different groups by combining similar areas such as colors or textures. This could be interpreted as blobs or contours, and proposes which of these regions it is interesting using some of the other metrics within the classifier algorithm. And it proposes these boxes here coming out of this segmentation type task, and basically feeds these boxes here to the CNN to classify. When selective search found these interesting boxes, it takes these boxes and passes it through the CNN, as I said before. One was trained on ImageNet dataset, so with ImageNet dataset, so it's quite well tuned and well exposed to a lot of data. And then what we do, we don't actually use the CNN directly for classification, although we can. We then use an SVM, as I said, it's a support vector machine classifier, to classify the CNN extracted features. We just compute the CNN features and feed it into another classifier, an SVM type classifier. So after the region proposal has been classified, we then use a simple linear regression to generate a tighter bounding box. But what exactly makes a good box? How do we know this box proposal over this guy here is a good box? Now, before we move on to other types of deep learning object detectors, we're going to discuss some metrics on how you assess object detectors. Now, this brings us to something called intersection over union, or the IOU metric. So IOU is defined as the size of the union over the size of the prediction box. So typically, IOU over 0.5 is considered acceptable. Now, let's take a look at this metric in a little bit more detail. Imagine this green box over this car here is our true human-labeled box to identify the car. Remember, what we want in localized boxes, we don't want a box that predicts half of the car and then misses at the back wheel, or we don't want a box that covers the car, yes, but covers a lot of extra area around the car. We want a box to be nice and tight exactly over the object in question that we detected. So let's imagine this red box here is the box our object detector has proposed. Now it looks fairly good. It covers roughly about 80% of the image. That's pretty good. Now let's take a look at the one on the right here. This box, which is actually covers a lot more of the car, covers almost 95% or more of the car, pretty much just missing out this little back piece here, covers even more. So technically, shouldn't this be classified as a better box than this? Well, that's not exactly what we want, though, is it? We don't want our box to be all over here. So that's how the IOU metric is developed. It's the size of the union over the size of the prediction box. So the union basically is this zone here. What is this zone here? This zone is, we compute the area of this zone here, and the size of the prediction box is put over here. So what we do, okay, this is the size of the prediction box is always going to be bigger. So what this tells us is that we want this prediction box to cover as much of the green as possible without it being as small on green on the out as small as possible over the green, essentially. Hope you understand that. Maybe I'm saying it wrong, but essentially we just want this red here to cover the green as much as possible without being too much over it or too much inside of it. So that's how we get this metric here. So anything over 0.5 is considered fairly acceptable in my opinion. There are a lot more stricter guidelines when it depends on type of classifier you're building, detector, but essentially 0.5 is a reasonable score. As you can see in this box over here, let's take a look at what the IOU would be. So the size of a union here looks, this is estimated at 50%, maybe even a bit, yeah, let's say 50%. And then the size of prediction box is definitely maybe another 50% here. So you're going to end up with 5, basically it's a 50% over 100%, which is double the size of this. So you're going to end up with something like 0.5. Whereas in this one is basically, you can say this is 80% here. And this is area that is on the outside is probably like 0.6 of the ratio of this thing here. So you can understand how you get a much higher IOU with this metric here. Now, there's another problem when we have object detectors. Oftentimes, we will have multiple boxes being proposed over the same object, and the object detector may not even know it's doing it more than once, because remember, it doesn't actually know what's in the image. It's predicting interesting boxes in the image that it may or may not be correct. It's very hard to determine for algorithm to determine, is it two cars packed side by side? Is it one car? So what we have to do is, if we have our ground truth labels, which is a green box here, when we're testing our object detectors, you may often get multiple windows proposed like this. So there's another metric called mean average precision, or MAP for short, that we can use to get, when we have multiple boxes over the same thing, we can actually, over the same true label here, ground truth, we can actually use this metric now to determine a map score, and that determines the form of accuracy of our object detector. So this one is actually a bit confusing. You can read some pretty long blogs explaining this metric that will help you understand. However, for now, just remember it's a metric used to determine the performance of object detectors. So now that you understand the metrics, we can go back onto the evolution of deep learning object detectors, and let's take a look at something called fast RCNN, which is an evolution of RCNNs by the same researchers. And what they did, they basically made some speed improvements over the original RCNN. The original RCNN was quite slow because it required 3 models to be trained separately and use them in conjunction when you're doing classification type work, execution in the end. And this required feature extraction model, an SVM to predict a class, and a linear regression to tighten the bounding boxes in the end. So you can see in real time this would be quite slow. So fast RCNN solved this problem by removing the overlap generated. Now how? What they did is that they ran the CNN across the image just once using a technique called region of interest or ROI pool. So essentially the problem fast RCNN solved was instead of running the CNN to extract features on all different regions identified, what they did, they actually ran the CNN just once over the entire image and then used those features going forward into the second and third layers of models in the network. So even still, that wasn't fast enough, and the researchers developed an even faster RCNN and named it appropriately faster RCNN. However, note there's no fastest RCNN just yet. So what the researchers of the Microsoft research team did to speed up RCNNs, or fast RCNNs, to give it the faster flavor, was that they eliminated the bottleneck that was involved when using selective search. So this sped up region proposal significantly as well. Which now brings us to something called single shot detectors, or SSDs. So we've just discussed and linked the RCNN family, and we've seen how successful they can be and how they evolve. However, typically they still run at roughly 7 frames per second, even on some fairly powerful hardware. However, SSDs and even YOLO are significantly faster, and you can actually see some of the stats right here. This is the FPS as well. You can see YOLO and SSDs topping the FPS at 45 and 46, and you can see the different scores and input resolutions as well, okay? So how did SSDs improve speed so significantly? Well, SSDs use multi-scale features, and they use something called default boxes instead of looking at interesting regions. And furthermore, they actually dropped the resolution of the images that were fed into the classifier itself. So this allowed SSDs to achieve near real-time speed performance with almost no drop in accuracy. And sometimes they actually saw improved accuracy with well-trained SSDs. So this is a general SSD structure. It's composed of 2 main parts. There's a feature map extractor, and VGG16 was used in the published paper, but however, ResNet and DenseNet may provide better results now. And then they use a convolutional filter for the object detection part of it as well here. So you can read the paper in this link here if you want to get an in-depth explanation of it. But just to summarize, SSDs are definitely faster than faster RCNNs. However, they are less accurate in detecting smaller objects. Now, accuracy increases if we increase the number of default boxes. That allows us to get a more finer grid on the image. However, that actually slows down the speed as well. And what it does with multi-scale feature maps, it allows us to improve the object detection at various scales. That's why we actually can increase the accuracy if we increase the density of the grid. So now let's move on to YOLO. So the idea behind YOLO, instead of using a lot of different models and networks and different sections to do different things in the object detector, YOLO uses a single neural network that's applied to the full image, and this allows YOLO to reason about globally across the image when generating its predictions. Now, it is the direct development and evolution of something called multibox. It basically takes multibox, which was used for region proposal, and turns it into object recognition, and then adds a softmax layer in parallel with the box regressor that combines everything into a box classifier as well. So you have the entire object detector built into it here. So how it works, it divides the images into regions and predicts bounding boxes and probabilities for each region. So YOLO then uses a full convolutional neural network, allowing for inputs of various sizes. And I must say, YOLO is one of the most impressive object detectors that have ever been built, and so nice to use, to train, to evolve into different situations. So now let's take a further look at it. And by the way, if you want to read a little more about YOLO, you can click this link here or go to the site here to read the actual paper. It's quite good and actually surprisingly entertaining as well. So how exactly does YOLO work? Well, the image is firstly divided into an S by S grid. And if the center of an object falls into this grid cell, that cell is responsible for detecting that object. So let's say this dog here falls into the center of this cell here. This cell is responsible for saying that this is a dog, technically. However, let's move on to the other steps and we get a bigger picture of how it works. So each grid then predicts a number of bounding boxes and confidence scores for those boxes. And now confidence here is defined as the probability of an object multiplied by the thresholded IU score. And IU scores of less than 0.5 are typically just given a confidence level of 0. Then, by multiplying the conditional class probability and individual box confidence predictions, we get something called a class-specific confidence score for each box. So you can see the steps here. We have all these bounding boxes here. You can see it proposes now a box region around this dog here. And this is all based on a class probability map. And then once it gets the final boxes here that it wants to classify, you can actually see the final detections here. And YOLO is quite good and effective in practice and quite fast. You can take a look at the YOLO architecture here as well, or if you want, as I said, I encourage you to read this paper here. Now, the architecture here has 24 convolutional layers and followed by 2 fully connected layers and alternating 1 by 1 convolutional layers to reduce the feature spaces from preceding layers. Now, this may not make much sense to you, but you can read the paper to actually understand the reasoning behind this design. So let's talk about the evolution of YOLO now, and it was voted the People's Choice Award paper at CVPR. That's a big computer vision conference. And then later on, YOLO Vision 2 was later released, and they would introduce batch normalization, which resulted in improvements in the map score by 2%, and it was also fine-tuned to work at higher resolutions. This is fairly high resolution for a computer vision object detection that is working in real time, I must say, and it could give a 4% increase in map overall. YOLO Vision 3 now was fine-tuned even further and introduced multi-scale training to help better detect smaller objects. So this concludes our discussion on YOLO. I hope you appreciated what YOLO has brought to the table. YOLO and SSDs are basically neck and neck in the 2 best type of object detectors out there. So now let's take a look at a summary of what we just learned. We learned basically the evolution of object detectors from hard cascade classifiers and hogs to the first deep learning object detector, which was RCNNs. Then we introduced fast RCNNs and faster RCNNs. We then explored single shot detectors with SSDs, which are also quite good and give quite good performance. And then we took a high-level overview of the YOLO object detectors, where YOLO Vision 3 is the latest one, and it's quite good right now. So now let's move on to the next video where we start taking a look at implementing object detection with SSDs and YOLO in Python using OpenCV 4. So stay tuned. Thank you. Hi, and welcome to video 6.5, where we take a look at implementing object detection with SSDs and YOLO in Python using OpenCV. So now let's move into our IPython notebook with our lesson code. So I want you to open file number 20, SSD and YOLO object detection, OpenCV. I already have my file open, so I'm just going to take a look at it over here. So the first object detection model we're going to explore using is an SSD trained with MobileNet, and this was trained using TensorFlow object detector. Okay, so before I actually step through this code a bit, it's not super complicated, but it can be tricky if you're new to this. Let's just run the code and see how it works. So what we're going to do, we have different images here, different trial images here with the actual label on the image itself, but let's just take a look and see what our object detector picks up. All right, so this was the original image here, and this is the extracted image here, and this is what it actually picked up, elephant. So you can see the bounding box is pretty good. However, it probably should have covered the entire elephant here, but I'm not complaining. It actually got the animal 100% correct, okay? So let's take a look at how it performs on some other images. So let's take a look at this traffic jam image I have. All right, so now let's take a look at this. So you can see it actually got almost all the cars in this image here, probably something that isn't a car over here, and it actually identified a traffic light accurately here. However, it missed this one here. That's not too bad. It's not too great either, but let's try it on some other images as well and take a look at performance on this one. So this is a laptop and a chair and a desk. It got laptop, it got keyboard, it got book in the end here. It got chair, which you can't really see because the keyboard is blocking the word, but it is chair here. So that's fairly good. I'm actually quite happy with that. Now let's try it on this one, which is a zebra and a giraffe, and it got both of them very correct. So that's awesome. Lastly, let's check out this one. Oh, apparently I didn't have the office image here, so I'm just going to delete that here. Add it into our data just in case you guys want to try it, but it's fine for now. So let's just leave it on zebra. Just run this code one more time, and there we go. So let's take a look at what's happening here with this code. How do we use this model that we're testing these images on? So I'm going to skip through some of this here. This is basically some image. If you noticed, all the images that outputted here were actually in this dimension. It actually cropped the images here. And that's because we have to feed the image into a specific size into this object detector, this trained object detector here. But for now, you can ignore this bit of code here. What this model here, this PB text file, points to a TensorFlow trained model, which is a SSD MobileNet version 1, trained on a Cocoa dataset. We have the frozen inference graph, which is actually the model weights as well. We have 90 classes, and we actually have a lookup here for the classes. So when we get a class in 0 or 1, it actually kind of uses it to put text on the image so we know what we're identifying here. And what we do here, this is where we actually create our model here, our net model, using this read from TensorFlow function in OpenCV. So we have our weights, we have our PB text, which we defined here and here. We have our threshold setting. We have a flag that indicates whether the first and last channels and two channel image is swapped. It's not super important. But actually it is important because if it's false, it's probably going to give you much worse accuracy because it's going to misinterpret the image. Then we have our blob, image blob from image here, which creates a 4-dimensional blob. And then this is what we use here to basically pull out our detections. So we have all of this stuff here just to get the image in the right format. And then what we do here, we basically check the boxes, make sure it's greater than the threshold here. And then what we do, we actually draw the rectangle over the image here, and then we get the class name by predicting and sending that box image here to get the text label. And then that's actually pretty much all it is in the end. So I should say detections are not done in here. The cycle iterated through here in this loop. Detections are generated from the blob over here as well. So you can take a look at this code. I may have brushed past some details. I may have gotten a little few things wrong because I'm trying to go through this quickly for you guys because this is more of a hands-on course as opposed to a theoretical, detailed explanation of everything here. This is something quickly that you guys can use and adapt to your own application. So if you wanted to build, say, an object detector that detects a baseball bat in a video frame, what you can do, you can actually just look at this here, and every time it gets class 2D9, you can actually put a box over it and ignore all the other boxes it's doing, and you have your baseball bat detector. So that's quite cool. So now we've completed this little brief exercise here on using an SSD. Now let's take a look at YOLO. So the YOLO is pretty awesome, as I said before. This code I actually adapted from another project I saw on GitHub, and I added in a lot more comments too as well to help you explain it. Now this one as well, it's fairly simple, fairly straightforward. It follows a very similar format here as well. We just get the weights, the config path from the YOLO. We have our images that we're going to test. So I'm going to loop through a few images in the directory I'm pointing to, which is images YOLO. And so those are some random test images I found. And then we actually just do the same thing here. We start timing the loop here just to see how it performs as well. We have all confidences and class arrays and boxes defined above. We iterate through the different layer outputs, get the detections from here, and then we just plot things that are confidence over 0.5, which is what we regard as a fairly accurate classification. We plot here. We just draw the boxes lower down here as well, but we just get everything here. We apply some non-maximum suppression. That is basically so we don't get overlapping boxes. Okay, something I didn't talk about too much, but you can look this up. Non-maximum suppression is a technique used when you have many overlapping boxes to get the best box or the centered box in a way. And then, yeah, as I said, we just put a label on the image. So this is a fairly good project here. So let's take a look and try it out. Okay, so it's got the elephant here, and it actually got a bird here. It's pretty cool. It's nice. Hot dog. Identified a hot dog 100% accurately. That is me, and yes, I am a person, and it's boxed over my entire body. And it actually got a boat in the background here, so that's awesome as well. This is the same desk area I had before. We have our laptop, we have our chair. It didn't get the books here, but that's okay. This is a living room setup. It got a clock, it got a potted plant over here, it got a vase here and a potted plant. That's actually pretty awesome. It got the sofa accurately. So you can already see YOLO is actually quite good. And this is actually an interesting one here. It actually got a truck. It kind of looks like a truck, more than a car, like an SUV or big van. This is a station wagon or SUV, got older version model SUV. It got all the cars on the road, the cars over here, traffic lights, both of them. So this is awesome. And again, it got the zebra and giraffe. You can't see text too well, but it is giraffe. So you can actually put as many images as you want into this directory here and just keep trying your YOLO detectors and see how well it performs. Alternatively, as a little homework lesson for you guys can set up this YOLO detector here to run on a video as well. Now you can see how slow the frame rate is here. However, it may actually work faster if you can do some sort of like algorithm where if there's not a significant change in the video screen, like if it's just like hovering on a scene of characters, you don't run classification here. I've developed that several times in some of my projects to speed up video classification. You only want to classify things when there has been a significant change on screen. So what I want you guys to do is adapt this code here, and maybe the code above too, whichever one you prefer, and adapt it to a video or webcam stream. So that's going to be pretty cool. So this concludes this lesson here on applying and implementing object detectors, a YOLO and an SSD object detection detector in Python using OpenCV. Now let's just summarize what we've learned in this video. So in this video, we've learned how to load these pre-trained object detectors in OpenCV. We experimented with SSD, mobile net trained TensorFlow trained model, and a YOLO trained model as well, YOLO vision tree. This one with 90 classes, this one with 80 classes. And then we just applied those object detectors to several different images to assess their performance. Now let's move on to our final video, which is a quick fun video on neural art style transfer. So thank you. Hi, and welcome to video 6.6, where we take a look at neural art style transfer, which is a very cool concept that you'll see shortly. So firstly, what is it exactly? Well, before we take a look at some example images, I'll talk about the original paper published in 2015, a paper that went viral because it allowed us to apply the artistic style of another image onto our image. So you can take a painting, like say Vincent van Gogh's Starry Night, and apply that style, that his unique artistic style in that image, to one of our images, it's our phone camera images or whatever, and get some very cool artistic pieces out of it. So let's take a look at some examples here. This is a picture of me, and this is the artistic style it applied to the image, and this is the output. So this is awesome. This is a picture I took of the Eiffel Tower, applying the neural style transfer from Vincent van Gogh's Starry Night. And this is another one here, just a generic selfie of my wife and I, applying this artist painting here to it, and look at the cool output we get. So we're going to do all of this in Python shortly, but before, let me explain the concept of what's happening here. The magic in neural art style transfer isn't in the architecture or the lengthy training process, but it is in with our special loss functions, which we'll describe shortly. So before we get into that, remember, you can visualize what convolutional layers learn. Imagine this is the lower layers here. They learn just little patterns and small details like this. Then as you go to the mid layers, you can see more defined patterns as we go. And then the higher layers actually learn a lot more complex patterns. As you can see, it's a face here. And this is like pieces of nose, eye, and these were just like edges and little blobs of patterns and colors there. So what does this mean? It effectively means that convolutional layers store details about the image or the training set that it works on. So basically, you've seen that a convolutional neural network in the weights stores some sort of information about the image or about the training data set that it was trained on. So given that, is it possible we can use this knowledge that is stored within a convolutional neural net, trained CNN, to apply some sort of metric or some sort of hierarchy of knowledge stored in that network or that model to another image? And that is basically the key basis of neural style transfer. Okay, so now let's take a look at a high-level view of the process whereby how we enable neural style transfer. So firstly, imagine we start with a blank image of random pixel values, and then what we do, we keep changing those pixel values as to optimize a cost function so that we keep our pre-trained CNN weights constant. Remember, we want to preserve the content of the original image while adopting the style of the reference image. The reference image being, say, Vincent van Gogh's painting, and our original image will be the selfie that, say, you have that you want to apply this style to. So let's take a look at the cost functions that I mentioned that we are trying to optimize, okay? These are two cost functions. Well, they consist of two parts, essentially. There's the content loss and the style loss. So let's take a look at the content loss. So remember how our filters learned special decompositions of an image. Remember those high-level and low-level features we talked about? Now you can assume that the high-level features of the convolutional layers, that's the top layers of the CNN, store the global representation of the image. Remember, let's go back to it. You can see how these are the top layers here. They actually store a lot more details about the image training dataset that it was trained on, in case it was a faces. So therefore, our content loss can be defined as the L2 norm. It's a distance metric between the activations in the upper layers of the pre-trained CNN computed versus the target image and the activations of the same layer computed over the generated image. Now, this is a bit much to digest, but you can read this and take a look and see if you understand it as well. Now, this ensures our generated image retains a similar look to the original images. So effectively, what the content loss function is doing is that it's making sure that the content present in the content image is captured in the generated image. That's all that we're trying to do. So let's talk about style loss now. So while the content loss uses just a single upper layer of the convolutional network, so it's the upper layers here, the high-level layers, this style layer is composed of multiple layers of the CNN. And why is that? That's because we're now trying to capture the styles from the reference image at all spatial scales extracted by the CNN. So we want all our low-level, mid-level, and high-level details from our reference image. And our reference image is our original artistic styled image that we want to copy onto our image. So now for the style loss, Gathis, who is the original author of the paper, uses something called the gram matrix of a layer's activations. Now, this is the inner product of the feature maps of the given layer. Now, this inner product can be interpreted as representing a map of correlations between the layer features. So now the style loss aims to preserve the internal correlations within these activations of different layers. So now, a bit confusing to keep track of everything that's going on, especially if you're new to this. But effectively, we do all of this just to ensure that the textures between images look similar. In theory, it actually works quite well, as you'll see in your code shortly. So now we have our content loss and style loss, and we can now use any optimizer to perform gradient descent to now generate our new image. This is basically written in a formula or mathematical way. Now, this is just a graphical illustration of what's happening during the training process, so where we have our target image here, and we're basically just trying to minimize the content loss and the style loss here that are basically coming out from the content image and the style image, basically using the VGG pre-trained network to extract the layers as we specified before. In this representation, the content image is the artistic or the reference image. This is our image that we want to get our style to. So I hope this illustration was at least somewhat helpful in understanding the concept here, where we try to find a balance between loss and style loss, where we're trying to minimize both effectively to generate a perfect target image that is taking the content representation and the style representation of our two images and generating a suitable and appropriate and aesthetic target image. So now let's move into our IPython notebook so we can apply this to some images. So now let's open file number 21 called neural style transfer. And just in a couple of seconds it comes up, and here we go. So now these are the artistic styles, missing a C here. These are the artistic styles that we're going to use to apply to our test images. So let's take a look at the code quickly. Now the code is actually fairly simple. Now I can run through this code before we actually apply it, which may help you. So what we do firstly, we load something called our T7 neural transfer models. These are the models that were trained on each artistic style here, so that we can now apply it to our input images. So we have our input images here. We have our Eiffel Tower image that I'm going to test it on. So now what we're doing here, we're just going to loop through each model here, each model in the model file path that it finds here. So we have these 1, 2, 3, 4, 5, 6, 7, 8, 9 different models that we're going to loop through and apply the artistic style to our Eiffel Tower image. So what we do, we just simply point to the directory that has the original painting that we're going to apply. So that's going to be another folder here. Bring it up for you guys as well. These are the files in the artistic style directory that we're going to use to generate our style. You can see we have these 9 paintings, these 9 famous paintings here. So firstly, what we do in the code is that we get our neural style transfer model here, just pointing to the path of the model above. And we take the model, actually, we take the image here. We just get a height, width. We resize the image a bit. And then we use something called the blob from image, which you have seen in the previous video, I should say. We take our resized image here and we just set some parameters here, with cropping being full in this scenario. And then we use this to apply a forward pass to apply this model that we loaded previously here to our image. And then what we do, we just reshape output tensor, and by adding back the beam subtraction, reordering the channels, that's done here. These are the parameters that we have to use. These are fixed values. And then we just show our style. So it's maybe a bit confusing for you guys to understand exactly what's happening here. If you want to learn more about what's happening, what this does, this is how we get our model. This is where we get our image and apply the model to it. And this is where we get the blob, and then we apply the model over here. And so you can actually read some of the papers on this, some tutorials online that have more detail. But for now, let's apply this code to our image and using the different artistic styles I listed here and you saw in the Windows File Explorer here. So let's try this out. So there we go. So this is the image here. This is the original image, I should say. This is our original artistic style, reference image. And this is the output. So you can see this is actually quite cool. I actually love how this looks. This can actually be an art piece in my bedroom somewhere. Let's take a look at another style. This one, it's pretty cool. It's not as cool as the first one, but it is definitely impressive. I think this style here is actually a bit complicated for this model. I mean, we need to make some adjustments to get the detail that you see here and apply it appropriately here. But nevertheless, this is still quite cool. This one actually works quite well. It's just simple feathers, like hand-drawn shaded feathers here. And you can see it actually looks quite good. It actually picks out blobs here of it, keeping the structure and style of the image intact. But then you see the shape is quite good and it has different emphasis at different points. This is all very impressive. Let's take a look at another one. This one, actually, I find all this works pretty well. I guess it's because it's actually simple textures involved here and it actually learns different pieces. You can see it uses this artistic style here. You can see it uses the blue on this region here. You can see it uses the body style here on parts of the tower, so it's quite good. It uses the picture frame or the mirror frame here on other parts here. So I actually love how this looks as well. This one I actually find works impressively well. This is colored window pane here, and you can actually see how it looks. Stained glass is actually the word I was looking for. And you can see it kind of generates this artistic style in the same sort of polygonal alternate colored form. It looks mighty impressive. This actually looks awesome, I should say. Now let's take a look at Starry Night, I believe is the next one. Yes, it is. And this one, again, it is pretty cool. However, I find that maybe they could have had more emphasis maybe using here, on this region here. But that's okay. It actually looks quite good as well. There's still too much detail from the original image here for my liking, but it is quite good still. This is a famous picture called The Scream as well. And actually it very much captures the nicely textured areas here from this painting. It doesn't actually look too much like the style, just the color palette is identical, which is awesome. And I think this is the last one here. This is one wave. It looks pretty cool. It's not as cool as I would imagine. I think it's a bit repetitive sometimes with using this pattern in it, but that's okay. And yeah, this is, I think, is the last one here. This actually looks quite good as well. And there we go. So you can see we've ran through all the different models here. And this is a very impressive tool we can use to apply to different styles. So this concludes our lesson here. The only thing I wanted to add here was take a look at the models here. These T7 models and this function here, you may be able to just read from Torch. OpenCV can now read pre-trained models from PyTorch, from YOLO, and Café as well. So OpenCV 4 allows some very cool features with using pre-trained models and applying it in Python using OpenCV as well. So this is the last lesson in this course. I really hope you enjoyed this course. Let's do a quick recap on what we've learned in this video. We've learned basically what is neural style transfer, how CNNs learn, and how they visualize their filters, or what they actually see when visualizing their filters. And then we use some concepts of content loss and style loss to build a diagram matrix and then learned how we actually perform neural style transfers. And then we actually use that pre-trained models to apply to our own images using OpenCV in Python. So now this concludes our course. Now let's take a look at a course recap. just to further consolidate the knowledge you've learned in these last few hours of these videos. So firstly, we took a look at some basic computer vision concepts and introduced OpenCV4. Then we started using OpenCV4 to do some more image manipulations, things like cropping and scaling and dilation and erosion. Then we started using OpenCV for image segmentation like contouring. We actually did edge detection here as well, so didn't want to leave that out because it's a very important concept. Then we actually used horror cascade classifiers in OpenCV to do some face detection and eye detection and vehicle and pedestrian detection. Then afterward, we started to take a look at machine learning and deep learning in computer vision, where we took a look at how neural networks work and how convolutional neural networks work. And in section 5, we took a look at a deeper understanding of CNNs, like how different parameters affect their training times as well. Then we used our own CNN and our own data to build a gesture recognition system. And then later on, we built our facial recognition system, which was all pretty cool in my opinion. And then afterward, final chapter, we started to take advantage of pre-trained models. So we looked at some pre-trained ImageNet models to do some object classification. And then we took a look at transfer learning using the CIFAR 10 dataset. And then afterward, we spent a lot of time with building up a theory for object detectors using SSDs, RCNNs, and YOLO. And then we actually applied YOLO and SSDs to some images in Python. And then lastly, we took a look at neural style transfers, and we actually implemented our own neural style transfers using OpenCV, some pre-trained model in OpenCV. So I hope this course was very helpful and enlightening in your computer vision knowledge. There are a lot of theoretical details that we may have left out because this is such a deep mathematical and in-depth topic. You can spend days and weeks maybe just on one particular area of computer vision, for example, YOLO or SSD. We are researchers that spend basically years of their life in adapting and building upon these concepts. So I don't expect you all to understand all of the mathematical theory, but what's good in this course is that it brought these concepts to you at a very high level, and even better, you are able to implement all of the concepts that we talked about in computer vision in Python using OpenCV4 and TensorFlow and Keras. So what's brilliant about this hands-on course is that you can actually now apply so many advanced computer vision concepts to your images or your videos, or even implement things like your own facial recognition system or train your own convolutional neural networks on your own data. So this is a brilliant course, and I really hope you enjoyed it. So I really thank you guys for taking the time to listen to me and listen to my lectures on computer vision. Thank you.